Daniel, can you hear us?
Yeah, you guys sound good.
Okay, cool. Did anyone upload their presentations for today?
So they're not going to be uploading their presentations because it's in the Damon room, so they don't need to.
Okay.
So everyone's going to be managing it from that system, from your guys' computer.
Okay,
The remote people will just be sharing their screens.
got it.
So yeah, I guess we don't require them to upload them beforehand for like the Damon room and the Chapman room. But for main seminar room, multimedia definitely requires us to have them ready.
Got it. Makes sense. Okay, so will they share from their laptop?
I don't think they're gonna need this computer then.
I don't think so either.
Yeah.
Okay.
We can leave as a backup, but. Right?
Yeah.
But I don't think they're gonna use it. But if they do, then they just need to grant us access to the hub. No, they would share those documents with us, right? With you.
They could either share them with me and then use this laptop to screen share, or they could just join the meeting and screen share from their computer.
Yeah. So I don't think they're gonna use this computer.
Okay.
Yeah, or they can, or if anybody asks, I mean, we can definitely still have them send them to upload them onto the drive because I've gotten one of them for tomorrow, but
Yeah.
we can still use those drives. There's two presentation folders in the land and ice. There's one for polar, and then there's one for land, and so we can just save them into those folders. We just have to make sure that we use that naming convention example, so just so that we're all on the same page.
Yep. Yep. I'm in those folders now. So cool.
Awesome.
All right. I think we should be good to go.
Okay, we are starting to record too now, so just FYI.
Yeah, and hey guys,
Right.
Alec, I was just going to ask about maybe testing, sharing my screen, or
Yeah. Go ahead.
is that the recommended way, or would you? I just emailed in the PDF, but is it better just for me to share my screen?
I think it's easier for you to drive because I would have to change your slides.
Yeah.
And I don't know the cues.
Yeah. No, my screen.
Oh,
You guys can see that?
yep. And it's on the big screen. Is
Okay.
there a way to like present? Oh, yeah. Perfect.
You guys can see that okay?
Yep. It looks good.
Awesome. And you can hear me okay?
Yep. I can hear you well.
Awesome. Thanks, guys. Appreciate it.
Oh, thanks for testing it out.
Yeah, I feel like I've been on too many of these things that have gone terribly. So
I feel that.
trying to get better at joining earlier and testing.
Yeah, absolutely.
Okay. Thanks again. I'll just turn off my mic and video for now, I think.
Yeah, we should be starting in like 10 minutes.
Any issues?
Nope.
Ooh, awesome.
You got it. We're good to go. Maybe turn the volume up a little. Yeah.
Yeah, so we can turn from here, right? From the pad.
Oh, yeah.
The
Yep.
pad are right there. Let's turn.
Hello?
Hello, hello.
I guess we're not going to hear ourselves. Okay, cool. Cool.
It's going.
I want to check on the speaker consent.
Yes, the baby is already signing them.
Okay, good.
Yeah.
Because we are keeping track here.
I
But
don't know.
a lot of people still haven't done that. Looks like. Oh. I think that was him.
So who's the first representative?
The first is Ed Blanchard Wigglesworth.
in person?
Yeah.
And they are outside?
Yeah,
Okay.
all the grayed out
Oh,
are
I see.
internal,
Oh, I see.
so we don't need it.
Good morning. Did you get a chance to sign the statements on stage or?
I'm still an in-car employee.
Oh, you are. Very good.
But I'm good.
Yeah.
How are the speakers doing the talks from their own laptop or from?
Whatever you prefer. This loaner laptop, you can send the presentation to and share from there. Or join the Google Meet and present.
I'm just gonna go towards the mountains.
Yeah, I'll try that and see if I can get on the Google Meet.
Whatever you.
How are you? Hi.
How are you doing, Ash?
Good. I got a little extra early this morning, and normally I walk into work, so.
Oh, wow. I, for some reason, thought this started at 8, so I also got up.
Morning, how are you?
Good.
You guys gonna record this?
Yep, it's already recording.
Oh, all right.
Yep.
We can only stream the MSR.
And then, what do you
Try to work with different times.
That's a Daniel question. Hey, Daniel, I think we're uploading it to the YouTube channel.
Okay.
Yeah.
What are we
Yeah,
doing?
we're gonna be, yeah, Paul, we'll take care of the editing and then we're gonna upload right after onto YouTube.
Okay. Can you hear me?
Okay, no, so she said.
Yeah.
So, just so you know, we can't record until you're actually ready to start the meeting because of privacy issues.
Okay.
If, I know you're gonna edit this, but if somebody walks into the room and they're talking about something that's, probably not, maybe appropriate or something, it'll pick it up and then, that's a liability. So if you could stop the recording until you're ready to go, and it'll be a cleaner edit for you too.
For sure.
So just so you know, okay?
Yeah, so what is the time that maybe we can record? Is like 5 minutes beforehand?
Yeah, like 5 minutes before, and then just let people know, hey, I'm starting the recording, just so that they stop the conversations and everything's ready to go.
Okay, yeah, we'll definitely do that.
Okay, all right, thanks.
Yep.
Let me know if you need anything. We'll be in the meeting too, just kind of monitoring. So if anything happens in here, we'll be able to come up here and check it out. Okay?
Thank you.
Well,
Thanks, Danielle. Sorry.
yeah, no problem.
Hey, Marika, it's Alec.
Hey, Alec, how are you?
Good. How you doing?
Okay, I'm sick, so I'm
Oh, no,
participating in the morning meeting from home. But
Mm.
yeah, I didn't want to cough all the way through people's talks. This way I can mute myself.
Yeah.
How are you doing?
Yeah, pretty good. Pretty good. Yeah. Sad not to be there, but I guess I haven't missed you now. But yeah, no, things are good.
Good. Yeah, I really wish I could participate in person.
Next year I'm going to be there.
Yeah.
IVAR meeting next month, and I was kind of debating going to, so I got a bit confused.
The big screen.
8:47.
Have you been here before?
Bangor, yeah.
Okay.
I haven't been in this room before.
Yeah, I love this room. It's like. You know the beef you're probably too young for this beef. It's What's for Dinner and soundtrack. No. Okay. Anyway. Soundtrack Colorado.
You did not see any of this?
Let me make your glass. Thank you. I'm Megan, by the way. Tree, by the way.
I guess, are either of you presenting?
I'm not.
You are, yeah, you're on the schedule. Did you send your presentation?
I sent him my PDF. but I don't know if I was supposed to-
Sorry, running late, had to get coffee.
I should confirm, because I didn't send them to anybody.
Hi,
Oh,
How are you doing? Not.
sorry.
I know. Thank you. Are you a hugging person? Do you want a hug?
Yeah, we know. Yes, kind of. I'm not gonna. Okay.
It was luckily very quick.
Okay.
Sure.
Yeah, so you can join the meeting
Tuesday and then
woke up early in the morning.
Or you can send
Like an hour later.
It was okay, so I'm really glad it was
Okay.
quick.
Sorry.
And then just. I mean,
Okay, that's totally easy.
Yes.
Okay.
I haven't on a class yet. Yeah, it's just, it's kind of, it was very shocking. She has such good help.
Okay. I just
And
don't
then
think it's
she-
ambiguous.
and then
Yeah.
Whereas
I think I have a similar.
I'm glad. Okay, cool. Anyway, I know I get it.
That's the loaner laptop.
Thank you. If you need,
I
know this can't replace
work,
but with other, if you need dog cuddles.
Thank you. You can also just.
I've still got my puppy meeting every Tuesday.
Right.
I have a tremendous amount of puppy time.
Okay.
Oh, man.
She'll go quicker. Okay, I'll just, probably just present from your own laptop. So,
Okay, so we don't-
jump off.
I did, I redid my analysis yesterday and it looks very scary now. It looks very different.
I saw your thing this morning and I
Okay,
was like, this
now
looks
go
really
back.
different.
Yes.
And then I was like,
Don't,
I'm not gonna worry about this right now.
yes,
Now, there
I-
should be a little.
yeah,
bit
I know.
down the
I am
bottom
aware.
that is.
I'm looking for what I've done wrong. Oh, man.
Just put the
So,
rainbow one back on there. It's fine.
We're gonna
It's
get started in about 5 minutes, just a second, so we're covering.
for the rainbow file. So it's either the rainbow
Oh,
or,
I still have the old.
yeah, I have that too.
But yes.
And then you should change the okay.
Yeah, I liked the other one better, but I know that one's wrong. This one feels wrong, but I think it's right. Anyway,
I also struggle with the colors because I like rainbow colors in general,
Mm.
but I once got like a reviewer was like, I can't rate any of your stuff because I had like, it wasn't rainbow, but it had
Where is our
red. So now I'm usually
second speaker of the day?
the yellow is bad too.
No,
It's
I'm
not, it's
second.
not very readable. So you're
Okay,
really right
well
about that.
then, that's even better. Where is our first speaker?
Because I'm so glad you had your tea. I was concerned. You wouldn't have enough supply.
this is like a true, like, you know, the Stanley craze or whatever, like you're
Yeah,
hard.
well, we might put you first, David, just if
Oh.
Ed's running a little late.
I bet he might be on the shuttle that gets here like at 9.
Yeah, yeah,
That would be
yeah.
my,
That
Yes.
should be fine, so.
Okay.
you're welcome.
Let's see.
So, yeah, did you hear that, Marika? Ed's not here.
I heard that, yeah. He'll be there.
Yeah,
We could shift things around if needed. We could
yeah,
start
yeah.
with the welcome. I'm really sorry I'm not there, everyone. I just don't want to cough on all of you, and I'm kind of coughing nonstop. So, yeah. And Courtney, I just looked at your poster. I'm sorry I didn't get to you earlier.
No, no worries.
And it looks great. So,
Except for the figure, which looks not right.
oh, the PPP? No?
Yes. Anyway, I'm working on
Okay.
sorting out the actual values, but thank you so much, Marika.
I should take a closer look.
Look good. It's all wrong. I'll look again.
So,
You know what? Whatever.
And it looks like there's coffee and snacks. Is that?
indeed, yeah, Gunter outdid himself yet again. And he's not even part of the Polar working group, so.
Yeah.
But maybe that's incentive for people to go to the land ice tomorrow.
Yeah, thanks to Dave for the coffee and Gunter for the snacks. Another reason I'm bummed to be missing the in-person part.
There he is. Hey. Have you tried your internet this morning? Okay,
but
if you want, you can go to my laptop, whatever.
I'll drop it.
Yeah, we have two, so. All right.
Last time it was a big kerfuffle.
No, I. Okay, we'll get started in about a minute here. Just to make sure I got all the talks I need.
A keynote, right?
Yeah, I have keynote on my list if you.
Let me just drop it to you.
Yeah, sure. That sounds good.
You're the hurricane.
I am the hurricane.
Maybe we should start calling him that. Oh, the hurricane's in the room.
I have a schedule pulled up.
Dallas is
I'm Hazard.
You're hazard.
But my last laptop was Schlepp.
Marika, do you have,
which is some
slides
city
you
in like
wanna
northern
start
Africa. They were
with, or-
going through some like city phase. I was like, how am I supposed to say this word? Like, it's not.
You didn't get to pick?
No, they choose them.
Oh, I was Nej,
Mhm.
which was very appropriate.
Yeah, as long as I've been here, I was like, can I have a different name? And they're like, no. Maybe if you're fancy enough, like maybe Marika.
Ah,
I don't like this name. Give me a name.
but not for,
You just say, here's what you said.
I don't know, some random city in Africa. It's fun.
I learned a new thing. So
Now you're Hazard.
Dave, did you ask me if I had a slide I wanted to start with?
Yes.
So I don't.
Okay, that's fine. I can.
But yeah, I guess just in terms of welcoming everyone, I'm really sorry not to be there in person. I would have loved to be in the room with you. Fortunately, I'm sick and I'm coughing a lot, and I don't want to disrupt everybody's talks with my coughing. So I can mute myself online. So I'm going to participate this way. But it's great to see everybody there. And Hansi, who's the other co-chair of the Polar Climate Working Group, is going to be joining off and on. She has some other commitments today, so she isn't able to be here for the whole meeting. And Dave, the Polar Climate Working Group liaison, is going to be running things in the room and also provided the coffee. So thanks, Dave. So yeah, it's just good to see everyone. I'm glad that, people are able to be up at the Mesa Lab and meeting in person. I'll turn it over to, I guess, Dave in the room or anything else.
Yeah, sure. So logistics wise today, if you want to join from the room, that's great. But we would prefer if you go on companion mode under the Google Meet. So if you're just logged on regularly from the room, then log back out and there's a little option over in the lower right to join in companion mode. So you can present from your laptop if you want in companion mode, or you can bring slides up here, send them to me, anything like that, and someone else can present them for you. So we don't have the official code of conduct slide, but I think there was some agreement forms out there for you to sign. Basically just, treat everybody with respect and, respect all questions and please try to get along. So, anyway, basically with that, I think we're starting off with Ed Blanchard Wrigglesworth in person. So I'm gonna see if I can speak. Do that. This the right? Yep. And then slide mode. It's like right. Okay.
So
Take it away, Ed.
people hear from me from here.
Yes.
Should I go over there?
Oh, no, it's fine. It's just the mic's right there. So yeah, help yourself.
Well, okay. Yeah, I'll just switch with these. I'm Ed. I know a few of you, and if I don't, hi. It's really fun being back in person at these meetings. And today I want to share some work understanding and in the recent winter 2023 Antarctic sea ice anomaly. This is work that we've done at the UW, and that has been led by my grad student, Zach Espinosa, who is a really fun student to work with. And if you haven't met him yet, I think you'll meet him soon, because he's done some really good work. He's been co-advised with Cecilia Bitts, who I'm sure quite a few of you know. As a little bit of motivation, I'm showing here on the, yes, Alice.
I was just gonna say, do you want it to be, is there like a full?
I don't know why.
On my screen.
It's full screen on
it's-
this one.
On this one, it's full, and I don't know why.
Okay. I just,
But I don't know, Dave, if you wanna see if you can, maybe from the Microsoft Teams, it's never used Microsoft. So a little bit of motivation on the left. I'm showing a time series of the Antarctic sea ice extent in June, July, and August, which is the austral winter, which from now on I'm just going to call winter. And you can see kind of that, relatively flat or slightly positive trend from 79 to about the mid 2010s. And then we had a bit of a decline, but things kind of returned to normal. And basically the main message from that time series, and you don't need to know statistics, is that what's happened in the last year is new. We haven't seen that happen before. So we've had a huge negative anomaly. And if you plot all months of the year for every year, which is shown on the right, you can see the seasonal cycle, but you can see how in 2023, we basically got really far outside from anything we've observed in the previous 44 years. And if you plotted this as a normalized time series, and there's a big asterisk, I'm not saying this follows a Gaussian distribution, but if you played the game of like saying, okay, how many sigma anomalies would this be? Then the 2023 anomaly is bigger than a 5 sigma event, which if you look at the statistics is a very, 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 very small factor. Right? So something pretty weird and new has happened in Antarctica in 2023, and we were curious about this event, and we've developed, with many thanks to NCAR and CSM, we've developed this sort of nudging tool where we take CSM or CSM2 and we nudge to the observed circulation, and we've kind of understood, or it's helped us understood a lot about the 79 to 21 trend and internal variability, and we were curious about how would the model do if you expanded that or extended that to 2023. I don't know how I get rid of that at the bottom of that. Am I click on that little hide? I'm sorry, I don't know where my mouse is. No, advantages. Okay, live with it. So essentially, what we do is we run CSM2, kind of like the same model as the CSM2 light ensemble with the same forcing, but what we do is we nudge it to the observed winds from era 5, and we only nudge the circulation south of 45 south, so over the Southern Ocean of Antarctica, and we do it from 1950 onwards to present, pretty much. And we ask a few questions, like the first question is, does the model reproduce the observed anomaly? And if so, what can we learn about the causes and predictability of the 2023 event? And a couple more specific questions is like, we know that ENSO had a big shift from La Nina to El Nino last year, and there's been a bit of noise or questions about did that have an impact on the anomaly? And also how much of the anomaly was predictable, say, a few seasons before. So I'm going to call it CSM2 nudge, right? This kind of version or this run that we do. In observations, to dig a little bit more into the observed anomaly in the winter, on the top left, I show the sea ice concentration anomalies for the winter, June, July, August. In shading, I must have gone the color bar, but the red is negative anomalies. And you can see that we had negative anomalies pretty much everywhere apart from the Bellinghausen, where we have positive anomalies. The magenta shows the climatological sea ice edge, and in black is the sea ice edge in 2023. In the bottom left, that is the circulation anomalies. The shading is the sea level pressure anomalies, and the arrows are the wind anomalies. So you can see that we had a very strong anomaly where the Amundsen low is, with the high sea level pressure anomalies. So we had this anomalous anticyclonic circulation, right? So we had northerly winds in the Ross, southerly winds in the Bellinghausen. But if you look at the rest of Antarctica, there is a bit of a wave 3 pattern going on, right? You can see also the positive sea level pressure anomalies in the Weddell and East Antarctica, and negative in between. But the fairly small, I can't. I don't know if I get, okay, maybe. All right. And then try play again.
Sorry, messed everything up.
So much better, thank you.
I'm not very good with computers, so thanks for that. So it's kind of interesting, right? Like if you look at the atmospheric circulation anomalies at the same time in winter 23 as the sea ice concentration anomalies, you can kind of, it helps you understand the Ross and Bellinghausen anomalies, right? Because we have northerly winds in the Ross, southerly winds in the Bellinghausen, but in the rest of Antarctica, we have very negative sea ice concentration anomalies, but the atmosphere isn't doing much. And on the right, this is a time series of the meridional winds along the sea ice edge. So the winds are in red. Positive values are southerly winds, negative values are northerly winds. and the black is the CS concentration anomalies. And you can see that, you can see this correlation, right? So there's this, agreement between the two time series, but you can see that in the Rosen and Bellinghausen, northerly winds give you negative CS area anomalies, and southerly winds give you positive CS area anomalies, as you might expect. But if you look at the Weddell and East Antarctica, there's like an offset from those two time series, right? So yes, where you have southerly winds, you have less negative CS area anomalies, but you're still not getting the positive area anomalies, right? And this will come back later in terms of mechanisms. And so there's probably something else going on, especially in the Weddell and East Antarctica, right? That there's the circulation anomalies the synchronous for the instantaneous circulation anomalies in the winter of 23 don't fully explain everything. So CSM2 nudge, how does it do? The quick answer is pretty well. So in the top right of the CS concentration anomalies that the model simulates, the bottom right is the sea level pressure in the wind anomalies. Now, by design, we want that to look pretty similar to the observations because we're nudging the circulation. And you can see for the most part, it's getting that big Amundsen low positive anomaly and then that wave 3 pattern. And when we look at the time series, now the top panels are the sea surface temperature anomalies in the winter, which kind of, they correspond with the CS concentration anomalies pretty well, right? So where we had negative CS concentration anomalies, we have positive CSCP anomalies and vice versa, which is what you'd expect. And the bottom, I think it's a more interesting figure here, is the time series. The black is the time series of the total sea ice area anomaly, and it's the color bars are broken down by regions. And you can see basically that the CSM2 nudge does a pretty good job at simulating the winter 2023 anomaly. It gets an anomaly, it's even a little bit bigger, it's almost 2.6 million square kilometers. In the observations, it was more like 2.5. And if your eye sees like a fairly good agreement in terms of the colors, like the regions that are leading to those anomalies, then that's the truth. Now, I do want to say for the summer sea ice problem, CSM2 nudge is maybe not the best tool because basically it loses most of the sea ice, right? So you can see that the anomalies around the start of the year, like in February, they're pretty close to zero, but that's just because there isn't much sea ice left in the model. There's a bit of a negative mean state bias, but I think for studying the winter problem or sea ice, it seemed to be a pretty good tool. So at least for that first question, we claim that it does a pretty good job. So now we can dig into mechanisms. So the first thing we did is get to this question about ENSO. This is the time series of the crosses of the weekly ENSO 3.4 index. The kind of that sort of filtered color time series is the monthly one. So you can see that in 2022, we went from La Nina, and there's a pretty quick shift to El Nino in early 2023, right? So there's this question of, well, did this play a role, right, with this anomaly? So what we did is we calculated the linear relationship between the ENSO index and the winds at every grid point in the observations. And then we regressed the ENSO index of 2023 out of the observed winds from 2023. So we produced this kind of synthetic 2023 winds that have the ENSO signal removed. And then we created a new nudge simulation starting in January 1st of 2023 that nudges to these new winds that basically have the ENSO winds or the ENSO component, the linear component of ENSO winds removed out of them. And we call that run CSM2 nudge, no ENSO. And this is the results. This is the time series of the total sea ice area anomaly. The top, just for 2023, but the top row for that top panel is just for the original CSM2 nudge run that just nudges to the absolute observed winds. And then the middle one is the panel, is the figure of this new run without the ENSO component of the winds. And they're very similar. And the bottom one is just the difference between the two. And the y-axis is different, right? But it's only 0.1 million square kilometers less sea ice, less of an anomaly in CSM2 nudge no ENSO, which is about 4% of the total. So we found that actually ENSO, at least these results hint or indicate that ENSO actually had a very small impact on the anomaly. And one of the reasons for that is that the winds are not actually that different, right? That the anomaly, so what I show you here are the winter 2023 circulation anomalies that go into, or basically the winds that the model been nudged to. The left is the original run, and the right is that no answer run. And you can see that, yeah, the amplitude is a little bit smaller, but we still have that massive Amundsen low anomaly, and that wave 3 pattern is still present. So reason number one is that the circulation itself isn't that different once you regress pencil out of it. There is a second reason, which will be clear in a little bit. Then now going to the question of, was this anomaly predictable? We were kind of curious about this, and I think it does. I think it helps explain or understand quite a bit of the processes, and hopefully that will be from taken also in a couple of minutes. But what we did is we run a forecast ensemble where we basically took the initial conditions from CSM2 nudge on January the 1st, 2023, and we kept running the model, but nudging to past year's winds. And this is a technique that or models that produce forecasts with ice ocean models have used in the past, because you're like, okay, what atmosphere do I use? Well, you can use an ensemble of past year's atmospheres. And so what we did is we produced a 20-member forecast ensemble nudging to past year's winds, but continuing from that January 1st, 2023, right? So whatever the ocean or whatever kind of predictive information might have been in the ocean or the sea ice from January the 1st, 2023 would have been carried forward, but with past year's atmospheres. And one of the key things is that the mean of that forecast ensemble has to be kind of close to climatology winds, because if you just randomly pick years that had one anomaly in the circulation or another, like, well, that's going to affect your forecast, right? But what we found, and this is the panel on the right, these are the winter 23 surge concentration anomalies in that forecast ensemble. And remember that that forecast ensemble doesn't have that strong winter 23 Amundsen low anomaly and all that I showed you before. But it gets about 2/3 of the observed pattern in CS concentration anomalies. Now you could, especially in the Ross and in the Weddell, it's not quite as strong as what we observed, but especially in East Antarctica and a little bit the Weddell it is, right? And basically this is what this is telling us, is that 2/3 of that signal was in the ocean, was kind of baked in by the end of 22, and it's basically a very warm Southern Ocean. And then what happened in the circulation in the winter sort of emphasize that, and in terms of the regional anomalies, then helps explain what happened in the Bellinghausen and the Ross a bit more, right? But when you look at the time series, we basically forecasted 2/3, right? So by I think January 2023, I think we could have made that forecast in real time back then, because we had past year's winds, and I think we could have maybe hindsight's right? But I think the signs were there, kind of preconditioning us for very low winter sea ice cover. And so what I show you here, the top panel is again the time series of the sea ice area anomaly from the original CSM2 nudge, and then that middle one is from the CSM2 nudge forecast. The bottom one is the difference, which you can think of as the forecast error. And you can see that the forecast error is very small till May, and then it does get a bit, we don't quite get as strong of a negative anomaly, but that's because that strong winter circulation is like giving you more of a negative anomaly, right? And if you break down where most of the forecast error is, it's in the Ross, and there's a little bit in the Bellinghausen, but that's because that's where that big Amundsen low anomaly was, right? So it makes a lot of sense knowing what those circulation anomalies were, which themselves were probably not predictable. So the bottom line is that it seems about 2/3 more or less of this anomaly was kind of baked into the ocean 9 months earlier. And we can see this looking at the SST anomalies in the Southern Ocean between 50 south and 60 south, which is shown here. This is a Hofmöller plot. So longitude along the x-axis and time along the y-axis, going from 2022 at the bottom to winter 2023 at the top. And the black line, that's when we kind of start that forecast, right? And you can see how the SST anomalies really persist into the forecast. They don't become quite as pronounced as in CSM 2 nice, but that added punch from the circulation. So in summary, Antarctic sea ice has reached this very much unprecedented minimum in this past austral winter. I think it's a great kind of modeling success that when the CSM2 is nice to observations, it does a pretty good job at simulating that anomaly. We found that ENSO's a pretty small impact. One, because it didn't actually affect or didn't seem to affect the circulation that much, but also, and this is what I hadn't quite explicitly said, is because so much of that anomaly was already baked into the ocean that it almost didn't matter, right, what the ENSO state was going to be, right? So, you know, basically ENSO was affecting a bit of the wind, but the wind was like 1/5 the total anomaly at the end. And then as shown by the predictability runs, you know, like a good chunk of this anomaly was sort of like it had a 9-month predictability, which is pretty long lead time. And I think the regional variations in the drivers in terms of, you know, there are going to be regional differences in how much was preconditioned by the ocean and how much was affected by the atmospheric circulation of the winter. But I think when we see these predictability runs, that's kind of consistent with when we see the actual anomalies. So that's it, and thanks for listening. And Zach's leading the write-up, and hopefully we'll be submitting this in a few weeks. But any comments, suggestions, criticisms, very much welcome. Thanks.
We have a couple of minutes for questions, but Clara had one early on. So Clara, do you want to unmute and ask that one?
Sure. Can you hear me?
Yeah.
Hi, thanks, Ed. We're really super interesting. Just a quick question. I noticed at the beginning, your nudged run at the very beginning, 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 beginning.
So something happened there. Anyway, apparently it was at the beginning.
Beginning, 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 beginning.
I don't think that's Clara rapping.
Beginning, 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 beginning.
Hey, Clara, you might try leaving the meeting and coming back in.
All right. Well, so she was asking about the SLP wind anomaly plot that you showed early on.
Yeah.
Nudge experiment.
Beginning, 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 beginning.
That too, we don't fully understand why, and I can go back to that plot. So this is the difference between the bottom panels. Why are these sea level pressure anomalies?
Yeah.
It seems like everything's offset to the positive, right? We don't fully, we haven't really investigated that. It seems like almost there's a bit more atmospheric mass, right, all over the like Southern Ocean and Antarctica. But in terms of sea level pressure gradients, they look pretty good. I think that's the main thing, right? And especially if you compare, it's a little hard on these figures, but if you compare the wind vectors, I mean, the whole point of this design is that to replicate the winds in the observations in the model. And I didn't mention that we're nudging the winds above the boundary layer. And these are the winds and sea level pressure anomalies at the surface, right? So we let the boundary layer be fully coupled. We let the surface be fully coupled. That's partly because of historical reasons and maybe slightly philosophical reasons that we think, you know, we don't want to completely run this like an ice ocean model and bake in the answer too much. But, you know, if you nudge the circulation above the boundary layer, you know, through that momentum transfer and conservation of mass and energy, you're going to get a pretty good circulation on bottom. But yeah, we don't fully understand why there seems to be a bit more mass or atmospheric mass or pressure. But it might be something else. I don't know. There's always a little bit of like dirty laundry, I think, with modern experiments and the nudging runs that we get these little features that may be unexpected, but I don't know. I think we're still getting useful results.
Do we have a quick question in the room, maybe? Okay, Alex?
Yeah, really interesting. Did you look at all into the future? Because that's the second big question, right?
Yeah.
Like if you
Yes.
continue running that in another
Right.
year, does it?
We do want to do a 2024 forecast, right? And it's a little bit, when you look at this time series, are we going to bounce back to what it was like before? Or is everything going to be from 2023 onwards? So we tried last week to look at the SST anomalies in 2023, in December 2023, and compare them to December 2022. ERA 5 still doesn't have them, at least Copernicus just gave me a bunch of nans, which is kind of frustrating because on the climate reanalyzer, you can see the anomalies, but they look very similar. So the ocean still looks very warm. And so I expect that winter 2024, I don't know if it's going to be as low as 2023. I don't know if you'll have that Amundsen low anomaly to give us that extra punch, but it's likely. I'd guess that we might still be, maybe where 2022 was, which was already pretty low. I'd be surprised if we say go back to zero our climatology. Like I think the ocean looks pretty warm, and I know El Nino didn't contribute very much, but we're still in an El Nino. So if I had to bet over, positive or negative number, I think definitely negative. Maybe not as low as 2023, but yeah. But we do want to run a forecast, repeat that kind of forecast exercise with past years when we do that.
All right, thanks, Ed. So our next speaker is David Schneider. So we're gonna see he can present. I think we need to stop presenting from this one.
Yeah.
Oh, it doesn't matter. I can watch this. I can watch this one anyway. So.
Oh, you could, Alex. I think
Yeah,
he's
you
gonna
can.
sit there.
Alice, you can
Yeah,
stay there.
okay.
So looks good. So we're trying to keep about 15 minutes for the presentation, 5 minutes for questions, somewhere in that ballpark. So. Yeah, definitely.
That work?
Yep.
All right. Good morning, everyone. It's good to see you all in person and online. So I'm the Dave who's going to talk about surface mass balance. So instead of a forecast into the future, we're actually going to go back in time through the 20th century and move from the sea ice up onto the Antarctic ice sheet. This is a grant-funded project. Most of the work's been done down at CU Boulder with a great team of people. Today, I really want to acknowledge Ziki Yin, who is a grad student in ATOC, and he stepped up in the last month or so and really helped me crank through a lot of data analysis and making figures and coding. So without Ziki's help, I wouldn't have a lot to talk about today. So I'm really grateful for that. The main question this project has been motivated by is this one, is how much sea level mitigation from increasing snowfall could we get in a warming climate? So this question has been around the climate and the glaciology community for a long time. And the basic idea is that as the atmosphere warms, it can suck up more moisture out of the ocean. The atmospheric circulation will carry that to the ice sheet and dump it as snow there. So if that snow piles up over time, it can lead, at least temporarily, to a sea level offset. But there's other things that happen as the climate warms. There's more evaporation, sublimation of the snowpack, melting and runoff. So whenever we're talking about snowfall on Antarctica, we want to put it in the context of all these other things that are happening. So we're actually, the quantity that we're looking at here is called the surface mass balance. So this includes all these terms. What it does not include is the basal melting at the margins of the ice sheet. It doesn't include iceberg calving. So we're just looking at the surface mass balance, not the total ice sheet mass balance. So if you want to know the total contribution of the ice sheet to sea level, you have to consider the total mass balance and maybe go to Land Ice Working Group tomorrow and you can learn about that. So for a long time, we didn't think there actually was evidence for increasing snow on Antarctica. And really this was the first kind of synthesis paper that came out about 4 years ago now, where they compiled all the ice core data and related it to P minus E in the reanalysis and gridded everything and produced this 200-year-long reconstruction, 1801 to the year 2000. And their key result was in this black line here, finding that the cumulative mass had increased over the 20th century, and that offset sea level by about 10 or 11 millimeters, with a couple of millimeters of uncertainty. And they found that since most of Antarctica is in East Antarctica, most of it came from the East Antarctica sheet, but in the last 20 years of the 20th century, the surface mass balance on the peninsula really kind of kicked up and started increasing rapidly. So this overall rate increases in the late 20th century. And those are the ice core locations that they use. So what we did, I think still not everyone quite believes that study or that result. So we wanted to compare it to CSM2 and kind of see what CSM2 has to say about this. So we computed surface mass balance across nearly 25,000 years of model experiments. And so our group of experiments, we've actually looked at more than what's what I'm presenting here. So of course we looked at the large ensemble, which is the all ensemble. We looked at the tropical Pacific pacemaker, where anomalies in the Eastern tropical Pacific are nudged to observations. And then we have this group of single forcing ensembles, greenhouse gases, aerosols, biomass burning, and everything else, which includes the ozone depletion and natural forcings like volcanic and solar forcing. And then we have the PI control run. And so for the PI control, we looked at the segment of the PI control that basically overlaps with the start years of all these above ensembles. And then we have a number of observational data sets, of course, the Medley and Thomas data that I mentioned. And then we have this kind of cool suite of reconstructions using proxy data assimilation from Gemma O'Connor at UW. So she published a set of these reconstructions using CSM1, and she's done a new set with CSM2. So you can kind of look at structural uncertainty across these reconstructions, which is pretty cool. So here's the main results. So that Medley and Thomas data set is in the black line here. So we kind of repeated their calculation and got basically the same number that they did at the year 2000. And then we have all these CSM2 ensembles. And so the ensembles are kind of bracketed by the greenhouse gas only, which is the highest surface mass balance, and then the aerosols, which is the lowest surface mass balance. Then everything else falls in between. So the large ensemble still falls above the observation. And then there's kind of a pseudo ensemble here in the blue, which is just the sum of the greenhouse gas and the aerosol ensemble. And then there's the tropical pacemaker experiment in red. And so those two ensembles kind of I'm pretty close to the observations, and we'll kind of look a little bit at whether they get there for the right reasons or not. And then over here we have this box and whisker plot kind of summarizing the ensemble spread. So these overlapping segments of the control don't really produce a significant increase. The large ensemble, of course, does with a pretty large ensemble spread. But you see the lowest values of large ensemble kind of match the observations. Then T-pace kind of falls pretty squarely within the observational uncertainty. Greenhouse gas, of course, above, aerosols below. So if you sum greenhouse gas and aerosols, you get something that's pretty close to observed. And then this bottom panel is just, for clarity, just plotted these other experiments on a different panel. So what's going on here, biomass burning, this line here doesn't do much. This is a subset of the large ensemble, which has the same initial conditions as the pacemaker ensemble. So from that, we can subtract this from the pacemaker to see the effect of that tropical nudging. So this negative value here is the impact of the tropical nudging. So that's a reduction in surface mass balance. So it's kind of, there's more sea level rise because of the tropical nudging. So to summarize that, things that make surface mass balance increase over the 20th century are greenhouse gases, and then everything else. And they're kind of, everything else is kind of in a distant second place. Things that make it decrease are the entropy of aerosols and nudging to the observed tropical Pacific SSTs. And things that make it stay the same over this long, century-long period are internal variability and biomass burning. So how does that work? So here in the dark blue, I'm plotting again the Medley and Thomas cumulative mass balance, and then that's contrasted with the relative mass balance in the cyan. That's basically the annual accumulation rate. And so you see it goes up, of course, but it kind of stair steps up. So it's got these periods of time where it plateaus or kind of even goes down a little bit. And so those are periods of time when the relative mass balance is negative. This is relative to the 19th century mean. So it's not climbing up all the time, but it's generally climbing up with the global temperature record, which is the dark blue on the bottom panel. And then cold periods in the global temperatures tend to be when you have these kind of plateaus in the cumulative mass balance. And then we also see how these different CSM ensembles do with the global temperature record. Basically, they're telling you that this general structure of the early 20th century warming, mid-century cooling, late century warming, basically explained by greenhouse gases and aerosols. But then there's other things happening. So in the large ensemble, you have other forcings included, such as volcanic eruptions and solar variability. So those are pretty important for capturing some of this variance in the global temperature record. And then finally, if you want to capture like most variance, you can include the observed ENSO variability. So that's what's going on in the pacemaker experiment, because it's nudged to the, basically nudged to the SST anomalies in the tropics. So overall, the pacemaker does the best at getting the global temperature record. So we can do simple regressions to look at the sensitivity of the mass of the surface mass balance temperature. So in this one, we do cumulative mass versus global temperature. And with the observations, we find really high R-squared values above 0.8. And then within the model, the correlations are slightly lower, but still very significant. And then that relative mass, if you go through these different correlations, it works best if you correlate it to the local or regional Antarctic temperature. And so in the blue dots is the observations, and then in the red is the pacemaker. And then in the cyan is kind of the observations rescaled, considering their uncertainty. So there's a suggestion here that maybe the model's over predicting the sensitivity. It's getting around 9% of increase in surface mass balance per degree of warming, whereas the observations are suggesting it's 5%. But there's a lot of wiggle room in these comparisons if you consider the different uncertainties. But there's a suggestion, and if you saw the cumulative mass, you know, that the large ensemble tends to overestimate the cumulative mass. So there's a suggestion that maybe CSM2 is a little too sensitive. So the relative mass is best explained by the Antarctic temperature anomalies, and the cumulative mass is best explained by global temperature. So the final part, I want to look at spatial patterns and consider the relative roles of internal variability and external forcing. So those are good questions for the large ensemble. And so in these postage stamps map, we have the observations here. I think it's the fourth panel on the top. The ensemble means. And then what we looked at here to the large ensemble was the spatial pattern correlation. So The observations have a certain spatial pattern, and then you can look through the large ensemble and try to find if there's a good fit within these ensemble members to the observed spatial pattern of the surface mass balance. So the best one we found was this one, happens to be number 49. So we're going to use that to do a little more analysis. So here's our observed trend. So I'm showing the Medley and Thomas reconstruction along with the circulation pattern that's reconstructed by Gemma O'Connor with the proxy data assimilation. So we take that best fitting ensemble member. This is how it looks. So the main feature that helps it get the best pattern correlation is this dipole in West Antarctica. We're in the peninsula region, increasing surface mass balance, and then the Ross Sea region, decreasing surface mass balance. Then across East Antarctica, there's kind of this gradient where there's this fairly large increase on the coast of Droning Mondland, and then as you go across the ice sheet, the trend kind of drops off. And so the force response here is simply the ensemble mean of the large ensemble. So that's giving us this pretty big increase in the surface mass balance, giving us a strengthening of the westerlies in the force response. And then we have the internal part, which is simply this ensemble member minus the force response. So that's our internal part where we get this more wave leg pattern. And so this internal part really seems to explain this dipole. Although you see it very slightly in the force response, you see it really strongly in the internal part. And so that looks a little something like an El Nino or La Nina teleconnection. So let's put that in global context. So the bunch of this is the whole 20th century. So there's a bunch of observational data sets up top. And we're looking at their SST trends. So there's a lot going on here. The few quick things I want to point out is that everyone knows kind of about the North Atlantic warming hole, but there's also this area of relative a minimum in warming in the South Central Pacific Ocean that shows up in these observational data sets, and it shows up in this proxy data assimilation reconstruction. And it seems to be associated with this strengthening of the westerlies, but they're not just westerly. There's this northerly component to the reconstruction here, where the winds would be drawing cold air out of the polar region to this mid-latitude region. And so here's number 49, which is our best fitting ensemble member. Here's that internal part. So this internal part indeed does look a little bit like La Nina, and you see this wave pattern across the Southern Ocean. But in the pacemaker, you actually see what the pacemaker is doing is opposite almost in the Southern Ocean to what this internal part says should be happening. So it's this internal part that best fits the observations. It's not actually the pacemaker. So the pacemaker does have a relative cooling in the Southern Ocean. That's why its ensemble has less cumulative mass balance, but it doesn't seem to have the right spatial pattern. So finally, I'm just gonna step it forward into the 21st century, and you can kind of watch your favorite map while I do this. So this is 2001 to 14 minus 87 to 2000. And so you see what happened is the internal variability kind of developed this La Nina, and its patterns of sea level pressure and SST in the Southern Ocean fit the observations really well, whereas the pacemaker just does not. So that's interesting. So to summarize, greenhouse gases and aerosols we found were the dominant drivers of the 20th century cumulative mass gain. CSM2 generally agrees well with the observed sea level offset of around 11 millimeters. it tends to overestimate a little, but there's a lot of uncertainty in the observations, and there's large ensemble spreads. So I think we can say they agree pretty well. For the spatial patterns, epicenter circulation is important. Both the forced and internal components are doing a lot of work to give us the observed pattern. And finally, a wild card, T-PACE has the opposite trend patterns to observed. And it kind of, the best fitting ensemble members seems to kind of evolve into this La Nina type thing. So what I didn't get to today, but hope to answer before I submit the paper is what kind of drives this big ensemble spread that we're seeing. Is it global temperature again, or is it circulation or something else? So I think I'll wrap it up there.
Well, thanks, David. Do you want to quit sharing there, and we'll switch over to Alec? Is there a quick question for David? And
Dave, you mentioned when you showed the Medley and Thompson results that no one really believes them, something like that. Why is that?
Yeah, so forever, like people were looking at like reanalysis based surface mass balance trends, or reanalysis prescribed to a regional climate model. And so for the 79 to present era, there wasn't really a trend. And there had been a previous kind of ice core synthesis done, which was fewer ice cores that didn't show a trend either. And so that was, Medley and Thomas was really the first one.
Right.
They covered 200 years. They gathered all the ice cores they could find. And they did find a significant trend. But still in
So it's more maybe because it was a different result to what was published rather than anything with the methodology.
Yeah, I mean, there's definitely uncertainty in the reconstruction, but I think they explored it pretty thoroughly.
And it's pretty encouraging that the CSM2 shows
Yeah.
very good,
Yeah.
consistent, right?
Yeah, at least consistent. But
great, thanks. So Alec, do you want to unmute yourself and go ahead?
Sure. Can you guys hear me okay?
Yes.
Great. And you can see the screen okay?
Yeah, looks good.
Cool. Well, yeah, hi everyone. My name's Alec Petty. I'm a polar climate scientist at the University of Maryland. I see a few familiar faces in the room. Great to see you all. And yeah, thanks a lot for letting me give this talk remotely. I really appreciate it. Young children still make it a little hard to travel. Yeah, my goal today is to give you guys a bit of an overview of this relatively new project we had funded through the Studies with ISAT-2 solicitation. Yeah, it's a project undertaken with Chris Cardinale, a postdoc also at the University of Maryland. He's really been the driving force behind a lot of the analysis I'll be showing today, producing some really nice plots too. And also Maddie Smith, who I think is online too, who I know many of you are familiar with. She's based at Hui. Let me just, there we go. Yeah, just to start with a bit of motivation, I think a lot of you will be familiar with plots like this. These are projections of September Arctic sea ice on the left and September Antarctic sea ice on the right from the CMIP6 archive. So we have the historical runs, then the different scenario runs in the different colors. I think these plots are nice because they show up the different sources of uncertainty in projections of future sea ice and also historical sea ice. So we have that kind of scenario uncertainty based on the differences in the different colors. We also have internal variability within the models, and then we also have kind of an intermodel spread or uncertainty as well, which we can see represented by the shading in these plots. So for us, that's kind of the source of uncertainty that we're most interested in trying to kind of help the community better constrain or calibrate or correct for. In terms of metrics we're interested in, obviously we were pretty interested in things like timing of an ice-free Arctic. I see there's some talks after me today that are going to be addressing that topic too. That's a pretty big one for our field. And kind of following what Ed talked about, there's been some interesting things going on down south. So the kind of potential timing of an Antarctic ice-free is another question that we're somewhat motivated by. But also trying to think just generally about how we can use the CMIP6 archive to better predict sea ice in the future from not just decades ahead, but also years ahead too. And, our focus is a little bit more on the kind of tools that we can bring in to help us do this kind of constraint or calibration. We're inspired by a lot of recent work that's been done in this area. Yeah, the two top papers I list here are kind of what I consider real baseline studies using the CMIP6 archive to look at Arctic sea ice and Antarctic sea ice projections. So the SIMIP community paper in 2020, which informed the latest IPCC sea ice chapter analysis. That was obviously a kind of a first look at Arctic sea ice in CMIP6. And then there was a similar effort by Letty Roach doing the same thing for Antarctic sea ice. I think one of the keys from the SIMIP paper was there was a little bit of work on trying to kind of assess plausible ranges within those CMIP6 models and using the passive microwave sea ice area record to do that work. Another takeaway from that paper was there was this kind of slight mistrust of the available sea ice thickness data sets to do a similar calibration in terms of thickness. Letty's paper was a little bit more involved, a little bit more focused on comparing CMIP6 to previous CMIP outcomes. And then since then, there's been some really cool work trying to come up with different ways of constraining mostly future Arctic sea ice. So Dave Bonin and others came up with this kind of approach of linking Arctic sea ice area to temperature variability to then essentially kind of bias correct or recalibrate the CMIP6 models to improve projections of an ice-free Arctic. And then last year there was a couple of papers in Nature Climate Change doing similar things but focused on different metrics. So one was looking at kind of a link between sea ice area variability and greenhouse gas forcing across the CMIP6 models. Again, a kind of a fancy recalibration approach, if you will. And then another study which focused more on representations of atmospheric circulation differences across the CMIP6 models and using that to kind of recalibrate projections. Then finally, we're pretty inspired by this paper by Francois Mazenet. I think Ed and others were involved in that too. That was really a nice study showing this nice relationship between sea ice thermodynamics across the CMIP6 models and how that relates very closely with the representation of mean Arctic sea ice volume. But a little bit similar to the SIMIP paper, they found that the observations of sea ice thickness and volume were a little too uncertain to actually reliably constrain or exclude some of the models, which was maybe a bit of a shame. And yeah, many other papers which maybe are going to be mentioned in the following talks. So, oops, oh, there we go, skipped a slide. So yeah, this kind of issue of thickness uncertainties keeps cropping up in these papers, and so I wanted to address that. I've got a bit of a background in sea ice remote since I was the Operation Icebridge Project Science Office, analyzing sea ice data from that mission, and then ISAT-2 after that. So I know I've given talks to this group before on kind of how we produce sea ice thickness measurements. Considering the pretty short time of this talk, I'm not going to go into detail on that. But I think the key kind of takeaway from how we measure sea ice thickness with satellite altimeters is that we don't measure sea ice thickness, we measure freeboard. So we measure freeboard, in my view, pretty precisely, especially with the laser altimeters from ISAT and ISAT-2. The lasers give us a measurement of total freeboard, the extension of the ice and snow layer above a local sea surface, and then radar altimeters like ESA's Cryosat-2, they give us a measurement of ice freeboard, just the extension of that ice-snow interface above sea level. As I said, I think those measurements are pretty great. Where we start introducing a lot of the uncertainty is when we try and use the freeboard measurements to estimate sea ice thickness. To do that, we typically assume that ice is freely floating and use the hydrostatic equilibrium equation together with additional input assumptions regarding the snow depth, the snow density, and also the ice density to then back out ice thickness. All of those input assumptions add to our uncertainty. I generally consider snow depth to be the biggest source of uncertainty, but there's no clear consensus on that, and it depends a little bit on if you're doing laser or radar altimetry and what input data sets you're using. Ice density has been a bit of a recent focus for the remote sensing community. It's hard to even constrain how big of a contribution that makes due to the limited data we have. There's other issues when we do this, like how we actually go from a gridded data set to a kind of basin scale mean. And then things are even more complicated for Antarctic sea ice, where we have less validation data and generally consider the snow loading especially to be more complicated than the Arctic. So lots of issues which we're kind of trying to tackle in the remote sensing community. But while we do that, our view in our project is to kind of maybe take a step back and use the direct observations of Freeboard instead, and see how well they can be used to help us kind of constrain or calibrate data from the CMIP6 models. So Freeboard measurements, as I said, are pretty great. In some cases, they're more accurate with a nice concentration. These laser altimeters are very sophisticated platforms for measuring Freeboard. We also have a growing record from the satellite altimetry missions we've had. So that was always in the past a bit of a limitation of thickness and altimetry. Was we only had a few years of data, but now we've got nearly 20 years of data from ISAT through to Cryosat-2 through to ISAT-2, which is still ongoing. So it's catching up with the multi-decadal record from passive microwave. So considering that, we can start to do things like constrain fairly reliably, in my view, the mean state, the seasonal cycle, and maybe even some trends. The nice thing about Freeboard is it does give us some information within the pack ice. So, if you look north of the Arctic archipelago and Greenland, we see some information about kind of Freeboard variability that we won't obtain from the passive microwave data. However, yeah, it is a less physical quantity, nice thickness. We have to do a bit of work to try and disentangle how much changes in Freeboard come from ice versus snow. And then when we try and convert from Freeboard to thickness, we need to make some assumptions regarding density. But the key is we have these observations, and also increasingly models, especially in CMIP6, are actually providing an estimate of Freeboard that we can use to compare the observations to the models with. So yeah, just shown on the bottom there are some examples of CSM2 outputs of total Freeboard, where we've added the ice Freeboard and the snow depths together. So yeah, that's a long introduction, but as I said, it's a pretty new project, so that's why. These are our kind of main objectives so far. So this first one is really just trying to characterize, which hasn't really been done much yet, the modern era basin scale sea ice Freeboard in the models and in observations, and then bring that together with some of these kind of newer calibration methods and see how much we can improve future projections of sea ice. Yeah, the following slides are just some of our project outcomes thus far. Yeah, and a quick note before I show those, we've been doing all of this analysis in this pretty cool cloud-based platform. Chris has been the one kind of spearheading all of this work. So NASA are helping fund this CryoCloud Jupyter Analysis Hub, which is really nice for kind of working collaboratively on the cloud. And the nice thing is a lot of the CMIP6 data is also on the cloud. So there's been a lot of work that's been done over recent years to make sure virtually all of the data from the CMIP6 archive is up on the cloud. Initially, it was with AWS and Google Cloud, but there seems to be a bit of an increasing focus on the Google Cloud storage. There are some slight differences in the availability of model output between the cloud and what was initially used in those papers, which we have looked at, but I'm not going to dig into today. And then the other cool thing is you can actually request and add more data to the cloud feedstock if there are things missing, which we have done to make sure the Freeboard outputs and also the ice thickness distribution are up there too, to simplify our analysis. So as I said, models are starting to produce Freeboard. Our initial goal was to figure out how many models actually do that. This is summarized in the table here on the right. So this was our kind of, or Chris's best guess at the availability of model data with some of these core metrics that we're interested in. As you know, 30 odd models are providing the kind of core sea ice state information regarding concentration and thickness. And then our guess is there's something like 13 models currently providing Freeboard output. It's the ice Freeboard, not the total Freeboard. So a reasonable number for us to do some science with, we think. There's obviously a bit of a difference then between how many SIM6 models there are and how many actually provide the freeboard. One of the other things we're kind of playing with right now is to see how we can derive freeboard from the observations that those other models provide. Sorry, the outputs of those other models provide. So to do that, we need to make some assumptions regarding the ice and snow density, and that's what I'll show in some later slides. Yeah, at the bottom left there's just the equation for calculating both the ice freeboard and then the total freeboard where we add the snow depth to it. So yeah, our initial work has just been trying to look at the seasonal cycles of freeboard across both the Arctic and Southern Oceans from that model subset that's currently providing the freeboard information. Luckily for this meeting, CSM2 is one of those groups. So good work, guys. So what these plots are showing is, yeah, the multi-model mean in red and the standard deviation and total range in the light shading. The CSM2 results are shown in blue. And then I'm highlighting this Access CM2 model, which is producing some slightly interesting results, which I'll dig into in the following slides. Shown in black is the observation. So these are the observations from ISAT-2. This is the gridded freeboard product ATL20. And yeah, for this analysis, we're just focusing on a pretty small period, 2018 to 2023, but we get similar seasonal cycles when we expand that period for the model results. So yeah, you can already see some interesting kind of differences between hemispheres. I'll dig into the differences between the freeboard and thickness seasonal cycles in a couple of slides' time. One of the things we initially noticed with this work was, yeah, we saw some of these models, well, this one model producing really, really low freeboards in summer, which was interesting. When we did a similar plot for thickness, we didn't see this. So one of the ways we can kind of diagnose what's going on here is to look at the ice density. As I said, you know, to calculate freeboard, we need to know the snow and the ice density. Ice density is one of the important parts here. Unfortunately, none of the models that provide freeboard, well, none of the CMIP6 models actually output and provide the bulk ice density. So we have to kind of back it out ourselves from the provided data. So that's what we did next. So we did kind of similar plots, but now looking at deriving ice density from the provided data of ice freeboard and snow depth. We do have to make an assumption regarding the snow density, which we set to 330, which seems like a lot of the models use that as a fixed value. And then we produced interesting plots like this. So yeah, we saw this kind of pretty big range in potentially derived ice density. And this, again, this Access CM2 model was potentially skewed quite high compared to the other runs. The black dashed line is showing the ice density that we tend to use in our remote sensing work, which is basically the density of pure ice, 916 or 917 kilograms per meter cubed. Obviously, we generally expect sea ice to have a different density to pure ice. It's a pretty different medium. But we generally think there's kind of competing influences from brine content within sea ice, which increases density, but then also the presence of air pockets, which can lower density. So in reality, we think there's this kind of difference based on how old the ice is. Old ice maybe has had more time for that brine to flush through. Younger ice might have higher brine content and higher densities. So it's hard to constrain those. So in remote sensing, we tend to just keep it fixed. Some people do a kind of ice type weighting. Some of the models just prescribe ice density at a similar value. So we saw some of the models using a similar constant value. CSM2 is one of the models that has a prognostic density. So CSM2 uses this mushy layer thermodynamic scheme where the bulk ice density is a function of the local temperature and salinity. So that's cool. And yeah, we think this is one of the first kind of looks at what that actually looks like, the seasonal cycles for both hemispheres. It seems kind of to produce plausible densities, increasing in summer and decreasing in winter, as we'd kind of expect from theory. We can plot that in a slightly different way. So this is showing kind of the same information, but now we can kind of see how each model is performing in terms of its derived density. Again, this has just helped us kind of maybe isolate this model as one that's producing implausible results, but all the others seem, as I said, plausible based on theory. Here, the horizontal lines are just showing the seasonal range of ice density across both hemispheres. So yeah, we could kind of redo the analysis now and get rid of that model, the Axis one that we think is producing weird results. And now things are looking quite nice. Next, what we wanted to do is kind of play around with some of those density assumptions. So as I said, one of the problems that we have is not all of the models produce freeboard. So if you want to try and estimate freeboard from the models that don't output that, we have to make a decision of what we prescribe the density to be. So to explore that impact, we did some experiments with prescribing ice density and then calculating freeboard ourselves from the other quantities. So here we're doing that with the CSM2 model. We've got the CSM2 on the left and CSM2 WACM on the right, the Arctic at the top and the Southern Ocean on the bottom. So the solid line is the output of freeboard from those models. And then the dashed line is where we calculate freeboard using a fixed ice density of 916. So we see that has small but not insignificant impacts on the estimates of freeboard. Differences of maybe 2 or 3 centimeters, and obviously bigger differences in summer when that prognostic density is doing more interesting things. So
Al, you've got about 2 minutes.
Okay, sorry. Oh yeah, I just saw that warning. Sorry, nearly done. So yeah, we can now produce similar bar plot like this, but now we have the different lines signify where we use the output of freeboard and the other one where we kind of fix the density and calculate freeboard ourselves. So again, small but not insignificant differences. Finally, yeah, just to kind of give you an idea of how the freeboard seasonal cycle compares to thickness. So we've got freeboard on the left, thickness on the right, just for the Arctic Ocean. Again, the nice thing, I haven't really dug into the observations here, but the nice thing about freeboard is we're a bit more confident on those observations during summer. So we have this complete seasonal cycle. The thickness, we're a bit less certain about what happens in summer. We have some preliminary data, but I didn't want to show it today. We do see some differences in the seasonal cycles, like we see this kind of earlier decline in freeboard, which we think is maybe snow melt, and we see, the observations and the models seem to be picking this up, which is encouraging. Gives us kind of a flavor of the type of diagnostics we could do. Yeah, and that's kind of it. So the conclusions so far, this is still very much active research. We're still in year 1, but we're already getting some nice results, I think. I think we're excited by this idea of trying to use freeboard to better compare models with the direct observations. These comparisons increase the need for us to consider and assess the underlying ice density assumptions used in the models. We don't really care so much about that when we just look at thickness. And we're really excited to use freeboard to do some Antarctic sea ice comparisons where thickness data is much more lacking. I'll leave you with my next step slides and happy to take any questions.
Any questions for Alec? Ed has one.
Hi, Alec, nice presentation. In your last slide, like regarding the seasonal cycle in freeboard, I was curious that in the observations it doubles kind of between August and October, whereas in the models it goes down. Like that seems like when you have a bit of a difference in that seasonality between the observations and the models, and I'm wondering if you've thought about that, or is it just simply the domain over which you're averaging these numbers, that whether you're including a lot of the new thin ice in the fall or not? Anyhow, I'm just wondering what you think about.
Yeah, that period's always kind of annoying with the observations, as you say. There's a lot of low concentration thin ice, and that's where there can be big issues with kind of sampling errors. So yeah, I imagine there might be something like that going on, and yeah, that's definitely on our to-do list next, is to kind of try and think about how to better compare when we have slightly different filters and thresholds.
Thanks. Great. Marika, you have a quick question?
I just had a quick comment. So later we're going to discuss a little bit diagnostic needs for the model. And I think it would be great to think about how we better incorporate freeboard in our standard diagnostics as well. So thanks, Alec. I think this was really interesting.
Cool. Yeah.
Great, thanks. Well, I think it's going to cut into your break time. So I'm going to cut it off there. Anyway, so we should be back here in about 15 minutes at 10:20. So thanks So. So there's got a couple options. You can sign in to the meeting by the Google Meet, but make sure you use companion mode, preferably.
There's a place in the code
So
where it's like the ice.
that assumes you have wireless, of course. right?
Yeah. On Wi-Fi.
And,
So I'm not sure exactly.
I feel like
there might be.
Yeah.
Or some.
And like kind of long.
That's just.
We just like I love it.
I know. And then I guess it's, you can redo that. You have like, that's the.
That's true. The third is fucked up.
A lot of
That sounds like.
Abby goes outraged about
I'm not sure how
Junior.
Yeah.
You heard like,
But yeah, Ash.
Well,
there's special names that people have.
yeah,
for-
but we do.
I was like, oh, it's 65. Just
Yeah, well, that's meant to be for silly. His sick child.
I presume the density he's
And
then putting in there is the like
Only depending.
total mass,
Yeah.
the column, excluding the snow, just divided by a thickness. As opposed to like
Very strange. Just like.
This is on Tuesday. But I don't, I mean, if it's actually the summer, I think that's wrong. Because in the summer is when you actually get.
All right, and then
the
you
green layer
probably
at the
do the
top, and so
share
it would
from
seem like.
here.
Well, you should, yeah. Yeah.
Where it's just like,
Um,
able to get like that deep.
Yeah. Like get it a little slow, you're just like, okay, I'm gonna go.
Yeah, exactly.
Along with these people that get there.
Oh,
That's how it is.
okay, so
That
that's
makes
the
sense.
browser, you need to. I'd have to restart the browser.
Okay, can I just send it to you?
sharing the.
What's that?
You said there were other options.
I always get worried about that where I'm like,
Yeah.
do I?
Well, your other
I
option.
can't actually.
My default is usually, what am I missing about it? When you did something wrong.
Do it, we also have a loaner laptop, so you can put it there.
Yeah, 'cause I've never got Google.
Apparently you
Yeah,
don't
give
have
me the,
access to.
6 times already? I don't know.
Okay.
And I've tried going
Well,
on
maybe
the, yeah.
That's nature behind the role.
Anyway,
Okay,
Yeah.
You're part of-
okay, right.
sometimes.
I'm part of
you.
Yeah. anyway,
I'm at NTAR.
I'll try the.
You're at-
So
Google
usually we
Chrome.
have access, but for some reason, like on
Yeah,
on the
And
VPN, it's
Google
not
Chrome
giving me.
generally works.
Do you know the
but-
NCAR library?
So-
Yep, oh, maybe that'll.
So if you just send it to me,
Yeah, I'll
that's
just
fine.
do that as a backup and then I'll.
Okay, and then I think Chris is.
And we
Chris was looking
did,
ready to go.
this will work? Similar construct.
And Ian, you're online,
Do not
right?
have it. Oh, yep, never mind, sorry,
You
okay.
got it? You
Yeah,
got
I
it through
could,
proxy?
got it through proxy, yeah.
Dave,
Yeah,
I went through companion mode. Can I just test that I'm
yeah.
presentation work?
Yeah. Knock yourself out.
In the room. Always in a row. Yeah.
Okay. Have it
Looks good.
switched.
Pfizer's not.
Okay, there we go.
Yeah, yeah,
All right,
Talk to
thank
the
you.
next session.
in the afternoon, not next session. Yeah, it was interesting work. I was surprised there's so, I mean, just last month when I thought, it seemed like there were so few measurements from East Antarctica.
Out of the Google Meet.
Okay, yeah.
Which I was kind of surprised by, honestly, because I would have
Yeah,
thought the ice
you need to go and
cache
scan. your
could have been
Ah,
used to
right.
provide
Sorry.
a lot of East Antarctic measurements.
Some of them, well, ITIS was a bunch of different traverses.
Yeah.
I know they had,
But it seems like,
I know
they
the
should-
Americans had one in East Antarctica.
Laura.
yeah,
And that map, I don't know, it didn't make it look like.
the map
Let's take a look
made
at
it seem like there weren't that
this.
many points, and I was wondering if they're.
Whether or not,
And the thing that's, I was wondering is, are they just using ice cores
Yeah, you would
Because-
think there'd be, like, there was a
Oh,
test
okay.
reverse across here.
And there's one going out,
And there was maybe-
that way across the Mega Dunes side, and there's one like out that.
They could be, they were either,
So what
Not
browser
logging.
are you using?
Now I was.
you might have had
listening.
Katrina about being,
Okay, weird.
you know,
I'm sorry.
200 years at least,
Well,
or being,
Um,
annual.
all right, well, just,
There might have been some problem.
I was wondering
Okay.
I was wondering if it's also just a bias in that, right, in East Antarctica, probably get 200 years in a snow pit. Like, I don't know that you have to core, or at least you can get back a decent ways, maybe not fully 200, but like,
Mhm.
I mean, some parts of East Antarctica, the accumulation's so low, you ought to be able to,
Yeah, maybe it's not time, maybe it's
maybe they had like, it
either
has to
data
go down a certain
resolution,
depth, or-
maybe they weren't annually resolved,
yeah.
or they didn't have the data. I don't know.
I don't know. It's just interesting because, right, like, you know, the data, the results are very heavily weighted by what's happening in West Antarctica in terms of matching the observations.
Yeah, though I think they do have enough to resolve, like, there's more accumulation in Drowning Wildland than there is over here in Oaksland.
Yeah.
In the middle,
How are you doing?
the hardest.
Look at that, looking promising.
There's definitely.
Professor, you're like, I get to
Hey,
go
Dave, can you hear me?
and go skiing. It's like a vacation week.
From the-
What a treat.
What
Yeah.
a treat.
A lot of the, like,
Yeah, then there's the.
model when you do the.
Yeah, as well. So a couple of
Also
them
at
really
Snow Mountain
sensitive.
Ranch.
Yeah.
Yeah.
getting them
Yeah.
peppered.
Inflation, like,
Yeah.
this area around the
Yeah,
beach,
I
like,
think Laura Landrum.
really, there's only a couple of cores that could be called.
Oh, did she?
And so that's where, like,
Through Friday night.
you know, the model,
Oh, very nice.
The
the rate should be increasing.
I'll be
really, like,
back Sunday because I want to go
That
see the
makes a big
women's
difference.
basketball. I'm like, really?
I've been really enjoying watching them as well.
No, I'm sure, but like coming from Stanford
I know,
too, like
but-
it's a total rivalry.
Yeah.
We went to Stanford
Yeah.
and we were wearing all the Stanford kit and like hats, shirts, the whole thing.
I know.
And then like they started losing and my wife is a fair weather fan.
And bought a huge t-shirt, put it over
She took her hat off first and she zipped up the coat. And then by the end, she was like, I need to go and buy a shirt. It was
That
really good.
game was
This goes.
awesome though. Oh my God,
Well,
like,
the USC game.
that was a good one too, but oh my God, the halftime, like that Kendall Wetta, she is like my favorite. And she like just
See, I'll be here.
launched that 3-pointer
That was
that went
so
in and
nice.
like everyone went crazy.
Devastating. Brutal. Yeah, we had that one game, Rudy for Stanford, and then we just
I think
switched
you
over
were-
fully.
You were able to
Um,
share.
But Stanford is also like
you
Still,
grade
still
it?
really well.
Which is amazing because they, I don't know,
But during-
they've been very good for a number of years. And then last year they left early. I think they got chucked out before the Sweet 16 level, which for them is
Oh.
insanely
Yeah.
early. And they had 4 people who I think felt like they were not being played enough transfer out.
Oh wow.
Did you go to the UCLA game?
Yes.
So they have a really tall girl, Lauren Betts. She's like 6'7". She played for Stanford in her freshman year and then was one of the ones who transferred out. And like,
Or 5 minutes.
so they now are really down to like 2 decent players. But they're making it work, but it's like
Right.
there's really only 2 really good players, you know? So
Right. Yeah, if you could shut those 2 down. One of them has a last name that's like Jump or something.
oh, Hannah Jump is great. Hannah Jump is great. She's
Observation.
she's very good at 3-pointers, but they completely just crushed her out at the CU game. It was
exactly.
amazing.
Because
And then Cameron Brink is the tall one who's really effective at blocking, and she was pretty like, I think they kept her fouling out. It was great. Very impressive play. I'm so glad you've been enjoying the game so
Well,
much.
it's
There's
so
been so many
funny.
good ones.
Our group is gonna go to the game
Southern Hemisphere
on the 29th versus Washington, which
Ooh.
is my alma mater. So
Oh my
like
goodness.
I'll probably wear a Washington shirt underneath, but the stuff on top. But also like they beat Washington by like 30 points this weekend.
Oh my
so I think
goodness.
Washington doesn't have a great team.
But it's pretty funny. The game is a fundraiser for this basketball coach whose first name is Kay. She died of breast cancer, but they have this like sign that they made that's like play for Kay. And I'm like, yeah.
Well, and the coach is J.R. Payne, and that's my surname, so we're well represented on that court. My
Play
goodness.
for Kay and Kay. That's true. Yeah.
Yeah, I mean, it's very fun getting to watch them, and for I guess they're not accustomed to doing quite this well, so it's.
Well, this team has been building. So Hai Sabor, who's a research scientist at NOAA and at CU, his daughter is really into basketball, and his family has had season tickets to the women's for a long time. And he was like, at the beginning of the season, he was like, I need to go to these games. Like, this team is really good, and they've been building, right? Like, it's not like a fluke that they're good. Like, these are a bunch of super seniors who got an extra year of eligibility because of COVID, and like,
Well,
they
Sherrod,
are
for example, is
very,
just.
very well aligned with each other.
Yeah.
They play for each other, which is so cool to like.
I mean, you can really see them when they're up against these massive opponents like UCLA, and they're like out heighted substantially,
Right.
like half a foot shorter than every other player, and like yet they're holding their own. It's very impressive.
Yeah, it is very impressive. Yeah.
I was wondering.
Glad you're into it too.
Oh yeah,
I think it's one of the best things going in town right now.
I know. I was on some random customer support line yesterday, and
I'm okay, thank you.
she was like, "You're in Boulder, like football," and I'm like, "No, women's basketball." Football. Oh man.
Someone else on the shuttle this morning.
Good scientist.
Like I live proposed like a 2 or 3 minute bike ride to shuttle. So that's pretty nice. Yeah, but I'm like gunning it. I see it turn into the kids' parking lot. I'm like,
That's fantastic.
Already
Spelled the right way.
plan to go to this game, and it's like for cancer stuff, and I definitely have like had some cancer stuff.
It's too perfect.
It's too perfect.
That's fantastic.
Yeah.
saved by the.
If you
Otherwise, I would have.
I've been going to a lot of these games with a friend of mine who is a former basketball player. She played for Harvard, and she had a teammate who transferred over to USC. And if you remember, like the very end of the USC game, it came down to like one girl who had nobody around her and was like shooting and missed, and it was her friend, and we were supposed to meet her afterwards, and she's like, "There's no way my friend is beating you right now." Like, she's very upset. She just absolutely screwed up this. She had like an opportunity to like win the game for USC
yeah.
right at the last
That
20 seconds.
The last 20 seconds of that game.
It was crazy. It was so back and forth.
And there was just like one missed shot.
Mhm.
But also, it's like you can talk about one missed shot, but there were so many shots through the whole game.
Oh, of course.
It's
but it
like
doesn't
not
feel like
one.
that. I'm sure.
I'm
to
sure
that.
if you're that one person.
If you're that one
But
person,
that's
you're
what
like,
I would
that's the
tell
one.
her if it was the coach, because it gets like these things are like mental. It's
Oh,
like,
yeah.
I'm rattled.
Absolutely.
Oh my gosh, I have to show you one more fun picture.
Oh my goodness.
So the ones you did.
They're so cute. They went to go see Santa, and they had a picture taken. Was that with you? They gave it to me as a present.
That's really cute.
I was trying to figure out who was Santa and the girl. That's so great.
Series has like a photo shoot with Santa. It's supposed to be for like little kids.
But at first I was like, is that like Jen? No, it's not Jen. It's
Honestly, Jonah looks like he could be one of the little children.
I haven't seen it.
So these are
Very, very seasonal. Yes.
Yeah, they all got out their sweaters.
That is too cute. I love it.
I was just going from the university.
stepping.
You look like a
Also a
little
dog
child.
George?
What? George then too.
Yeah, they're pretty funny.
We're
This is my.
gonna get started again here. Gonna try to keep on time.
Thanks a lot.
So hopefully you get a chance to enjoy the wonderful snacks that Gunter McGee brought.
Thank you, Brenda.
So, yeah, Anyway, and you didn't see any of this next, by the way. So anyway, leading us off on our next session, Sandra Yan from CU. So go ahead, Alex.
Okay, great. Thanks. So yes, I'm gonna talk about the impact of definition differences on projection ice-free Arctic, and that's work that I did with Maruka Holland and Jen Kay. First, let's start with kind of the current projections of an ice-free Arctic, going to the CIS model into comparison project 2020 overview paper, which showed that the occurrence of the first ice-free Arctic is primarily determined by internal variability, not scenario differences. And we can see that here, both if we look at all CMIP6 models and then selected models based on certain performance characteristics, that we can see ice-free Arctics occurring both under the lowest emission scenario, SSP 119, and the highest at about the same time. And the other thing we can learn from that is that first ice-free conditions are likely to have occurred by 2050, and likely here using the larger than 66% threshold from the IPCC. So 66% of the models have seen an ice-free Arctic, the CMIP6 model by 2050. Obviously, that wasn't the first study to look at ice-free projections, and you don't have to read the table. This is just kind of showing there's a lot of studies that have looked at ice-free projections. As part of writing this review paper that's currently in press on predictions of an ice-free Arctic, trying to kind of looking at that in more detail and trying to compare them directly, what came out is that there's almost as many definitions of ice-free as there have been predictions of ice-free conditions. And I think that's something that's not really appreciated because we always say ice-free, but there's actually a lot of different ice-frees that we've been looking at. And so what are some previously used definitions of an ice-free Arctic in September? We can use the first time the monthly mean sea ice area or extent is less than 1 million square kilometer, and use the sea ice area. That's what the SMIP 2020 paper used, but it can be an extent or area, and that has an effect on the timing, and I'll show you that. Prior to about 2005, 2008, when this 1 million square kilometer threshold kind of became the common ice-free threshold, early predictions of ice-free conditions actually used sea ice extent reaching axial zero. And there it's important that it was extent, so it wasn't like absolutely no ice, just no more ice in the grid cells that has more than 15%. So still some ice probably floating around, but the ice extent was actually zero as that threshold. Then some studies looked at the first time the 5-year running mean of the monthly mean sea ice area or sea ice extent is less than 1 million square kilometers. Or they looked at consecutive years of ice-free conditions, often 5-year consecutive years. That doesn't mean year-round, but September after September after September for 5 years in a row. Or longer-term running means, 10 to 20 years, and there's all kinds, 10, 11, 15, and so on. Or the first time the ensemble mean, either the ensemble mean of a large initial condition ensemble or of the multi-model mean being less than 1 million square kilometer. And these are all valid definitions. If you define your ice-free Arctic to be that, then that's what you're predicting, but we'll actually get very different dates if we use these different definitions. And also, generally, when looking at that, we can see that they kind of fall into two general groups of what we predict. The first one is predicting actual first ice-free conditions. So the first time the monthly mean sea ice area or extent of less than 1 million square kilometer. And all these others kind of refer to what we term consistently ice-free conditions in the review, because they look at ice-free conditions that are likely to occur after that time. So let's look at that kind of in some realization. So the first consistently ice-free Arctic, we look at the months, this is looking at sea ice extent, the monthly mean, and the 5-year running means through that, get the first ice-free conditions in the monthly mean in 2038. And in that same ensemble member, the consistently ice-free based on the 5-year running mean occurs in 2047. So almost 10 years later. Oh yeah, and then no more ice occurs in 2078. So using that ice extent of zero threshold, you can see that's really, really far delayed. And so ice-free first ice-free conditions are almost a decade earlier than consistently ice-free and 4 decades earlier than the no ice definition. And so definitions really matter. If we kind of publish a paper on each of these, one paper is like, oh, it's in the 2030s, the other's 2040s, and last one's 2070s, even though they're actually looking at the exact same model and that CI is extended. And that's not just the case in this one ensemble member that I picked to illustrate that, but that's the case in all these selected SIMP6 models, where we have the first ice-free conditions based on the monthly mean CS area occurring significantly earlier than the consistently ice-free. And we can see that there's some differences between these different definitions. So 5-year means, 5 years in a row, and 20-year means, they're not all identical, but they're all kind of in a similar ballpark, and they're definitely all delayed compared to first ice-free condition. If we use CS extent versus CS area, in the same ensemble member again, first ice-free conditions occur in 2038 due to ice extent. At CS area, with the same 1 million square kilometer threshold, that's already in 2029. So another almost decade earlier than if we're looking at CS extent. And so again, definitions really matter. We compare predictions based on CS area. They're always going to be earlier, or almost always. There's some cases where it could happen the same year, but almost always earlier than CS extent. And again, that's something that we see in all the SIMP6 models, where we have monthly CS area, ice-free dates being earlier than at first ice-free dates based on CS extent. And that's similar for consistently ice-free Arctic. And it makes sense that that's that way because, again, CS extent only counts ocean grid cell, or counts all ocean grid cells that have 15% or more CS concentration. But CS area looks at the actual CS cover. And so CS area is lower than CS extent, unless we go to very, very high resolution when they start being very similar. To further complicate that, there's also some impact of scenarios on that delay between first ice-free condition and consistently ice-free conditions. So first ice-free conditions are independent of the scenario, but consistently ice-free conditions occur earlier under the strongly forced scenarios than under the more weakly forced scenarios. So the more weakly ones being up here, the stronger ones down here. And so we can see that there is generally a bigger offset between first ice-free and consistently ice-free conditions if we're looking at the weaker forced scenarios, and where that can happen much, much later, whereas the offset is shorter for the more strongly forced scenarios. And a definition that hasn't been used, but I think that we should add to this jungle of definitions, is to actually look at ice-free conditions in the daily data. We have daily CS extent available now from the CMIP models. And I think that's important to look at that and look at predictions of ice-free conditions in the daily data, because that's when we're actually going to observe that for the first time. And I'm pretty sure that that's what's going to make the headline, Arctic is ice-free. I mean, there were already headlines saying the North Pole is ice-free for the first time, even though it was just the North Pole that was ice-free. There was still lots of ice around it, but just the North Pole. So first time, the daily observations from satellite data show that the Arctic is less than 1 million square kilometers. That's when we're actually going to have the news. And what the CSM2 large ensemble shows is that there is an offset between the daily ice-free conditions occurring on average 4 years earlier, but with a really large range of 0 to 18 years. It's offset here, and we can see that the larger offsets occur for later ice-free realizations. But even just a 4-year earlier offset is noteworthy. And earlier ice-free conditions in the daily data compared to the monthly occur in 56% of the members, with 20% of the 50 members showing an offset of 10 years or more. And some of these daily ice-free conditions actually first occur in the last days of August, so not just in September in the CSM2, but already in the latest couple of last days of August. Okay, so these are all the different definitions, and kind of related to that is how are we going to decide that we have actually reached ice-free conditions. So I was talking about this work at the IARPIC seminar a couple of months ago, and that was a discussion we had there, that kind of came up from the discussions we had there. Because the satellite observations aren't absolute, there is uncertainty in them, And so just kind of as one illustration showing the difference between the bootstrap, which is the dashed line, and the NASA team for the satellite CS area observations. And so we can see that there's a clear offset. Which one's going to go ice-free first? Well, the bootstrap, because it tends to be lower than the NASA team. But then there's also other algorithms, other more higher resolution data sets. This one probably maybe will, the NSIDC, the SSMR data might not continue until we reach an ice-free Arctic, so we'll have to switch to the AMSR-E or something else. And so we might not be the ones to decide that, but I think as a community, it's something that is important to talk about. And I think something that also inspired that was like the discussion that we see in the media now about, oh, we've reached 1.5 degree warming already, everything's lost, it's much earlier than scientists predicted. And I don't think we want to be caught with that again, like, oh, some people say we're ice-free, some people say we're not. What are we gonna actually consider ice-free, and then kind of agree on these same definitions to make predictions of ice-free that hopefully align with that. So if we're gonna call it based on CS area, because that's gonna be earlier, then we should make predictions of ice-free conditions based on area as well. Yeah, so that's kind of the call to action that I hope we can have some discussion about. So to think about how will we consider when we have reached an ice-free Arctic, and then to kind of align our predictions with that. But also just in terms of the prediction community, kind of think about whether we can agree on one definition for ice-free. And I would recommend CS area, as it's not as resolution dependent. We're going to go to higher resolution models in the future, and extent is very sensitive to the resolution. And so just by changing the resolution, we might get earlier ice-free Arctics because of that. And yeah, that will also help kind of assessing these recalibration methods that Alec mentioned that have been coming online more and more and that are really cool. But it's really almost impossible to compare them because they use different models, use different definitions. So these two most recent ones use area and extent. And so to really assess the impact of just the recalibration versus just definition difference, you can't really disentangle it unless you redo the whole analysis. To close off, so one way that I like to look at ice-free conditions is the probability in a given year, rather than just focusing on the first time ice-free conditions occur, because I think there's a lot that will happen in the Arctic after that. They also provide information both on first and consistently ice-free condition. So first, any probability above 0 means some ensemble members have gone ice-free. Consistently usually is when it's in the likely threshold, so over 66%. But also if you have a different threshold that you're interested in, you can just read that off without having to be tied to what the person kind of making the prediction is looking at. Also, I think it's really important because it really shows that there is still an impact of the different emission scenarios on the Arctic, even though we will probably see an ice-free Arctic under all of these scenarios. The Arctic will look very different under the high, medium, and low emission scenarios, with an ice-free Arctic virtually certain to emissions could decrease again, becoming less likely again as the Arctic sea ice recovers. And tied to that is also that we need to look at ice-free conditions in months besides September, because that's where we see the biggest scenario impact, where we have under the lowest emission scenario, unlikely by the end of century ice-free conditions in September and August, so possible but unlikely, to ice-free conditions likely in September and some possibility for 2 additional months, up to 3 months of virtually certain ice-free conditions under the SSP 247, so kind of this middle of the road one, and then virtually certain ice-free conditions based on these CMOP6 models in 5 months of the year, with a possibility of 9 months of ice-free conditions. And so in Arctic, that could be ice-free as late as January, which is like astonishing, and obviously will be a very, very different Arctic than if we occasionally get an ice-free Arctic, or even every year get an ice-free Arctic in September. So predictions on the ice-free Arctic are really very strongly affected by how ice-free conditions are defined, with impacts of the predictions of a decade or more. So it's really important when we look at prediction on ice-free Arctic to clearly differentiate between a first possible ice-free Arctic Ocean and consistently ice-free conditions. And ideally, we can kind of start agreeing, just like we agreed on this 1 million square kilometer threshold, kind of agree on a new common definition of ice-free using sea ice area and this 1 million square kilometer threshold, and then looking at first using the monthly or even the daily data compared to consistently ice-free conditions, after which ice-free conditions are basically likely unless the forcing comes down again. I think it's important that we talk about the daily ice-free conditions and that they could occur before monthly ice-free conditions, and moving towards showing probability of ice-free conditions in a given year as well as in months besides September. I think is really important to really convey what the scenario impact on sea ice in the Arctic is going to be in the future. So, thanks.
For a couple questions, anyone? David.
So I really like that you mentioned the uncertainties with the passive microwave products. And I guess in addition to the sort of area question, there's also a thickness uncertainty in those products. I think it's up to 40 centimeter thick ice can be classified as not ice in them. And so should we also have a passive microwave ice-free, like Arctic in the model that would be, you know, the ice thickness is less than this plus some concentration or something like that. I don't know if have you thought through that?
Yeah, I think that's a really good idea. Like, I think aligning our predictions with what we're actually going to be observing, since it now seems like very likely that that's what we're going to see, I think is really important. So we're not caught like, oh, this happened like way before we predicted it or something. When afterwards we can analyze and be like, well, actually it aligned it, but then it's I think it's better we think about that now rather than after the fact to realign it. And so, I think having that, like kind of what Marika said, we'll have a discussion about diagnostics. So having kind of what will the passive microwave signature be for in the model for the simulated sea ice, I think would be really cool.
Just gonna say along those lines, Laura's done something like that for the Southern Hemisphere, just kind of like, okay, if the threshold's 40 centimeters and let's set that all to 0%. Now, how does that affect variability? So not ice-free conditions, but that'd be interesting to see.
Ed, great talk, Alex. Earlier in the talk, you mentioned that internal variability dominates over scenario uncertainty, right?
For the first ice-free.
And that's why the low emission scenario required ice-free years as early as the high emission scenario. But what's the role of model uncertainty and mean state biases? Because I imagine the models that have early ice-free in that low scenario, they probably have very low sea ice already, like in present day, right? And so if you take how do you think about that?
I mean, there's definitely model uncertainty, and we can see that here. I mean, some of them, even in selected models, have first ice-free potentially occurring before 2020. And so they have a low mean bias. But kind of here we have all the models are just the same. I mean, sometimes they don't all have the lowest scenario, but they're the same ones across the different scenarios. And so we still, within the internal variability uncertainty, we still see that they're occurring at about the same time.
Like I guess again with the sort of having the public or the reactions from the public, right? Especially when you do those PDF plots, right? I wonder if we want to be careful to exclude maybe models that we know the mean states are really off, right? Because if we're saying, hey, we have these models that say we would have already had a 20% chance by now, or I mean, we're entering the steepest slope there. And so I wonder if you select models or just choose the models that have a decent mean state, how does that change?
I mean, this is already looking at the selected models only, but that's using the SMIP 2020 definition. And I think these recalibration approaches are really interesting. And I think that we should do more of that. But I think, like, again, like knowing which one is the best way, because like in the last year is one that said it should be 10 years earlier than previously predicted based on recalibration. And the other one was, which should be actually 10 years later. based on the atmospheric circulation and things like that. And,
Cool.
but I do agree that, yeah, this is already looking at the selected ones, but maybe those are not the best criteria. And I think thickness has been shown to be really important, and that wasn't included here. And I think in terms of the mean state thickness, so if we're getting to better, like what Alec was showing, like better assessment of model mean state thickness simulation, I think including that in the selection to kick out the models that are already way too thin and hence go ice-free much earlier would be really important, yeah, to kind of improve the messaging.
All right. Well, thanks, Alex. Let's continue our ice-free presentations and move on to Chris Wyburn Powell. So I think you should be able to share, Chris.
Looks good. Cool, yeah, thank you. Yeah, so following on from Alex's talk, I'll be talking about how an earlier ice-free Arctic is expected due to the current realization of Pacific decadal variability. And so I don't really need to give much of an introduction about what an ice-free Arctic is, but we'll just say again that the first ice-free Arctic is likely to occur sometime in the 2030s or 40s, independent of emission scenario, and that's across the CMS6 models. If we just look at the uncertainty that's due to internal variability by looking at some large ensembles, but I'm showing on the bottom right here, we can see that the first ice-free year ranges by around 25 years between the different ensemble members. And even if we were to just look at low frequency variability by taking an 11-year running mean, we only reduce this uncertainty to 16 years, which just emphasizes the amount of internal variability uncertainty we have for an ice-free Arctic, which is still present if we take away the interannual variability. And so then this prompts a question of, can we reduce this internal variability uncertainty? And today I'll be talking to you about how insights from the Pacific climate variability can be used to have a look at this question. So one way in which Arctic sea ice is expected to be impacted in the low frequency variability is by the interdecadal Pacific Oscillation. And you can see the figure on the right here shows the sea surface temperature correlations with the IPO index. And so this was, the IPO was shown to be important in CSM1 large ensemble in determining the timing of an ice-free Arctic. And then in this Screen and DESA paper in 2019, the figure on the bottom right here, they found that an ice-free Arctic occurred 7 years earlier when selecting trajectories that start in initially negative IPO phase compared with initially positive IPO phase. And then they proposed that the mechanism which brought this about was the transition of the IPO from a negative phase to a positive phase. And during this process, there was a deepened Aleutian low, facilitating greater poleward energy transport, resulting in faster sea ice loss. So if it really is the transition from the negative phase to the positive phase of the IPO, which is causing these changes in ice-free trajectories, then we need to have a look at how this performs in these different large ensembles. So we're using the definition of an IPO phase based on persistence for 10 or more years, and this is to align with the persistently negative IPO that we've observed, but it hasn't always been particularly strong in magnitude for this negative phase. And so if we look at the different large ensembles in the figure, we can see that on average it takes 7 years to transition from an initially negative phase to a positive phase of the IPO. But there's a very large amount of variation between the different ensemble members within a large ensemble. And I'll also note that CSM2 and CSM1 both show a relatively rapid transition from a negative phase into a positive phase of the IPO. And so it's not just the IPO which is being proposed as being influential for the Pacific influencing sea ice. The PARC, or the Pacific Arctic Tail Connection, has also been shown to be highly influential. And so on the top right here, I'm showing you a figure from Baxter et al. 2019. And so here we start off with negative sea surface temperature anomalies in the northern equatorial Pacific, which is also a similar condition to when we have a negative phase of the IPO. This is propagated to the Arctic via Rossby waves, which results in enormously high geopotential heights and eventually leads to reduced sea ice. This Park-Tel connection in the observations has been much like this schematic, but in the pre-industrial control, there's also been evidence that this has been highly variable. And so the figure on the bottom right here shows the Park-Tel connection on the y-axis, and this is the correlation between the sea surface temperatures in the northern equatorial Pacific and the geopotential height anomalies in the Arctic. And so in red, we can see that the observations have been during this instance of the Park-Tel connection being negative, but we find that there's a large spread during pre-industrial control of these different black dots showing different time periods within the pre-industrial control, suggesting that there are multiple situations which can occur with this different Park-Tel connection. And then on the x-axis, what I'm also showing here is the fact that there is a relationship between the Park-Tel connection on the y-axis and also the correlation between the sea surface temperatures and the September sea ice extents. And so when you have a negative phase of the Park-Tel connection, as we have of the observations, we generally also have less sea ice extents. So when we're talking about the Park-Tel connection in the subsequent analysis, we're using this box of sea surface temperatures here, and when we're relating it to the geopotential heights, we're looking at this region of the Arctic over the Beaufort Sea. And then we're also using 8 different large ensembles to provide us sufficiently large quantities of data to look at both the IPO and the Park-Tel connection on sea ice trajectories. So one of the things we want to look at first is whether our large ensembles are accurately simulating the Park-Tel connection. And so here I'm showing you the same idea of a plot that I showed earlier, now this time for CSM2. And the different colors here represent different initial years for our 40-year time periods. And then we've also populated this with the 50 different ensemble members. And so there doesn't seem to be a large determination of the position of these correlations, depending either on the time period or on the independent ensemble members. Then if we now look at this in a wider context for the 8 large ensembles and for the observations in the bottom right, we can see that the observations, which are also plotted on the other subplots as this red square, we find that often the large ensembles do not reproduce such a negative state of the Park-Tel connection. And even if they do, it's usually a relatively unusual occurrence. But still, when this negative Park-Tel connection occurs, for most of the models, we find that this is also associated with correlations of lower sea ice extents. So kind of following on from the Skrini and Dessa analysis, they just looked at CSM1 large ensemble, and that figure is reproduced in the bottom here. And that shows that when there's significant differences between the different trajectories based on the initial phase of the IPO, that's bounded as black bold lines. And if we look at the rest of the large ensembles, we find that there's usually very little difference between the trajectories based just looking at the IPO and starting from a 4.7 million square kilometer initial point. And in fact, we even have ECF3, which is the other one shown in the red outline, which has the opposite situation, whereby it's a positive initial phase of the IPO, which is associated with an earlier ice-free Arctic. And so we wanted to repeat this analysis by looking at by pooling 11 different trajectories, so not just starting with one initial state, but looking at 11 different states between 4.2 and 5.2 million square kilometers to give us a greater number of representative samples. And so when we do this, we find that there's some instances where there's a greater number of, that there is significance between these two different trajectories, although it's generally short-lived, and CSM1 still stands out as being the large ensemble with the greatest length of time where there's consistent differences between these trajectories. So just to summarize this for ice-free years on this plot here, we find that 6 of the 8 large ensembles show that initially negative IPO results in an earlier ice-free projection. And this is shown on the figure here by anything that's to the left of the dashed line is earlier than the ensemble mean. But we note that it's only CSM1 and CSM2 which show that there's a significant difference between these two trajectories as shown by the black dots. And the other model which stands out is ECF3, which shows that it's actually a positive phase of the IPO, which is significantly different and significantly earlier from the negative initial phase of the IPO. So we also wanted to look at the Parktel connection. And if we just use that as a predictor on sea ice trajectories, we find that there's never any significant difference between the trajectories just looking at the Parktel connection. And we'll also note that for CSM1, there's almost no difference at all between these trajectories selected based on the Parktel connection state. However, as I'm going to show you in a minute, sometimes the Parktel connection modulates the effect of the IPO. And so when we consider both the phase of the IPO and the Parktel connection, we can sometimes increase our specificity in ice-free year compared to just looking at the IPO. And so if we look at this based on a few different groupings of models, firstly, we'll look at CSM1 and CSM2. So for both of these models, we find that it's when the IPO is negative, coincident with a negative Parktel connection, when we have the earliest ice-free conditions. And then conversely, during positive IPO and a positive Parktel connection is when we have the most delayed ice-free conditions. And this is not the case for all of these different large ensembles. And in fact, we have CANISM2 and CANISM5, which behave the opposite way around, such that it's a positive Parktel connection, which modulates the effect of the IPO to bring ice-free conditions earlier. Further, we have ECF3, which is behaving very differently again. And it's I'll point out here that ECF3 is also an outlier in terms of the mean state and high internal variability, as it has a rapid decline from high sea ice extents to ice-free conditions. Here we have negative Parktel connections patterns are causing this wider distribution. So if we just look at the IPO on its own, we have a much more narrow expectation of the range of ice-free years, but then just selecting from negative Parktel connection, these are much extended, so that we have a range of 17 years between the negative IPO and positive IPO during the negative Parktel connection. And finally, we have 3 of these large ensembles which show that there's relatively little influence of the Parktel connection on ice-free years. So sometimes we see that the Parktel connection is modulating the effect of the IPO, but there's no real overall consensus between all of the large ensembles. And so I'll just wrap up here. So do we have consensus between the large ensembles? Well, if we just look at an initially negative IPO, this brings about an earlier ice-free Arctic for all of the large ensembles we looked at, except for ECF3 and MARC 6. But we only find at CSM1 and CSM2, which is showing this earlier ice-free conditions are significant compared with the different phases of the IPO. And finally, the Parktel connection often modulates the IPO's effect on ice-free year. And generally, if we include both the IPO and the Parktel connection state, then we're able to have a greater range of ice-free years which we predict. However, we note that CSM and CANISM generally produce opposite results of how the Parktel connection is modulating the IPO's effect. And finally, we know that there's currently a negative IPO and a negative Park-Kell connection. And so if we consider this, all of the large ensembles, so 7 out of the 8, suggest an earlier ice-free Arctic by approximately 2.5 years relative to the ensemble mean. And I'll take any questions.
Great, we have time for a couple questions. Jonah.
I have a question. It's really interesting. I'm wondering if you did this with pre-industrial control simulations, like to kind of expand the volume of your data, do you think that would be helpful, or do you think that like kind of existing in a mean state with consistent forcing is really important to get this result?
Yeah, it's a good question. I think when we're making predictions for the future, it's usually important, I think, to try and start with a mean state which is similar to how we're starting out. And so that's why we started the trajectories very close to the observational value. And so I'm not sure if there is much evidence that the Park-Kell connection is particularly sensitive to the mean state. But I think that's one extra consideration that we'd have to think about if we did look at the pre-industrial control. So I think by looking at the closer to present day mean states, then we can rule out some other additional factors that we'd have to consider.
Excellent. Other questions?
Yep.
Of course.
I can shut up whenever you want to. Chris, do you have a sense of how models simulate the IPO? Like, is it, because I know, for example, there's a lot of models spread in how they simulate ENSO, and
yeah,
historically struggled anyway in how to simulate ENSO. So, yeah, are they all doing their own thing with the IPO, or?
I think there's a wide range, shall we say, and it's also a lot of the models are at this kind of transition point between the historical period and the future scenarios when maybe the IPO was simulated relatively well in the historical period, then it degrades in the future. And yeah, but there's a big range in the realism of the IPO. And I think that's why it's important to look at multiple models, and hopefully there's some consensus that appears, but it appears that there's not a huge amount of agreement that is actually occurring. I'm not sure if that's really due to the IPO or other factors.
Thanks.
So I think Qinghua had a question online.
Yes, thank you. Yeah, I have the same question just asked by the ad, but I have another one. Just it's very nice talk. My question is that the seasonality. Do you think the model guys are right in observation? Maybe some season, but the model different. What do you think about the seasonality of this park or this linkage? Thank you.
Yeah, that is a good point. That is something that isn't really something that I've looked at so much, just because of the previous literature focusing on this, the summer mechanisms. But I think that'd be really interesting to look into, and that might give us some more information as to how the models may be biased, and help us kind of determine which models maybe we can trust more than others. But I think that's definitely a good point.
Thank you.
Maybe one last question. Yeah, Jen.
I just had a quick question. This is an interesting approach, right? To take the literature and look at things that are happening in nature and see if you see them in the models. But another approach, and I think you've taken it, so I want to hear from you on it, is to try to see if you can just ask what conditions lead to early ice-free conditions in the model. Like irrespective of all the indices that are out there, like if you just make maps of what the sea level pressure anomalies look like or what the SST anomalies look like, are there any hints from that kind of analysis that could be useful here? Because I'm a little nervous that we're like relying on these like boxes and indices and we're obscuring physical mechanisms by doing so.
Yeah, and I think that's a good point, because also a lot of these indices are based on observations which may not be actually typical to the climate system. And so, yes, I think I have looked at like the sea level pressure fields, the sea surface temperature fields, and there is a little bit of a signal with the sea surface temperature that looks a little bit like the IPO, which was which was one of the reasons to pursue this line of inquiry. Sea level pressure fields, I really don't see very much of the signal, and that might just be because we're looking at quite long time periods. And I wonder if there's, I looked at the Aleutian Low Index, for example, in this analysis, and it appears that there's very little influence from that. So I'm wondering if maybe for the sea level pressure fields, that it's just too long of a time period for much to really appear.
Great. So with that, thanks, Chris. We'll move on to Megan Helmberger for more of a ocean perspective on this.
Looks good.
Okay, great. Hi, everyone. I know some, but not all of you. I'm Megan Helmberger. I'm a postdoc at Colorado State University working with Jim Hurl. And today I'm going to be presenting some of my work from my PhD with Mark Serez. So largely I'm trying to look at what the seasonality of ocean heat gain calculated from the surface heat flux from 3 different reanalyses. I don't really need to go into this in much detail, but as we know, the sea ice is getting younger and thinner. I really like this figure because it shows the years changing, or the age of the sea ice changing from 1985 to 2021 in March. And it really gives you a striking contrast between earlier in the record compared to today. So the main goals of this work were to look at spatial and temporal patterns of ocean heat gain from 1979 to 2018. I wanted to look at the differences between this heat gain from 3 different reanalyses because they use different parameterizations for a lot of their atmospheric conditions. And another piece that I thought was important was looking at the ocean heat gain over sea ice and versus open water to see if that changes trends, to get an idea of how much ocean heat gain is available for sea ice melt versus what is potentially being stored in the surface mixed layer across the Arctic Ocean. And lastly, I wanted to look at the trend in ocean heat gain and whether that fits with our decreased observation or observed decrease in sea ice extent across the Arctic Ocean. So just to briefly go over the methods, it's mostly averaging and summing, so nothing too complex here. But I started with sub-daily data from ERA 5, CFSR and MERA 2. Those are averaged daily values, and then the ocean heat gain is calculated using the surface heat flux equation. Those values are separated over ice and ocean using the coordinating sea ice data from each reanalysis. I could talk a bit more about this in the future of how those compare to one another if you're interested in it, but it was important to use the specific ones for each reanalysis. And then those values are summed for monthly. They're subset from April through August. I wanted to focus largely on the time period where you have the sea ice starting to decrease after the March maximum extent, and then up until you get your sea ice minimum extent in September. Those are summed to seasonal values. And then you have a subset of just the Central Arctic Ocean and the marginal seas. So we're excluding areas that you get a lot of input of ocean heat from the south and the Canadian archipelago mostly. So this just, I wanted to throw out there just to reiterate some of the methods for calculating ocean heat gain. It'll be referred to as OHG going forward from here. So to jump into some of the results of this, here's a climatological average of ocean heat gain in megajoules per meter squared. CFSR, it's hard to see, but CFSR is on the top left for us in the room. ERA 5 is next to that and MERA 2 is in the bottom. And I mean, overall, you have some similar patterns where you have more ocean heat gain around the coastal areas, where you have that ice melt earlier on in the season and lower values, excuse me, as you approach the center of the Arctic. But I think the most important thing here to note is that you have much smaller values in MERA 2 on the bottom than you do compared to CFSR, particularly in then ERA 5, which is more in the middle, but falls closer to the values that you're seeing in CFSR. So each point here is one value per year, which misses a lot of the detail, which is why I showed you the previous slide. That you get spatially, but just to get an idea of what we're seeing temporally. Again, ocean heat gain is in megajoules per meter squared. On the top, these are values that are just over points that have had sea ice on them. And then the rest on the bottom is points over open water. And you get a lot of similarities in terms of years, like increasing and decreasing from year to year between the reanalyses. I should also say, for those sitting back of the room, MERA 2 is orange, CFSR is purple, and ERA 5 is green. The colors don't come out super clear from here, but gives you a general look. So particularly over the sea ice points, you see a pretty large spread between those values. Which is somewhat concerning to me. It can really change what your output is if you're using it to initialize a model. Over ocean points, you don't see as much of a spread, but there is a bit more noise in terms of how those temporal patterns align with one another between each reanalysis. So here are the colors are different. That is something I should correct in the future, but CFSR is orange now. ERA 5 is red and MERA 2 is green, but you still see that MERA 2 is along the bottom. These are total ocean heat gain values across the entire Arctic Ocean. They have not been separated out between ice and ocean. So here you do see somewhat of a positive trend in all of these values, and you do see similar patterns of increase and decrease from year to year, similar to the last figures. But in the previous slide, we didn't see any of these trends. So there's definitely a piece when you're taking into consideration the ocean heat gain for the whole Arctic Ocean versus when you're separating out those values based on surface type. So to dig into that a little bit more, when you have ice and ocean water subsetting, since you're only looking at one piece of the surface cover, whether that's ice cover or ocean cover, you're going to not be taking into account the change in its surface type. But when you're looking at the Arctic as a whole, whether you have that piece of ice on the right being that size or larger if you're in March or less if you're in September or a different year, that can significantly impact the trend that you're seeing. So we don't see a trend in the separated ocean heat gain values because you're not taking into consideration the difference in the area of sea ice versus ocean, but you are when you're looking at the previous figure. So I just wanted to throw up a couple of spatial maps now that we've looked at the temporal patterns. And I've highlighted 1982, 96, 2007, and 2012 to compare 2 years that have pretty high sea ice maximums or minimums, and then extremely low sea ice minimums in September for each of the models to show that for the most part, there is agreement in terms of the spatial pattern that you're seeing. So there's in the high sea ice years, you have larger positive values of ocean heat gain along the coasts. And in the central, you have negative values of ocean heat gain. And I guess I should say negative values are up from the surface, positive values are into the surface. And then in the years where you have extremely low sea ice extents, that you get larger positive values across the Arctic, and fewer negative values. The other important thing for me here is that there are similar patterns between reanalyses that you do see, especially in 2007 is pretty well highlighted, that there's this large negative values across the central Arctic along the Beaufort Sea, Canadian archipelago, and towards Greenland. And on the right, just briefly, there is percent differences to give you a different view of those types. So down in the bottom right corner here, you can see that between ERA 5 and MERA 2 and CFSR and MERA 2, that there's pretty large differences in their values here. I should say this one was over sea ice. The next one is over open water, and it tells very much the same story, that in years where there was more ice, you have more negative values. In years that there was less ice, you have more positive values. And fortunately, particularly in this set over open water, there are pretty similar patterns, particularly along the coastal regions. So part of that was like, okay, so what is contributing to these large differences, particularly between MERA 2 and CFSR? Here, CFSR is green, MERA 2 is orange, and ERA 5 is blue. On the top for all of these figures, it's sea ice values over sea ice grid cells, and on the bottom are values over open ocean. On the left, it's net shortwave radiation. On the right, it is net longwave radiation. And again, these are in megajoules per meter squared to keep with the ocean heat gain values. Unfortunately, in the net shortwave, you have MERA 2 that's along the bottom. And when you're looking at that compared to CFSR, there's quite a big difference in what those values are. And that, to me, is a bit concerning, because for the most part, like, we know how much downwelling shortwave radiation is at the top of the atmosphere. And I'm pretty sure that most of these reanalyses like use that value as their input, but then what's happening in the atmosphere between aerosols and clouds and those variables, which are pretty heavily parameterized, especially over the Arctic, is contributing to this gap in value. In the net longwave radiation plots, you do see similarities, that MERA 2 is again at the bottom of those values, but there's not quite as large of a spread throughout most of the years. In the interest of time, I'm going to go through this a little bit quickly. Again, these are the same types of figures: latent heat on the left, sensible heat on the right, over sea ice on the top, over ocean on the bottom. And MERA 2 again stands out in the latent heat as having less negative values than as CFSR on the bottom. But then CFSR has much higher sensible heat values, especially over sea ice. I'm mostly talking about sea ice because that's where the largest spread is. And I think that with sensible heat, I mean, granted, both sensible heat and latent heat in terms of the net surface flux are very small values comparatively, and in reanalyses, they're not really well captured because most of them are parameterized. So this is not necessarily a great piece of analysis. Like, you can't make the whole argument based on these figures, but I think it was important to look at each piece of the net surface flux that I was working on. So I guess just as a recap here, to look at spatial patterns of ocean heat gain over time, yes, they are largely variable from year to year, and they have different values over ice and over open water, different patterns. We did see that they are different between each reanalysis, and much more so over sea ice surfaces. And that's partially, I looked at albedo and I didn't include that in this for the sake of time, but there are some differences between albedo that's used in each of the reanalyses that is contributing some to this difference as well. They're not huge differences, but there's still some there. Separating the data out does over ice and over ocean definitely does change the trend. As there is no trend in those figures versus the whole Arctic, you do see a trend that fits with the observed decrease in sea ice extent. So with that, thank you all for listening.
Questions?
I have a quick one. How did you, I don't fully understand how you determine an ice grid cell versus an ocean. Was that like the annual average? It had some ice, or any time during the entire record it had ice?
Yeah, so I didn't include that either, but I took daily values of sea surface cover, so of ice concentration or sea ice fraction from each reanalysis. And for the daily value, I just subset if there's ice here, take that value and put it in the same grid cell from the ocean heat gain to comprise it of ice on that day. So there is a little bit of
Oh, okay.
spread.
So it's summarized over the day.
Yeah.
I mean, all the
Over
days of the
the,
year.
yeah,
Yeah.
yes, exactly. So that's why there's a spread in some of the plots that there's like, oh, there's ice in these areas, and that's why you see ocean heat gain values there, but also there's like values over ocean too, because
some days have.
Yeah, some days have ice and some days don't. Yeah.
Okay, thank you.
Yeah.
Other questions? Yeah, David?
I have two. One just definition is, does the ice count as part of the ocean for the heat gain? Like, is this the heat gain basically below the snow interface?
So I think that goes along with this question. It's because it's calculated from atmospheric variables. It's largely like what heat could be. It doesn't take into consideration like conduction through the ice into the surface of the ocean. Does that? No.
Okay, so yes, basically it is. Yeah, and then I guess the follow on question is, I mean, you sort of started getting at this, but what do you think is the difference here? I mean, you hinted that it was aerosols and maybe the downwelling shortwave, but is the ice is the ice thickness, is the ice concentration in the different products different? Like, why?
Yeah, I didn't dive into the sea ice characteristics because I was largely working with the atmospheric variables, but that's definitely a good question and something that I need to dig more into.
I have a quick comment. I know that Mara is a little bit wetter than
Mhm.
most of the reanalysis. I'm not sure if that is
So that-
potentially
yeah.
contributing, especially to the temperature being the lowest and the lake being
Yeah.
higher. I don't know. It was just an idea.
Yeah.
Can I ask a quick follow-on question? Is this really the best observational constraint we have? Is that why you're doing this analysis? Because I think at the top of the atmosphere, something like Ceres for the net shortwave flux would be a much better move. And I'm just not sure there's value in saying there's disagreement in the reanalysis. Like, I think we know that, like, we got to push that. And it's not surprising. I mean, reanalysis doesn't conserve energy. It's using the same parameterizations, probably even cruder than climate models, to represent many of the physical processes that are relevant. So I guess I'm just wondering, like, kind of why is this valuable? Like, and I'm sorry if that's a little bit of a strong question, but it's just like, I think there's a lot of us in the room who are very familiar with these differences, and so we're not surprised to see them.
Yeah.
And so, yeah.
Yeah, I mean, I think that, so when Mark and I were talking through this research years ago, I think the use of, neither of us, I think, had seen research that used atmospheric reanalyses to estimate values for ocean heat gain, which was like part of that to try and get an idea of what like that value plays into sea ice predictability. The ultimate goal was to get to sea ice predictability purposes using this data, and the rest of my dissertation kind of ballooned, so I didn't get to that, which is part of my postdoc. But I think the other thing is, I mean, I know that Ceres is definitely a useful data set, but people are continuing to use reanalyses to initiate models and that kind of thing. So trying to get a better understanding of what is incorporating, you know, what is causing the differences between these and trying to make a larger statement around that. I wouldn't say I necessarily like fully answer that in this presentation, but trying to get at those smaller pieces that aren't necessarily entirely understood because it's an evolving field. So
I just know, like, for example, work at ECMWF and others, and, you know, other people should feel free to chime in, but like are doing a lot more coupling with the surface and with the snow and the representation. And a lot of these reanalysis models are just, they're really lagging behind in terms of any kind of representing the physics that we know controls these processes. So you can make an estimate of ocean heat gain, but I'm not sure it's going to be the first thing somebody's going to want to use to initialize a sea ice forecast these days. And so I don't know if other people have things to chime in along those lines, but I just think it's important to kind of push the field forward and make sure we know, like, is this the best tool to be doing that, or do we have better tools available? And my sense is there's some things coming online that might be better tools for doing that kind of work right now.
yeah, I mean, I completely agree with you. I also think though that people are still using reanalyses for like a lot of this.
I know,
stuff.
but
and so that's like
true.
Part of me that's like, but I do this work and then I see people at talks all the time talk about using them to initiate.
And then
I'm
I see
like,
them submit the paper to Journal of Climate and it gets rejected. So I feel like you guys should
Well, this is a great lively discussion, but we do really need to move on. So if you could stop sharing.
Oh, yeah.
Megan, thanks. And Ian, if you could share your screen. Hopefully you're
Sure.
there. Yep.
Yeah, can you hear me and everything?
Yeah, we can hear you.
Okay.
So moving to more of an atmospheric perspective, perhaps. Ian Baxter is joining us remotely.
Can you see that?
Yep, looks good.
Okay. Hello, everyone. I'm Ian Baxter. I'm a grad student at UC Santa Barbara. And today I'm going to talk a little bit about the increasing importance of a North American source moisture transport pathway for the Arctic summertime water vapor feedback. I want to thank my collaborators on this project and to acknowledge the support from the Polar Climate Modeling Working Group, and just say that the working group was really instrumental in getting these runs started. To start with some motivation, I think a lot of recent work looking at polar amplification in particular has really brought up the importance of looking at summertime warming and drivers of changes in the summertime surface heat capacity, because this is really what's setting the pacing or rate of polar amplification. And so a lot of work recently has started to look more at a seasonal perspective of polar amplification. And so the plots I'm showing on the left is from Python and Moritzen in 2014, and then on the right is from Chung and Fettel, 2023. And these studies have kind of started to split warming into summertime warming on the x-axis. I'm sorry about that. And then wintertime warming on the y-axis. And I want to point out in particular, these two here with the water vapor feedback, and note that it's the second largest contributor to the summertime warming, again on the x-axis, just after the albedo or surface temperature feedback in red on the Python and Moritzen plot on the left. This is because, and one thing that I want to note also is that these two are kind of tied together, where changes in albedo with decreasing sea ice would be expected to increase evaporation and therefore enhance this kind of water vapor warming effect. And so the idea that we wanted to do is to look and see if, in particular, because this water vapor kind of feedback or radiative impact often assumes a fixed relative humidity, so it assumes almost an infinite supply of moisture. We wanted to see if there was discrepancies between or important aspects of this moisture transport and contributing to this water vapor feedback. To do this, we're using two different tools. The first is moisture tagging. And so what we're using is the isotope enabled CESM1 or ICSM1. And we've run a couple of experiments, but the two I'll show today, we split the globe into 8 different regions first, based on land versus ocean. And then the second set, we split into 54 evenly spaced regions based off of longitude and latitude. This ICSM has been used in the past by Hansi Singh in 2016 and 2017, as well as Tyler Harrington in 2021, to look at changes in Arctic water vapor and precipitation. However, these simulations often use the free-running CESM, and so there might be a lot of discrepancies between comparing these with, say, reanalysis or observations. And so the idea that we wanted to do is to also include nudging, which is the second bullet point here. So we're nudging to ERA 5 in the same kind of approach that you saw from Ed earlier this morning. So we're nudging U and V, but here we're also nudging T this time. We're also using fixed greenhouse gas concentrations because we're nudging that T. The idea with the nudging is we're trying to replicate the ERA 5 Arctic hydrological cycle and to get it as close as possible so we can break apart changes in water vapor availability or their radiative impacts that we see in the reanalysis. So here on the right, the top plot is showing JJA or summertime total column precipitable water from ICSM1 in blue and ERA 5 in orange. The bottom plot is showing summertime total precipitation average over the Arctic, so from 70 to 90 degrees north. Again, from ICSM1 in blue and ERA 5 in orange. And hopefully what you can see is that when comparing the blue and orange curves, they match up almost exactly. And so what this means is with the nudging of UV and T, we're almost exactly replicating this kind of precipitation or water vapor changes from ERA 5. The next thing that we wanted to do, and what I'll show you from here on out, is to kind of characterize the regional contributions to these changes in water vapor and precipitation and what their impacts are on kind of radiative fluxes. The first thing that we kind of looked at was looking at the annual cycle versus trends over the historical period. We wanted to, again, compare these previous studies from Hansi and Tyler, as well as another one that I'm adding here from Matthew Fearon that I just learned about last week. And so on the right, what I'm showing is total precipitation, the annual cycle, as well as the monthly trends on the bottom plot. So the x-axis is showing months, and I split it here into remote land in green, remote ocean in orange, and then the local contribution in blue. And what we find that stands out in particular is that during summertime, so JJA, there's about a 62% contribution from remote land. This is kind of similar to Tyler Harrington's study, which found about a 56% contribution using, again, free running circulation. And it's much higher than what Matthew Fearon found, where he found a 32% contribution from land. And this maybe highlights the discrepancies in the approach, where Tyler and I used moisture tagging with ICSM1, whereas Matthew used backtracking, as well as kind of soil moisture perturbations to quantify this land contribution. Another thing that I want to say is that just the local and remote ocean sources seem to play a bigger role during wintertime as opposed to summer. And the trends here on the bottom plot are pretty consistent in terms of their relative contributions with the kind of annual cycle in the upper plot. I think a good way of kind of seeing this land contribution comes when we look at these atmospheric river frequency trend plots that I'm showing here in panel A and panel B in the middle. So panel A is from the CESM2 large ensemble, and at the moment we've only been able to run about the atmospheric river tracking algorithm for 10 members. So this is a 10-member mean on the left, and then in the middle is showing from our ICSM1 simulations with that nudging and water tagging. And then the panel on the right is showing the average of atmospheric river frequency over the Arctic, so from 70 to 90 degrees north from these different products. And the thing that hopefully stands out is the kind of ensemble mean or this small sample ensemble mean, is that the atmospheric rivers frequency seems to occur kind of spatially uniform across the entire Arctic, whereas in our simulations with nudging, which kind of emulates the reanalysis, we find a highly spatially variable pattern. And in particular, there's about 4 major pathways that kind of stick out when we look at the panel in the middle. There's 2 that are coming from Eurasia, 1 over Central Eurasia and 1 over Siberia. Then there's 2 kind of coming from North America, with 1 coming from the Alaska side and then another coming from the just west of Greenland. And this pattern west of Greenland also shows a strong decreasing trend in atmospheric river frequency south of Greenland. And so this kind of highlights this kind of diversion of these atmospheric rivers west of Greenland, as opposed to through the North Atlantic, through the Fram Strait. And this is important because this tends to happen when you get this cyclonic wave breaking. And so when you have more cyclonic wave breaking, you get this kind of high pressure Greenland blocking in the seasonal means over Greenland. And you see this diversion of these atmospheric rivers west of Greenland. And in the past, we kind of tried to take the nudging tool and look at changes in Arctic sea ice. And what we found is when looking at long periods of strong Arctic sea ice loss, on the left is showing from era interim. I'm showing summertime 200 hectopascal geopotential heights. And then on the right is showing 200 hectopascal geopotential heights from the CESM-1 pre-industrial control simulation. And what we found was there's this kind of disconnect between changes in the central Arctic, where you have this high pressure, just as we see in reanalysis on the left, but the model struggles to capture this extension down over Greenland. And so this kind of blocking over Greenland, that would be diverting your atmospheric rivers to the west of Greenland, as opposed to through the North Atlantic. And this could be a potential source of the discrepancies between, say, Hansi and Tyler's simulations with ICSM versus ours, where we're imposing the nudge circulation. And then now to look at these kinds of changes and then quantify how they're impacting the water vapor feedback, we then switch to looking at these ICSM simulations, where we split the globe into 54 evenly spaced regions based off of latitude and longitude. And so the plot on the left is showing the contribution from each of these regions on year-to-year timescales, quantified as the root mean square error. And then the plot on the right is showing the linear trends over the historical period from each of these regions and their contribution to the change in water vapor within the Arctic, so from 70 to 90 degrees north. And then some of the things that kind of stand out on the left, looking at year-to-year changes, is it really is occurring, the moisture is really being sourced from this band from 50 to 70 degrees north. And again, it's coming largely from over land sources. There's a little bit of contribution, say, from these kind of western boundary currents as well, though, when we look at year-to-year changes. But when we look at the trends on the right, it really seems to be coming a lot from, say, eastern or western and central Eurasia, as well as over North America. In particular, the numbers here are listing just the source region tag. So for region 43, region 44, and region 47. I want to also highlight this region 47, where it's not as big of a contributor on year-to-year changes in the panel on the left, but it really stands out in the trends on the right, and it's actually the highest contributor when looking at the actual magnitudes. I wanted to highlight it in particular because when we try to quantify the kind of radiative impact of each of these regions, what we do is we take the CAM5 radiative kernels done by Angie and Pendergrass, and we use each of those trends that you saw in the previous plot in the calculation. And the one that stands out is this region 47 over northeastern Canada. It's this largest contributor to this summertime or JJA water vapor feedback. And other regions, such as region 43 over western Eurasia, seem to drop off in terms of their radiative impact. on the Arctic. And this, we think, is mainly occurring because of the kind of vertical extent of the transport into the Arctic. So region 47, northeastern Canada, has this kind of spatially vertically uniform transport into the Arctic, and this creates a very uniform water vapor feedback throughout the column and giving it this really strong impact. Other regions, such as region 43, region 41, it seems that their moisture is being diverted to higher altitudes or elevations. And so you're getting something of a canceling out effect between the upper and lower levels. Or in the case of the continental US, if you recall on this previous plot, region 41 over the continental US has a very strong negative water vapor feedback in these calculations. And this is because the water vapor seems to be getting pushed much higher into the atmosphere, say the lower stratosphere, and giving a decrease in water vapor throughout the troposphere. So it gives a very strong kind of negative water vapor feedback in this case. I also want to note that below the red arrow is where we have the local contribution to the water vapor feedback, and only about 8% of this water vapor feedback seems to be coming from local sources. And so it's really important to consider remote transport into the Arctic when looking at things like the water vapor feedback. And so to summarize, by nudging temperature and winds, we were able to almost exactly replicate changes in Arctic moisture and precipitation that we see in ERA 5. And when comparing with previous simulations with ICSM-1, the model seems to struggle to capture anticyclonic circulation over Greenland that diverts atmospheric rivers west of Greenland, creating this North American pathway that sources a lot of moisture from northeastern Canada and is the strongest contributor to the water vapor feedback. And so with that, thank you for listening, and I'd be happy to hear any kind of questions or discussion. Thank you.
Everybody stayed on time perfectly. This was great. We have time for lots of questions, but also I realized my arithmetic was horrible today. So we have an extra 10 minutes of discussion too. So if you have any questions for Ian or for any of the previous speakers, please jump in. Jen.
Great talk, Ian. This is Jen K. I think this question about how much gets sourced from the land and the ocean is a really interesting one. And I wondered if you had any thoughts about how that might change into the future, where we have ocean warming and potentially more evaporation there. You know, the land warms more than the ocean, but land is drier. I mean, how do you think this is going to change into the future?
Hi, Jen. Thanks. I think that's also a really interesting question. I know that your student Sean has been doing a lot of work on this kind of with the evaporation, and I think there's a lot of interesting things that we can look at there. One of the things that I would say is that with the tagging, a lot of the moisture that does come from the land in this case originally probably comes from the ocean, and so there's also probably a lot of interesting things to look at the interactions between the transport from ocean and land, and then how they ultimately get to the Arctic as well.
Cool. David.
Yeah, Ian, great talk. I was sort of struck by this comment you had kind of at the very end about how so little of the moisture is locally sourced. And I guess my question is, like, do you believe that? Do you believe that the parameters, we've heard all this talk about questions with the parameterizations of latent heat flux in sea ice dominated regimes. I mean, do you think, I wonder if you have any speculation on the locally sourced moisture.
Yeah, hi David, that's an interesting question too. I don't know about believing or not, but I think Hansi in the past has tried to kind of quantify, look at the different ways in which people look at local versus remote sources. And one of the things that she noted was that as opposed to using the tagging in other kind of approaches to looking at local versus remote, some studies were probably overestimating the local contribution by about 75%, as opposed to when we look at use the tagging approach. And so I think this kind of approach with the tagging is giving us a much better or more constrained quantification of how much is coming locally. And I don't know enough yet to kind of say how well the models are doing in that regard for the local fluxes and things like that.
Thanks. I was going to say, and I'm sure that Christine can say more, but you had your the analysis of atmospheric rivers and CESM too. And I was just going to say that you might be able to talk to, like, I know Rudra's run this algorithm on, I think, all of the members, many of the members. So it might be worth checking with other people what I know there are lots of nuances with how to calculate atmospheric rivers and trends and all of that, but just for that part of the analysis, instead of rerunning it, you might want to talk to some of those other folks first and just see if they're willing to share, or if they, I think it depends a lot on the algorithm and all of that as well. So that was the only comment I had.
Yeah, thanks, Alex. Yeah, I'll talk to Rudra or Christine. Yeah, thanks.
Denke again, this comment about, do we believe locally sourced moisture sources are small during summer? I think there's a lot of good physical justification for that too, right? If we think that turbulent fluxes depend on gradients of temperature, the temperature gradients are really weak in the summer, whereas in the middle of winter, if you have open water underlying a really cold atmosphere, those gradients are huge. So I don't think there's a lot of physical reason to think there'd be huge gradients of moisture in the summer. And it's really a counterintuitive kind of thing, because you see all this open water and you think, oh, I'm going to get a huge flux of moisture. But like, if you look all the way back to like the earliest models like Manabe and Stouffer, they didn't see that flux. And we don't see a cloud response to sea ice loss during the summer, in large part because we're not seeing that moisture flux coming out of the ocean. So I believe it. I like your response though, Ian. I'm not sure about believing.
Other question?
Yeah, I think I just wanted to say that I think Jen's explanation is probably the right kind of perspective. I was also thinking, I saw a paper recently by Isla Simpson, and she was kind of looking at arid regions and looking at changes in specific humidity versus relative humidity. But then the models seem to kind of had the increasing specific humidity changes with kind of fixed relative humidity, whereas looking at reanalysis and observations, she found specific humidity seemed to be constant, whereas relative humidity was decreasing. And so I think that kind of spoke to more a discrepancy between models and observations in terms of sources and this moisture availability again.
Great. Other questions? I have one back to Alex's presentation then. So I guess I never remember this metric, but the 1 million square kilometers, is this including the Arctic archipelago? Should we be including that in our metrics?
Yeah, usually it includes all the northern hemisphere sea ice. And so that would include the archipelago. And I mean, it came about because the Arctic is essentially ice-free, and most of that ice that remains at 1 million square kilometers right north of Greenland and in the Arctic archipelago, where we have the thickest ice. And so for many impacts of an ice Arctic at 1 million square kilometer, we're there. We're also there at 1.2. So it's like it's one number that's kind of became established.
Right. Well, it seems to me too, like the zero, completely no ice is kind of a very
conservative.
Yeah. I mean, it just takes so much longer to get there. And then I guess a follow-up I had to that too is, I mean, should we also be as a community putting out metrics of more regional ice-free metrics too? Because these are going to be important for the stakeholders around the Arctic.
Yeah, and there's definitely been much less work on regional ice-free. And again, there's basically 2 papers that looked at that, and there's 2 different definitions that they used for whether a region is ice free, if it's 15%, less than 15% of sea ice, or I think it was 94% ice free or something like that. So it was similar but different again, like what the regional ice free concentration threshold there is. So, but then it's even harder to kind of look at, well, you can look at all the different models, but they disagree even more because there's no compensating biases.
Right.
A lot of these metrics that have been established to kind of select models, they haven't really been looked at in the regional scale. So I think that's really important to look at it beyond just the Pan-Arctic ice free more regionally. And I think we can learn a lot too about potentially which models we want to trust more, because maybe the ones that are studying the pattern of ice loss correctly are maybe the ones that are more promising for giving us the right range of ice free predictions.
Great. Looks like John has raised his hand. Do you want to unmute?
Yeah, I have a question to Ian, and thank you for the nice talk. You explained everything very clearly. I'm wondering, is it fair to say that the water vapor may be largely controlled by temperature pattern and circulation? So if we have reduced moisture source from one particular region, it may be picked up by, say, another region. And my question is, what's the added value here for figuring out the moisture source from different regions if we don't directly compare with in situ observation? For example, if somehow we have observation from flux tower, from NEON instruments.
Hi, John. Thanks for your question. I think this kind of idea of the moisture transport maybe being redistributed to other regions might be the case, and is an interesting idea that I've been wanting to look at more. Because comparing with Tyler and your study, we kind of found a very similar contribution, right, from, say, the different sources, land versus ocean, where I think in your study it was about like 56%, whereas ours is maybe around 62%. So that maybe speaks to that kind of redistribution as well, since you've focused mainly on Central Eurasia, I think, whereas we're kind of highlighting more this impact from North America. In terms of like comparing more with like more direct in situ observations, it would be really great. I'm not too aware with what's available actually to compare, but if you have suggestions, it'd be great to talk after this. Thanks.
Thank you.
Great. Any other thoughts, questions?
Yeah, Ed. Hi, Ian. Great talk. This is Ed. Have you thought much about what happens in the spring, like in May and June? Because I know there's a bit of research showing how important moisture intrusions into the Arctic are, and that's, this very sensitive time of the year when the positive shortwave feedbacks kick in, and if you can melt that snow on the ice early, then it's got impacts on like the end of September sea ice. So I was curious. The other thing too is that in the spring, the North Atlantic storm track is still quite active, so you might see more atmospheric rivers coming in from the Fram. Because I was kind of surprised, as you mentioned, that you don't really see a Fram or like a Barents pathway.
Yeah. Hi, thanks. Yeah, we have thought about that a bit. Actually, Marika suggested that, looking at that, and so we've since started running some fully coupled versions with the tagging as opposed to AMIP style, to try and look more at things like deposition of snow or rain onto the sea ice surface and how that might impact preconditioning. In terms of looking at the transport, I have looked at spring, and it does shift a little bit more to the North Atlantic as you go towards winter as opposed to summertime. In both the kind of annual cycle as well as in the trends. And so I think there is a lot more importance for this kind of preconditioning, but a lot of it actually seems to be coming from Central Eurasia. And I think this kind of backs up some studies before from, I think, Young and Magnusdotter kind of looked at this a few years ago. And so I would say actually more of the preconditioning, if there is preconditioning, it's coming from Central Eurasia, most likely, as opposed to the North Atlantic in this case.
Thanks. Great. Well, so we're intentionally ending at 10 minutes to noon, just so that we can beat the rush for getting lunch. But you're welcome to stay and discuss longer, certainly. We're gonna restart again at 1 o'clock Mountain Time, the continuing David show. So please get back here promptly about 5 to 1. That'd be great. Marika, do you have any other words?
No, just thanks for a lot of really great talks this morning. So look forward to seeing you all after lunch.
Yeah, she and I.
Nice talk. Can I ask you what you're up to now?
Do that again. And I was like, oh, I don't have to. It's shorter.
I was thinking about.
I'll probably be there too, but check. Yeah. Seems like the, stuff in climate stuff. So I'm like,
Is your new job more like?
Fly there to do, I waited, I booked the hotel for the whole week and then I waited.
It was good to meet you. Okay. Are you, tell us what you're doing now.
Yes.
We're flying out on Friday.
Yeah, we did very last night. Yeah. I'm gonna try to get it.
I have it automatic. It's just automatic.
Yeah.
Hey.
So this is why I'm curious. I was curious about this question.
Right.
Is in basically outlining a single column model forced with, so IcePack forced with mosaic observations.
Right.
And the dotted lines are all actual observations of the heat flux terms, and then the solid blue line is the model output.
Yeah.
And
We were pleasantly surprised.
unfortunately, we have a gap right in the interesting period, but in the latent heat flux, at least in the single column model, it appears to represent, should have this pulse and latent heat flux happening.
I mean, I guess.
I would say that that's inconsistent with observations on the ground too, like from Sheba and stuff like that. Like all of that explanation that I said about temperature gradients checks out with observations
With
too.
Sheba, yeah.
Yeah.
Yeah, this is why I've been kind of, I don't know, it's only ever been just a curiosity for me.
Right.
Because it's like
I'll wait in
a
here.
small enough portion of the overall budget that.
Yeah, and I would ask, what is driving that, right? Like, what are the temperature gradients? Are they realistic? What are the moisture gradients? Are they realistic, right? Because I mean, all of these things are parameterized based on those gradients. And I would expect those gradients to be relatively small in the summer compared to the winter, which is why I think the local source of moisture from evaporation is more important than the water, and becomes increasingly important as we go to the warmer climate, because we have open ocean, like Alex says, maybe into January. Like, that would be great.
Saw that and I was like, oh my God.
Yeah, so this is forced through a 2-meter measurement from the flux slides.
That's hard. And I'm not saying locally in one instance, it might not be big. I'm just saying like overall, the gradients are small at that time of year. And so I'm not surprised to see those types. And maybe it's kind of a little bit like the climate perspective versus like, single place in time kind of perspective too. You have to always be a little bit careful of that. Funding from Ranford to bring someone in too, right?
Right.
You could ask someone local, like, why would you?
Right. Well, we were also trying to think too, the amazing thing about this working group is that, but the amazing thing about this working group is it's, as far as I remember, it's always been with female co-chairs. Except the very beginning, when it was like Dick Horowitz from UW, that was the first couple of years or something. So I kind of like the idea of continuing that tradition. So,
That wasn't something I thought about.
I think that sounds very sexist, Dave.
Whoa.
I don't know. I don't think so. I think,
I mean, I think you should find the best person for the job, and when the best person for the job just happened to be a woman for 15 years, like, that's awesome. Says a lot.
no, but I think it says a lot.
Yes, it does.
So,
Don't screw it up. Are we live? I hope this is not being recorded.
It is live, but they edit out the lunch part.
they
so
beat it out.
They will.
Marika heard it all though.
She is.
Rika's the best person to lead NSF now. She's like, no, never.
Oh, huh.
If you get switched around.
No, that's fine. I just power. Oh, that's what happened to my power.
Dave,
Yes, Marika.
I sent you my talk just in case. I'm gonna try.
I did get it. Yes.
Try and show it from here, but if there's an issue.
So strong.
Did your
Very confusing.
I love that.
Just do this rather than like.
We're just complaining. I don't know if complaining is the right word. We're discussing that this room, while it is a really nice meeting room, not the best presenting room.
No. No, it's more of a like have a meeting.
Yeah, like if,
Trying to move into the 2020s using Google Slides.
That was a really good talk.
Oh, thank you very much.
So. All right, looks like a few people are still finding their way up. We'll wait another minute or so, but. Oh, and there was a question for you from Alec Petty. Did he email you separately or?
No.
Okay.
Let me check.
Here we go. So Alec, I don't know if you're on the call anymore, but
I don't have an email from him.
yeah. All right. Anyway, you might want to send that question by email to Ed.
Yeah, sure. That sounds good. Vetoed from UCAS.
So.
Want to learn more about these nudging things.
Yeah. Well, it's an exciting thing.
Nudging these days, you know.
Nudge, wink, wink. Anyway, so let's see. So I just also wanted to mention, welcome back, and for those who were speaking already, you should have got an email from Elizabeth Faircloth to send your slides. So if you're comfortable with sharing those, she's going to post them on the website and everything after. So please do send along your slides if you're comfortable with that. So I'm going to kick off this afternoon just to give you sort of a general plan and progress of where we are with CSM3, which is going to be the next release of the model. And then also I'm going to say a little word about diagnostics, and then hopefully that can sort of springboard into a discussion later on, because I don't think there'll be quite enough time to talk about here. And so, but so though most of you know this, but nonetheless, I wanted to emphasize the fact that we're using the SAIS consortium CI component. So this is a consortium of institutions and funding agencies from all around the world. And then actually this slide hasn't been updated, but the Access Group in Australia has now joined the SAIS consortium, and they're going to be using this version of the CIS component as well. And so what does it mean to be part of this? It just means that you're contributing some amount of a person's time, some amount of funding, or whatever else to the consortium. And this is our main avenue that we can get all sorts of new physics developments into the model, into the CIS component. And, you know, so the workflow, because it's mainly me responsible for the CIS component of the CSM, but the workflow is that we put it into the consortium first, get it reviewed there, make sure everybody's happy with it, and then it meets the needs of all the different centers that are included in this. And then I will be the one incorporating it into the CSM once it's there. And so the hope is that this will be a much more rapid sort of progression, so that as updates come in, I can, you know, get them into the CSM, and we'll have a new physics parameterization, or, you know, widgets in the CIS, whatever, you know, that'll come in very, very quickly. So, so then, you know, for years, we've sort of been tied with our CSM development to the CMIP timeline. And we're kind of decoupled here a little bit this time around. But you can see here that the rough draft CMIP deadline, things really get kind of cranking near the end of this year, beginning of next year, something like that. And we're only talking about sort of the main sort of deck simulations of historical pre-industrial at this point. Because the thing is, we're not going to have forcing for future scenarios for quite a while yet. And there has to be a process there too before we can even get that. So, but in the meantime, we're going to be working on the 1850 pre-industrial climate runs, and then doing some historical and some 1% CO2 increasing experiments. And so this is just sort of the rough CMIP timeline. And then to give you an idea, so our CIS plans in terms of CSM3, you can see we're here right now, winter 2024 working group meeting. And so basically there is hope that there will be some sort of freeze of the model in summer of this year. So that'll be June, might be June 31st. But it's probably gonna happen this summer. And what does a freeze mean? Well, basically it just means that we can't really put any new science into the model. After that point, there'll just be continued sort of tuning, and you know, we'll be doing coupled experiments, and so there's inevitably going to be some issues there, and we're going to have to do some retuning and adjustments in the whole coupled model at this point. For the Polar Climate Working Group, we've got a lot on our plate, but I will say to start that almost all the code for this is already in the model, thanks to the SAIS consortium. You know, that's what we've been able to do. And so we're just using physics that's already there. What we don't have experience with is actually using it in a coupled framework and understanding how it affects the coupled model. So the thing that we've done here is we've said, well, okay, the top two arrows with the black outlines around them are basically saying these are things that are almost definitely going to make it into CSM3. So one of those things, I've got simulations underway now with this new advanced snow physics. And so this follows a lot of the ideas that were in Olivier Lecomte's PhD thesis, you know, so blowing snow, snow going into leads, you know, metamorphosis of the snow grains and that sort of physics going on. And that will most likely be in the next version of the model. And then we also have some enhancements to the pond physics. A lot of this work Data is working on. And so those, again, both of those are very likely to be in the next version of the model. The next category is sort of without the black outlines, and these are a little less certain whether we're going to make those deadlines or not. But again, most of the code's in there. It's just that we haven't had a chance to really understand the sensitivity. And so flow size, distribution, wave interaction, that's something we're relying very heavily on Letty Roach and Cecilia Bitts. I don't know, Letty, if you're on, but anyway, but the issue there is that, you know, we don't have a lot of experience doing this in a coupled model. We're relying very heavily on those two collaborators, which has been great. I've been meeting with them regularly to try to understand, you know, some of this, but the other big thing is just a logistical problem of the WaveWatch model. It's awful. I mean, it's just a terrible model. It's really slow. It's hard to use. And so we're relying on fields from the WaveWatch model. And so it's been a bit of a burden. The land-fast ice, this is basically Jean-Francois Lemieux's parametrization. And Jean-Francois has done a lot of good work with this, but he's done it mostly in sort of a forecasting model context. And so we don't really know, again, is it going to matter in a coupled climate model? We don't really know. And so for those of you maybe who don't know, land-fast ice is just when sea ice grows thick enough, it can actually stick to the bottom in areas near the coast. And it happens around Antarctica, it happens in the Arctic, more so in the Arctic, but, you know, and it's fairly large regions where this land-fast ice is important. And so we could likely get this in, it's just doing the sensitivity runs. There are some other things sort of down this list, and you can see that the text is kind of disappearing a little bit more and turning white, and that just goes with our level of uncertainty of whether we're going to make these in or not. So there's, you know, improved conduction parameterization through the snow and sea ice that we'd like to know something more about. And this kind of goes somewhat to Lorenzo's work with the machine learning parameterizations and so forth. There's the opportunity maybe to use improved radiative transfer where we're using 5 bands instead of 3. This has come in through SICE6 as well. But again, really understanding the coupled model sensitivity to this is going to be a key thing. And then the thing that I think we can probably do right away, we just have to do a lot of simulations, is this new C-grid staggering. I'm happy to chat with people about it later, but the new ocean component MOM6 is on this staggered C-grid. And it would be desirable to have the sea ice also on the sea grid so that they match in terms of their velocities and stress terms and so forth. But ultimately, the coupling infrastructure would still be passing everything through at the center of the grid cells, so the so-called A grid. And so there's some coding and logistics that are going to be a bit more complicated with this. And then again, something that's been on our wish list, and it's kind of beyond the summer deadline, is the sea ice biogeochemistry. You know, we've had this on our wish list for, I don't know how many working group meetings now, but it's been there a long time. And I think the thing is that Mike Levy and I have actually put together a spreadsheet of the fields that we want to couple between the ocean and the sea ice. And we're getting there. You know, we've identified the things that we need. It's just putting in the infrastructure to get it into place. And then somebody, Courtney, has to actually look at those runs and assess, really assess the realism of the coupled BGC between the sea ice and the ocean. So anyway, so that's sort of a rough timeline. You know, Yeah, no worries. No, that's what we're doing. And you know, one of the methods that we've done, and David has done some great work on this already, that you know, we have this IcePack single column model, which is just basically the thermodynamics and the ITD from the full SICE model. And it's been a great tool for doing parameterization development. And so David's taken some, you know, observations from Mosaic and other field programs and so forth, and began to really hammer on this single column model version to test out the parameterizations, to find problems with existing parameterizations, and hopefully to build new parameterizations out of this. And so by using this single column method, then eventually we could get that back into the full 3D SICE model too. So anyway, so that's about enough on our sort of timeline and sort of physics that we're planning. Another painful issue is, some of you may know, you know, Cheyenne went away. And so a lot of our old software diagnostic sort of packages are now broken because they don't run on Duratia, they don't run on Casper. And while the old CS Diagnostics that was in the CSM post-processing was very helpful to assess a lot of different runs that we had done, basically right now we can't use them. And so what were they? Well, it was this nice overall package that produced a whole bunch of PNG plots, you know, and we could compare against National Snow and Ice Data Center extent. We had ICESat thickness in there, and maybe Freeboard in the future. And then I was even using some Southern Hemisphere aspect program data. But, you know, the aspect program, the problem is it's over many, many years, many ship tracks. And so it's kind of this climatology, and it's very coarse resolution and so forth. And then we did also start including biomass and other sort of available data sets. But I think this should be part of the discussion too, as we move forward here. What sort of things do we want to be thinking about? Because we have to reinvent this. You know, we have to think about something else, more modern. We have to move into the 2020s and deal with this. So on that, so fortunately, some people in the lab office were kind of listening to this. And so they realized that this is a worthwhile thing to keep going forward. And so Mike Levy and Keegan King were appointed to come up with this new sort of post-processing package, diagnostic package. And they've dubbed it CUPID, which is a great acronym, but it's the CSM Unified Post-Processing and Diagnostic Package. And so this is all going to be Python based, Python and Python notebooks and so forth. But essentially, it's going to be built to be flexible enough, so it's very easy for people to add on here. We're sort of starting from this atmospheric diagnostics framework, and they've already sort of transitioned towards Python more too. And so we have this brand new framework that we can use to build in new diagnostic packages. So as a starting point, then I have hoping, maybe I have to exit out of. All right, it's not going to let me click on here, but maybe I can exit out of the full screen mode. Or where's the Google slide thing? Oh, yeah, that's fine. Perfect. Okay, so so that's not presenting. So let me just stop sharing. Reshare. Okay, so so I've got the basics of something now, all written in Python. And it's actually done in Python notebooks. And then we have this other tool, which actually takes a Python notebook and translates it into an HTML page. It's called Jupyter Books. We use this for the tutorial this summer for those of you who are involved in this. But basically it's, you know, a lot of Python code. I think you're used to sort of seeing this. But I've tried to generalize it so that it reads into cases, and it's relying on this single variable time series format, which is still an important part of this overall. For some reason, the single variable time series format is much, much faster in Python than the old sort of history slice format. I don't even have an explanation for that. But basically, we are reading in these time series and a series of variables, and then I've set this up so that I've got these two YAML files. So it's just a text file, but it has a whole bunch of information about the region mass and the variables that we're interested in and the particular levels and so forth. And so I'm just gonna page down because we are, yes, Alice, we're gonna take the code out of here. So you can see here where it's actually reading in the YAML file and it's saying, oh, well, these are the variables of interest, AICE, HI, HS, T-surface, and here are the levels that we want to plot. And then this sort of format should look familiar. I'm experimenting with color tables, so would love feedback on this. But I think it's you know, one of the things is it's often you want to detect the difference between 0.9 0.95 and stuff like that. And so I use this really ugly color table that helps you really see the differences in the mean fields and so forth. And what I'm actually comparing here, this 59 run, is actually a wave with the flow, a run with the flow size distribution and the wave model interacting. And so I want to see, just look at the mean state of this run and see how does it compare with one of the standard sort of CSM runs, the three development runs that we're doing. And, you know, I mean, the wave run's only about 40 years, so I don't think you can ascribe very much significance to these differences here, but there are some interesting differences to be found here. But it just loops through all the variables in the file and it says, okay, well, these are the color levels and so forth. And so it just prints them all out. And this is eventually going to be in a nice standard HTML table, so it's easy to click on the different plots and stuff like that. But for now, it just cranks through a whole bunch of variables, a whole bunch of different levels, and you can do different time periods, you can do sort of things like that. And then there's a whole other hemisphere, you know, that we should worry about and think about too. And so again, it's set up so it's pretty flexible, so it can do either hemisphere. And then maybe the more important metrics are the integrated time series. So looking at ice area, volume, snow volume, which I'm getting there. So anyway, but it's yeah. So this run is the one run, the 54, is 150 years long, staying very stable. The Labrador Sea is not freezing over. You know, it's a good thing. But then the shorter, the wave ice interaction run is quite a bit shorter. It's only 40 years, but I think you can get the sense here. This is just all of the monthly data. And so you're seeing the whole seasonal cycle here over the whole period. And then I plot annual mean versions of these. And I'm not sure why the axis doesn't go out 150. I was trying to play around with this. But I did highlight the fact that there's mass available too. So it's reading in, well, it's actually reading in the NSIDC observations too. So we can compare the sort of climatological seasonal cycle of the model runs with the NSIDC. Keep in mind, these are 1850 runs, so we are quite a bit above NSIDC. So, and then And then finally, there's one more thing I wanted to show. I think this is the one. So, you know, one of our key problems is that some of our runs, the Labrador Sea freezes over. And so again, having a metric there so that I can mask just the Labrador Sea region. So anyway, I've gone well over my time and I'm not doing a very good job at timekeeping. So I think I'll just take the opportunity to stop there and maybe take one or two short questions. So.
Maybe I can ask one question.
Yeah.
Is this data analysis package all derecho based? So does it run only kind of for CXM when it's on the Anchor computers?
No, very good question. Right now it's all derecho Casper based, so NCAR machine. However, we're trying very much to build an environment that's very portable to any machine. So that's part of, there's a whole YAML file too that has all the packages that are needed. And so as long as you have a compatible version of Python with those packages available, it should be much more portable than the previous version of this package. So, yeah.
I thought it was really interesting you said about the WaveWatch model, right?
Yeah, that's right.
I've heard that elsewhere. But I'm always, maybe it's just my own ignorance, but with waves, I've always thought, well, all you need to know is the surface winds and the landmass. How hard can it be? Is it trying to develop like an AI or some kind of like much simpler?
No, excellent question.
Because I feel like you can get 90% of the answer with a fairly simple, like, yeah, I don't know if that's a whole different.
It does kind of open up a can of worms, but yes. So we have a postdoc here who's between Sizzle and CGD, MoMA Health. He had been working with Baylor Fox Kemper on sort of alternative wave schemes and so forth. And so he may have some exciting results very soon and available for this. But yeah, I mean, I think basically we had a collaboration with NOAA on this, and we brought in WaveWatch because it's a NOAA model, and that has been our standard wave model. And for the ocean purposes, you know, we've ran it at 3-4 degree resolution, and anyway, it's there's a history there, but nonetheless, we ended up with WaveWatch, and so hopefully we'll be able to find ways that we can run it a little more efficiently and/or alternative versions. So anyway, I'm sorry about going over. I did that, but I think I stopped sharing. So anyway, so our next speaker is Lorenzo Zampieri, who's going to talk about sea ice modeling efforts in Italy now.
Yes. Okay.
What sea ice is there in Italy?
I once, in the Lagoon of Venice, I once saw some freezed lagoon, but yeah, that's not really sea. Okay. Yes. So this time, so first of all, I'm Lorenzo, and I don't understand why you don't see the full screen. But yeah, let's see.
It looks like you're not in slideshow mode. There's a little button down the bottom.
Yeah. No, I am on my computer.
Okay.
Google for wins.
I had the same issue.
Are you mirroring or anyway?
Yeah. Let's try again.
Share that window.
And if I not this. Nothing.
See if we can figure it out. Hold on. There's the like.
While they're doing this, did you get my
Controls.
Did you get my
Stop sharing your window first.
Oh yeah.
Okay.
In case it doesn't
Or you
work.
have it down.
Yeah, I've got it. Yes.
Yeah, apologies.
Maybe if you share, I found it worked if you shared your whole screen instead of just the one tab or window. Kind of an annoying people.
Oh, you have to. Okay, maybe David, can you go first and then I try?
Sure.
Figure this out.
Sure. Dave was saying what was supposed to happen. All right, we'll see if I can share. Oh,
Looks good.
okay.
Except you've got your sharing thing.
I've got my sharing.
Get rid of the.
Good.
Perfect. Thanks. So yeah, a little change up. Instead, we're gonna have David Clement Sewell presenting, so.
Okay, so non-Italian sea ice. Yeah, so thanks everyone. As I think Dave kind of introduced already, I'm going to talk here about melt ponds in SEIS/ice pack. And I want to acknowledge that this is work that a whole bunch of us on the PROMIS team, which I can't remember what that acronym stands for right now, have contributed to this. So a lot of these figures are actually not things created. I should start with just a little bit of motivation. This plot on the left here is showing what we call the albedo accordion. So this is the ice area averaged albedo over the summer. The solid lines with circles on them are Mosaic and Sheba in red, Mosaic in blue, respectively. And the fainter line with the band in the back is a CESM derived albedo, CSM2, sorry, for basically the same grid cells at Mosaic and Sheba we're in. And if you look at this plot, you'll notice what jumps out to everyone, which is that the albedo time series in the model and the observations aligns quite well. So well, in fact, you say, well, David, why are you spending your time trying to do anything to this? But it's actually quite surprising that the model works out so well in the grid cell or the ice area mean albedo, because if we look at just the albedo stratified by surface type, which is shown in the upper right here, the box and whisker plots here are the model, the CSM2, just the error bars are observations from Mosaic. You can see for snow-covered sea ice and for bare ice, the observations in the model align quite well. For ponded ice, they do not. The distribution of surface albedo in the model is way too high for ponded ice compared to the observations. And so that makes it, you say, okay, well, how can the overall ice area average albedo work out correct then? Well, it turns out we actually have an offsetting bias in our pond area. And so this plot at the bottom here is showing a comparison of now the pond area fraction of the ice at Mosaic and Sheba, again in the solid lines with the dots, compared to the ponded fraction as simulated by CSM2, which is in the bands here. And effectively what's going on here is that the ponded ice albedo in the model is about twice as high as it is in the observations. But the pond area fraction in the model is also about double what we see in the observations. This has worked out to produce a reasonable albedo for Mosaic and Sheba, but there's really no guarantee that these offsetting biases will continue to exist, or for that matter, continue to hold in other parts of the Arctic. And so that's really the motivation to dig deeper into these pond questions. And it turns out there's actually one fairly straightforward mechanism that can explain both
a too high pond albedo and a too large pond area fraction. And that's if our pond's geometry is off. So if the ponds are too extensive and too shallow, we can have about the right amount of meltwater on the surface, but the pond thickness is going to be way too low, and the pond fraction is going to be way too high. And this here is a plot from Marika showing a number of different variables in CSM2 output for a single grid point. But the main thing to take away is this plot I've highlighted in the center right here, which is showing that the pond thickness as simulated by CSM2 is between about 1 and 4 centimeters. And this is too low by, about a factor of, well, somewhere between a factor of 10 and 20 compared to the observations. And if we look at how the albedo is parameterized within IcePack, this actually helps explain why we have this discrepancy. So this plot on the left here is showing the spectral albedo in 3 bands as a function of pond depth on a logarithmic scale down here. And as you'd expect, when the ponds are shallower, we parameterize the albedo as being higher, as being closer to the bare ice values. When the ponds get really, really deep, we parameterize the albedo as being effectively open ocean. And in between, we have basically an interpolation. And what's going on is right now, CSM2 is simulating ponds whose thickness is in this region, shown in the red rectangle, and hence whose albedo is considerably higher than what we actually observe for pond thicknesses in the field. And so for the remainder of this talk, I want to actually take kind of a deep dive into melt ponds and talk really about pond processes and pond geometry and how we might think about addressing this. But to start with, I want to just kind of review a life history of how melt ponds evolve on sea ice. This is heavily taken from papers by Chris Polshensky and Hayo Aiken, and conversations with people throughout the PROMIS project. And so this figure here is showing basically, you can think of this as a sequence over time. So time through the summer, increasing as we go down the plot. And the sort of key things to keep in mind are, first off, when ponds initially form, the meltwater runs downhill and fills depressions on the ice surface. So this cartoon over here, the dark blue area is a pond, light blue is an ice. This is a sort of cartoon of a vertical slice through the ice here. And I've also indicated approximately where sea level is in this sort of jagged black line. And so when ponds initially form, they form as above freeboard ponds, right? The ice surface is, for the most part, above freeboard. The ponds fill depressions on the ice. And once you establish a pond here, for simplicity, I'm not going to talk about the pond-snow interactions, although that is important. But once you establish a pond here, the pond itself drives accelerated melt. It has a lower albedo. And this accelerated melt actually is what creates having a pond base that now sits below freeboard. So long as the ice is impermeable and there aren't transport pathways for the pond water to run into macroscopic flaws like lead edges, this pond water can sit up above freeboard. And this has been seen consistently in various field campaigns. However, at some point, typically within 1 to 2 weeks of this initial pond formation, either the ice becomes sufficiently permeable that the water can drain through the ice via percolation, or the hydrologic network on the surface becomes connected enough that water can run off laterally to a macroscopic flaw, whether that's a lead edge or a seal hole. And once this happens, the ponds very rapidly drop such that their surfaces are at freeboard. And this means that basically from here on, because the system's connected to the ocean, the pond area fraction is really just constrained by what is the fraction of ice that sits below freeboard. This has been observed in a number of field campaigns, and it also has been observed via satellite observations of pond area. And once the ponds are at sea level, the pond coverage tends to sit between about 20 and 40%. We don't see the extremely high pond coverages that are simulated by IcePack. And once we're here, that's basically where the ponds remain for the rest of the summer until the lids freeze over and they seal, right? There's no longer a pressure head driving water to leave the pond. And so they're going to sit here. And this is actually the sea level pond is where the pond sits for the majority of the summer. And so this is I've simplified here in various ways, but I think these are illustrating a lot of the key processes that are what actually end up controlling the melt pond fraction really observed on Arctic sea ice. We can contrast this process with what we do in the model currently. And so I'm going to run out of time here, so I'll do this somewhat quickly. But the quick version of the current pond parameterization is that the ponds are effectively perched on top of the ice surface. The ice surface is the ice thickness is assumed to be uniform, and as soon as ponds form, they immediately start exponentially decaying. They have this exponential drainage term representing macro porosity drainage, and then when ponds do grow, however, both their depth and their area grow by a fixed ratio. So we add more meltwater, the pond gets bigger, both wider and deeper. However, the current parameterization, all of the ways that ponds drain, they just drain vertically. So we just lose depth, we don't lose area as well. And then finally, if the pond mass would depress the ice floor of the pond down below freeboard, we say, oh, well, that can't be, the system is unbalanced, so we have to actually drain pond water off instantaneously to bring the ice surface up to freeboard. Collectively, what this means is that the current parameterization can't represent below sea level ponds. And below sea level ponds are essentially where the real system sits for most of the summer. And so this is a real challenge, I think. Just to highlight with some field data that, I'm not just making up and showing you cartoons here. This is an example from some of Chris Polashensky's work. The main thing I want to highlight here is this dashed line is showing the pond coverage fraction. And the key thing to keep in note here is this pond coverage fraction decreases as the ice drains, right? So the ice the ponds don't just drain vertically, they also decrease in area when they drain. I think that's all I'm gonna say on this one. The other point I wanted to make here is about if pond mass depresses the ice locally below freeboard. We actually see, in this case, this is mosaic data showing that about 40% of the ponds on the transect had locally the ice surface should be below freeboard according to buoyancy. So this constraint is clearly not actually observed in the real world. And this has an impact. So if we compare basically single column model simulations of just the mosaic case study and compare the simulated pond and ice evolution shown in the solid blue line here with observations of pond fraction, we see that the simulations simulate substantially more pond fractional area than is actually observed in the field. The solid dots here with dashed lines are field observations from mosaic mass balance sites. And incidentally, we also get the melt rate in the summer is off, partially related to this and partially related to other challenges in the model. And so In my remaining 3 minutes here or something, I'm going to try to really quickly say what I think we should do about this. And the first thing is, I think we want to explicitly represent the hypsometry of the ice cover. I'll get to what hypsometry means in just a second, but this is essentially the mechanism that would allow us to control depth versus area changes, how to parameterize when we lose water, how much area should we lose, and it would also enable us to have ponds below sea level. I'll come back to these remaining changes afterwards because they all basically follow from this. So what do I mean by hypsometry? Hypsometry is essentially the distribution of elevation relative to sea level. So an example taken here from Wikipedia is shown on the right, where you have mountains are high, you have sort of the average height of land, and then the average height of the seafloor, and then a couple really deep trenches. And these types of studies have been done on sea ice as well. This is a really nice example from Jack Landy's work. And the assumption that I'm going to make here implicitly with this hypsometry is that water pools in the lower elevation parts of the ice category, which is fairly consistent, I think, with observations and with the physics. Now I say parameterize this to start with. How I think we should parameterize this, or I'm proposing we start with the absolute simplest thing, which is just parameterize this as a straight line. And so here's an example of doing this type of hypsometric parameterization. On the left here, this is showing the height above the base. So this is not above the ice base and not technically hypsometry. And I think it makes sense to actually have this hypsometric curve vary as a function of ice thickness, because otherwise the system sort of, you get to these really strange non-physical things where you could have, if you just had a constant hypsometric curve, then as the ice gets really thin, you end up with ice surfaces that are substantially below the base of the ice, which is physically rather strange. And then the other thing that having this parameterized as a function of ice thickness lets us do is we can then take the observational constraint that when ponds are at sea level, they end up being about the same area fraction, and we can actually encode that directly in the parameterization. And so the right here is showing the actual hypsometric curve. So this is height above sea level now on the Y. And I've set up this parameterization such that when the ponds are at sea level, the pond fraction should be about 0.27, so right in the middle of that range. The following changes here, I'm not going to go into too much detail, but they all basically follow from this hypsometry. Once we have hypsometry, we can have a pressure head, and we can change our drainage to be based on that pressure head, and we can also have the freeboard constraint applied to the entire category. And if we make these changes in IcePack, it's not perfect, but we actually, I think, can get a better match to the observations. So the main one to focus on here again is this pond fraction, the second from the top. The original current IcePack parameterization is in blue again. Now this orange line is showing our modified parameterization. And you can see here with this linear sea level hypsometry, we can actually keep the pond fraction much closer to observations, much more consistent with what we saw in the field. It's not perfect. The pond depth is still too low, and there's some other sort of weirdnesses in the parameterization that I'm happy to discuss more. But I think this is at least an avenue for improving how the ponds are represented, albeit not necessarily the perfect one. So no, I'm probably over time at this point, but that's kind of a brief update on sort of the proposed pond changes that we've been working on here. The ongoing things we're planning to do is, I mentioned that the linear hypsometry is not perfect in some ways. I'd like to test out using a logistic type curve instead of a linear function for that. That's an example of that shown down here. We also want to do a much more detailed comparison with the transect observations. We've primarily compared with mass balance sites. And then, of course, we need to actually, as Dave mentioned, implement this in SEISS and do a whole bunch of testing and parameter tuning. So sorry I've gone way over time, but thank you all for listening.
David, maybe if you could quit while we test Lorenzo, but let's take a question while we're trying to test out Lorenzo's.
David, this is Alec. Can you hear me?
Yeah, Alec, go ahead.
Yeah, I was just wondering, maybe I missed this, but you're not exploring the topographic melt pond scheme at all from like Danny Feltham and Daniela Floco?
I didn't show a plot with that. You're right, but it also produces very, very high pond fractions.
Okay.
Yeah. Because it represents, like, within the category, it represents the ice surface is basically flat, and so you end up filling entire categories with pond area.
Right. So similar problem. Okay.
Yep. Okay. Sounds good. So looks like Lorenzo's ready to go.
Yes, we made it. Okay, yeah, sorry for losing some time. I will try to make it up now. Yes, I'm Lorenzo Zampieri. For who doesn't know me, I just moved from NCAR to CMCC in Italy, and I thought it might be nice to give an overview of the CIS-related activities that are ramping up at CMCC, also to maybe establish some collaborations in the future. So first of all, what's CMCC? It stands for Euro-Mediterranean Center on Climate Change. It's an institute which is very spread in Italy. So if you go on holidays in Italy, you will end up in a CMCC location for sure. But yeah, what we do there is the classical, let's say, modeling of the Earth system with models and observations. But there are also branches of the institute that work on adaptation strategies to climate change, and also work in the direction of climate economy and social science studies. When it comes to CIs, we are a small group. I like to put faces. So Dorotea Iovino is kind of leading us. Then it's me, Francisco Coccetta and Elena Bianco, who are postdocs now with us. And we are the people that work more on CIS model development, process studies. And then we have Andrea Cipollone and Julia Slivanova, which work more on the data simulation part of the CIS. And we all live in this Earth system modeling and data simulation division. Yes. So when it comes to modeling tools that we use at CMCC, I think we are quite a bit spread over with many collaborations. So on one side, we work a lot with SEISS and, let's say, the CSM family. And as I will show, we basically use this model for CMIP type of run, SIMIP, OMIP, and also we have a seasonal to decadal ensemble prediction system based on that. And on the other side, we work also a lot with the NEMO community. So we also end up using SI-Cubed, which is the new CIS model that comes with NEMO and replaces LIM. And with that, we do more high resolution type of simulations and also operational ocean prediction at very short lead time. And of course, I mean, we like to make things complicated. So there is also a new avenue of research that goes in the direction on unstructured CIS modeling. And that's what I've been working on recently. And this model diversity, of course, brings a lot of pros because you work with a lot of people and you establish many collaborations, but also it's, I would say, it's not straightforward to manage. When it comes to the CMCC Earth system model, as you can see, it's very much based on CSM. And the only difference is the ocean model, which is NEMO, and also we have an in-house biogeochemistry model. In this configuration, we also run the OMIP type of runs. And yeah, just, I mean, this is an overview of the performance of the CMPC CM when it comes to Arctic and Antarctic sea ice area. This is the annual mean, and you can see that we are biased low in the Arctic. The Antarctic, it's kind of okay, I would say. I'm not sure we really know why it works decently in the Antarctic, but yeah, this is kind of the status, but I think it's in line with the performances of probably CSM2. When it comes to more to the runs that we do with NEMO and SciCube, we have in this context pushed the boundaries of resolution, I would say. So we tried to play with the hierarchy of model resolution, so from 1 degree to 1/4 of a degree, which would be probably be something like our CMAP7 ocean, to 1/16 of a degree, where we resolve at this and in the ocean, and this is particularly beneficial for the ocean. And it doesn't necessarily do miracles for the sea ice increasing the resolution, but certainly so for example, we have a much better hydrography in the North Atlantic, and this then brings also benefits for the Arctic sea ice. And this is just an animation showing the sea surface temperature.
Is this the 1/16th or is this the 1/4?
No, this is the 1/16th
Okay.
of a degree. Cool. And yeah, the nice thing is that this is kind of a forced run, so it doesn't have an interactive atmosphere. So it's realistic in terms of the observed interannual variability, but also we don't have data simulation, which means that at least the ocean, it's consistent. We don't have jumps, and it's conservative. Of course, it's not fully conservative because the atmosphere is a Rayleigh analysis. Yes. Okay. And now a bit on this new unstructured CIS model. So the idea is to have unstructured modeling, in particular for global coastal ocean simulations. So there is quite a bit of focus from CMCC on coastal regions, coastal processes. So having simulating well at high resolution the interaction between the ocean and the rivers, the tides, and yeah. Also, I think makes sense in thinking a bit forward in context of sea level rise. And yeah, the idea is to do this globally. And yeah, of course, then you need also to think about Arctic and Antarctic coasts and at the sea ice model, basically. And yeah, this unstructured model is called MUSE, multi-scale unstructured model for simulating the earth-water environment. And yeah, we are building it a bit from scratch right now. So, of course, with quite a bit of input from the CIS consortium tools. In particular, here you can see the time stepping of the model. It's the typical time stepping that you would have in CIS. And in fact, the green parts come from IcePack, so they are taken directly from the consortium. But we are working on our dynamics and tracer advection because, yeah, of course, we have unstructured meshes, so we cannot work with the size. And yeah, this is might be a bit technical, but that's how our grid can look like. And in particular, we have a big grid discretization when it comes to storing the variables in memory to have compatibility with the ocean. But then the sea ice computations are all done in an A-grid setting. So we jump with the velocity at each time step, basically. And we implemented the thermodynamic part. So the static model works course, it's not surprising because IcePack works very well, but we kind of built all the drivers around it, and this is a 1-year simulation. And currently we have the MVP scheme also working, and we are playing with test cases for the tracer advection. So here I'm adjusted vecting. The idea was this to be a sort of a Christmas box, a Christmas present for my box, because it finally moved around Christmas. But yeah, yeah, we are working with this flux corrected transport scheme, which is quite different from what it's used here in the SAIS consortium, which is remapping based. But yeah, in a structured context, yeah, this is maybe less efficient, but easier to implement. And yes, and I want to conclude with a couple of slides on yeah, other SAIS modeling activities that we do at CMCC. In particular, we are investigating quite a bit also reanalysis, and the idea behind this is that we as CMCC produce global ocean reanalysis, so we want to know how they perform, but also we envisage that with all these machine learning based models, reanalysis will become very relevant, as ERA5, for example, is becoming for weather forecast models. So I think it makes sense to assess how they look like. And this work has been done by Francisco Pozzetta, which is a postdoc in our group. And in particular, we had a look at the performance of GREP, which is an ensemble of global reanalysis. So we know that typically making ensemble, like the ensemble mean performs better in a CMAP context. And we wanted to test if this is the case also in when it comes to sea ice. And we compared this to biomass and topaz, which, and of course, against observations, which, it's they're very reliable, at least for sea ice area. And we can see that the performance when it comes to the total Arctic sea ice area are, in line with that, within the difference between different climate data record from NSIC and OSISAF. We also did an investigation of the marginal ice zone, and we see that in this context, like the ensemble approach brings benefit, particularly compared to biomass and topaz, which have biases, and it makes the sea ice a bit more like the representation of the sea ice more robust. So I don't really have conclusions. I want to thank you all and invite collaborations and take questions. There are some.
Thanks for getting us back. So questions for Lorenzo.
Well, that was a beautiful simulation of the SSTs in that 16th of a degree. Are you planning to run long simulations with that high resolution?
I mean, so the simulation that we run spans a full reanalysis cycle. So it's from 58 to present. And I don't know if we plan, like what we could do is to do multiple cycles of the same reanalysis. It's not a coupled system, so we cannot really run in the future for now. But are the hopes to make it coupled? I mean, the model is coupled, so in principle we could do it by increasing the resolution of NEMO. I don't know if it makes really sense to then have a 1/16th of a degree in the ocean and then keep CAMS at low resolution. So in principle it's possible. It's just a matter of, and of course in the coupled context you need to spin up the model for much longer to have decent results. So it's it's not so straightforward as it can be in a forced scenario.
I had a question about when you had the animation of, I think, the unstructured grid and how it was progressing. I noticed, this one. No, the full globe one, not the present. I'm glad that was a good present though. I was just, I mean, I'm not sure that I was looking at the right one, but it kind of looked like sometimes it would like jump forward. I especially noticed it in the southern hemisphere as it was progressing. Is that very physical? I mean, I guess you see how you can kind of see it like walking
Yeah, I mean,
forwards.
it's
I'm just wondering if that's like, is that, I think one, it looks good as like a first approximation with an unstructured
No,
grid. I'm just curious if that's kind of like,
it's physical no, it's not physical because of course in reality the ice would move and everything would be much more smoother respond to the weather. It's physical in a sense that like the ice forms only under certain weather patterns. So it forms, it stays there, and then maybe another like colder event passes and then it forms more ice. So it's we expect it to behave like this when there is no dynamics. Of course, when you have dynamics, it's another story. But I think it's okay in this con. And also when it melts
the same way. Yeah, I guess the temperature hits exactly whatever. Okay, cool. I think I was. That does make sense if there's no dynamics.
Anyone else? Other questions? One online.
Thermodynamic simulation. I was just looking at the ice.
Okay. So yeah, I scheduled a break. So let's get back here about 2:20. There's 4 more great talks coming up. So please don't go anywhere. And so we'll see you back at 2:20.
That works.
Yeah.
Sorry.
No. Or I should have.
There's always
because
something.
I tested before the screen. I said, I don't put it full screen. It's okay. You already see my so no final stuff.
Oh, no, it's okay.
It is Dave's first. He announced you.
It's true.
Oh, you watch online?
Yeah.
I'm so sorry. I feel like you've thought through the melt pond physics much better than I have. And I'm like, oh, hopefully this all works. That looks beautiful.
Yeah. So, I mean, there's a lot of awkward things, even with trying to explicitly.
Looks good.
I think there was just a line there that I was kind of.
In like the northern,
I'm getting
it's like,
this.
it's like northern map.
Yeah.
But I.
Yeah.
You need
I guess
to
you're
stuff.
Okay.
That looks.
I'm happy. Yeah, I'm happy to.
I was gonna say, well, this is, I don't know if I have any coherent questions on the spot. Like, I think the biggest thing is I went through in detail very clearly like what's happening in reality. And then I was like, okay, now what's happening here? And I had to think through it, but that was faster. And then I was like, wait, where'd it go?
Sorry,
No, I'm not
I
mad.
realized I was running low on time.
No, you're fine.
And I think,
But I was gonna say, I don't know if it was gonna get funded, but one of the proposals I put in the fall was to NASA. And I was thinking we would do nudged runs and look at try to do nudged runs, look at melt ponds and see ESM and compare them with observations of melt ponds and see what's going on. But if, depending on where this is and where you are, if you're still here, if you're somewhere else or whatever, but I think if you're willing to collaborate, that would be.
that sounds great. Yeah, I mean, I'm certainly willing to collaborate. I think. I mean, I think even if I'm not here,
Okay.
I think it's highly likely to be able to collaborate. I mean, I've basically conversation with Chris last week about, talking about start date. And I was saying, I want to finish out actually trying to get these changes into CESM3.
Yeah.
And he basically said, that stuff, like if you started next week, you can keep working on that.
Okay.
Here, like that would be completely within the scope.
I was thinking too, like, I know that there's this code freeze date.
Yeah.
Words order. But by the time CESM3 simulations are actually run, so one, I'll probably be a co-chair for during that time.
Mm.
And I was trying to think like, okay, what papers will there be? And I think when you do this, there'll be a paper about the parameterization. And I was thinking it'd be nice in the kind of overall polar paper.
That's great.
You know, that one's like more of an overview.
Yeah.
Minute or so to get like, okay, here's general things of the polar simulation. It'd be
Good.
nice to have some Melton comparison and to contribute with that. But then also if you have this publisher, you to be able to cite your paper already to be like, here's how this was
Yeah.
done. So depending how things go.
Should we mute the?
I unmute myself on my laptop.
No, definitely. We want to use the room mics.
Okay.
I mean, you can, and then we'll get this like.
Yeah,
on
no, we
feedback.
we don't want to be at the beginning. The beginning.
Anyway.
So. All right, well, so let's get started here. So Jed Linetsky is going to talk about the topic near and dear to my heart, actually, the North Water Polynya. So looking forward to hearing about that.
Great, yeah. So, for those of you who don't know me, my name is Jed Linetsky. I'm a PhD candidate at the Atmospheric and Oceanic Sciences Department at CU, and I work with Alexandra Young and Chris Weatherpowell, who you also heard from today. I'm going to be talking about future productive changes to the North Water Polynya. And this is work that's currently under revision for submission to environmental research letters. And I just want to acknowledge my co-authors listed below and the National Science Foundation as well. So what is, there we go, just the mic, okay. What is the North, so the North Water Polynya, which we'll abbreviate to now, or Pikialis-Swak, as it's called in Greenlandic, is one of the most productive ecosystems in the Arctic Ocean, and it reaches a maximum size of 80,000 kilometers, or around the area of South Carolina at its internal peak. And it's formed from two different mechanisms. The first is dominant northerly advects sea ice to the south, and the Nares Strait and Cane Basin to the north is very narrow, and you have a blockage of sea ice in what's known as the Nares Strait Ice Arch. And then you also have these northerly winds also further advect sea ice to the south, creating an area of open water in northern Baffin Bay. And then at the same time, these northerly winds lead to offshore Ekman transport and coastal upwelling of warm Atlantic, West Greenland, Erminger waters, which bring increased nutrients to the surface mixed layer, and also bring heat, which further reduces sea ice concentrations. We also care about the North Water Polynya because it's a nexus point of transports of sea ice and fresh water between the Arctic Ocean and subpolar North Atlantic. So just to kind of give a little bit of spatial context, on the right we have a map of the North Atlantic and subpolar circulation, and we have fresh surface. We have fresh polar surface waters exiting the central Arctic Ocean through the Canadian Arctic Archipelago, through the Barrow Strait and Nares Strait, entering the North Water Polynya region directly, which is in this black box. And then we also have fresh polar surface waters exiting the Fram Strait on the other side of Greenland. These waters travel southward, circumnavigating Greenland, eventually traveling northward into Baffin Bay, and are joined by, at depth, these West Greenland Erminger waters, which are of Atlantic origin and are warm and salty. And then on the right, on the panel on the left, we have just this zoomed in map of Baffin Bay where you can see these different ocean currents. And so this talk is going to be guided by 3 different science questions. The first is, how does the size of the North Water Polynya change under different global warming scenarios? The second is, how do oceanographic conditions in the North Water Polynya change under these global warming scenarios? And 3, what are the implications of these changes on biological productivity, or NPP? And so one unique aspect of this study is that we focus on 30-year means at specific warming levels instead of time. So we use the CSM1 large ensemble for a historical period, which we define as 1980 to 2009. And then also our highest warming level of greater than 3.5 degrees, which we use the time period of 2071 to 2100 for that time period. And then we also make use of 2 low warming simulations from Sanderson et al. 2017, which were branched from the CSM1 large ensemble in 2009. And these simulations use a custom greenhouse gas forcing to limit global temperature increases to either 2 degrees or 1.5 degrees. And so again, for these low warming simulations, we also use the 2071 to 2100 time period. And just kind of for going forward, our greater than 3.5 degrees warming level is going to be referred to as high warming, and then the 1.5 and 2 degrees C warming levels are going to be referred to as lower warming. So how do we calculate the North Water Plinia area? So we basically define our Plinia area within this red box. And we basically take the sum total of all grid cells with sea ice concentrations less than 70%. But as we know, that sea ice conditions in Baffin Bay experience a large seasonal cycle, and later in the summer, Baffin Bay becomes pretty much completely ice-free. So and a Plinia is not only defined as open water, but open water surrounded by sea ice. So we have a second region to the south in this yellow box. And basically, if average sea ice concentrations in this yellow box are less than 50%, then we consider the Plinia area to be 0, because even if there's open water in this red region, it isn't actually a Plinia, and it's just part of a larger open water area in Baffin Bay. So question 1, how does the size of the NOW change under different global warming scenarios? So in this plot, we have the seasonal cycle of North Water Plinia areas for our NSIDC observations over the historical period in black. In blue, we have the CSM1 the historical period in the CSM1 large ensemble, and then we also have our 3 different warming levels. And we see that Plinia areas in the winter are very small, and then Plinia areas really quickly increase in April and May. And then across all these warming levels, the peak area of the Plinia occurs in June, and then in July and August, Plinia areas decline, and then for the rest of the fall remain very small. And there are really two key changes that we're seeing. The first is the area of the Plinia is increasing in the spring, and the Plinia is also disappearing earlier in the summer. And we can also look at these changes in terms of probability. And so, basically, for example, in April, for the historical period, there was a 60% chance of the Plinia area being 0. But then under low warming, there's only a 25% chance of the Plinia area being 0. And then under our highest warming level, about a 12% chance of the Plinia area being 0. So the further along the x-axis you are, the higher likelihood there is of a larger area. And we see this pattern throughout the spring and summer. But one interesting aspect is that in June, in our highest warming level, we actually have a 45% chance of the Plinia area being 0. And this is because you have an earlier retreat of sea ice in Baffin Bay. So even though there's large amounts of sea ice of open water in the North Water Plinia region, the Plinia area itself is still 0. But in those cases in this high warming level, when there still is sufficient sea ice in southern Baffin Bay, the Plinia area is larger than these lower warming or historical levels. So question 2, how do oceanographic conditions in the NOW change under these different global warming scenarios? So this figure shows temperature and salinity profiles at 2 different locations in the North Water Plinia, one in the west and one in the east. And both of these temperature salinity profiles show changes at both the surface and at depth. So we see increasing stratification and increasing temperatures and decreasing salinities and surface freshening at the surface at both locations. But then interestingly, we also see increasing salinities and temperatures at depth. And this is associated with the increasing presence of this Atlantic origin West Greenland Erminger water. And so what's driving these changes? One, we looked at local sources of fresh water, and so this plot shows the seasonal cycle of land runoff into the North Water Plinia region, and we can see very large increases of freshwater of surface freshwater runoff into the North Water Plinia region as we increase warming levels. So this is the local mechanism driving the surface freshening that we're seeing. But also, Jan and Leiho in 2020 used the same climate simulations to look at freshwater fluxes in and out of the Arctic Ocean, and in particular, they found that that freshwater import into Baffin Bay through the Nares Strait is projected to increase under low warming and high warming scenarios compared to the historical levels. So freshwater import through Nares Strait into the North Water Plenary region is kind of a remote mechanism that can also be driving the surface freshening that we're seeing. And then what's driving this, the increasing prevalence of West Greenland Erminger water at depth? So we didn't look at this directly in the model, but a few different paleoclimate studies, such as Jackson et al. 2021, have theorized that basically if you have a more stratified water column, that basically allows for the increased intrusion of this Atlantic origin water. So this is a possible mechanism that we're also seeing in the paleoclimate record that can kind of give credence to this, to these increasing concentrations of Atlantic origin water that we're seeing in the North Water Plinia as we increase warming. So question 3, what are the implications of these ocean changes on productivity in the North Water Plinia? So this plot on the right shows the seasonal cycle of productivity spatially integrated over the entire North Water Plinia region. And we see that for January through March and even April, productivity is very, very low. This is because there's very little sunlight in the Arctic during this time, and that's required for productivity. And then as sunlight returns to the region in the spring, you have this very large bloom in May and June, and then leading to a peak in productivity when the nutrients in the surface mix layer are used up, and then you have a decline in productivity towards the end of the summer and fall. And so productivity is similar through all these warming levels for January through May, but under lower warming levels, the timing of the peak in productivity shifts from June to July. And we see a similar shift in productivity for our higher warming levels, but we also see a step reduction in productivity. But it's important to note that productivity across the North Water Plinia region isn't spatially uniform. So as a result, it makes sense to examine changes at a few different regions. So we chose 2 regions that kind of show the highest productivity over the historical period in the CSM1. And so we have this location in the Western Plinia and then in the Eastern Plinia. And these are the same locations that I showed the temperature and salinity profiles for earlier. So first, in the Western location, we see that productivity is similar for all warming levels for January through April. And under lower warming levels, peak MPP shifts from June to July. But under higher warming levels, we don't really see the same peak, and productivity kind of plateaus. And we believe that this is just due to the increased stratification that we saw earlier. And then if we look at the Western, at the Eastern region, we see some really interesting changes. So once again, productivity is similar for the winter and early spring, but under lower warming levels, we actually see a pretty large increase in productivity. And this is, and we hypothesize that this is due to the increased prevalence of these very nutrient-rich Atlantic waters at depth. And the reason, and the reason we see the increase in the east as opposed to the west is that this is where the coastal upwelling is the strongest from these northerly winds. But under our highest warming level, under the highest warming levels, stratification is too strong for these nutrients to actually reach the surface, so leading to a decline in productivity despite available nutrients at depth. So just to summarize quickly, under increased climate warming, the North Water Plinia will open and disappear earlier. Surface stratification will increase from Arctic freshwater input and land runoff. And warm, salty, nutrient-rich West Greenland Erminger waters will intrude deeper into the North Water Plinia region. And under low warming scenarios, productivity may increase due to more available nutrients, despite increased stratification. And under our highest warming scenario, stratification is too large to make use of increased nutrients at depth, leading to a decline in productivity. And what these results together kind of lead to is that it's really important to limit global warming to 2 degrees C in order to prevent the substantial and adverse environmental impacts in the now. So with that, I'm happy to take any questions, and thanks so much for listening.
Any questions for Jed?
Yeah, I have one. Do you have data to actually show the cycle of NPP in that observational data to show the cycle of NPP? Which you can look at?
There are unfortunately observations are a little bit limited that can kind of show a full seasonal cycle. I think there was a satellite study in 2017 that basically looked at seasonal cycle, and it wasn't the seasonal cycle directly, but they basically found that kind of the timing of the peak was around the same time that we were seeing in the model.
And one of the reasons I ask is the CSM, you're using CSM1, correct? And you're using it with the usual biology, okay. That my understanding is kind of shallow in this region, but that high latitude oceans tend to have nutrients and be light limited, that the spring blooms are triggered by the arrival of light on an already relatively high product or high nutrient layer. And so in order to actually model, really adequately model transfers within different trophic levels and to capture this very different system, that it seems worth, and Kristen just has a paper coming out on this, on modeling different trophic levels, and that it changes, and it may change like whether it's small diatoms or large diatoms. And so I was curious if you thought about that at all, and if there's like a change, not only in the timing of the bloom and the timing of the net productivity, but if you have any thoughts about changing in the like trophic transfer, or what organisms are thriving or not thriving, or just curious.
I think that's a really excellent point. We haven't really examined that yet, but I think that definitely bears looking into for sure.
Thank you.
Yeah.
So I don't know much about this region at all, so this might be a very naive question, but I was wondering, how important is the meltwater from Greenland for this area, and how is that, if that's important, how is it accounted for in the simulations?
Yeah, so we're not actually accounting for it at all, but I do think it is important. Because CSM1 large ensemble didn't have a coupled ice sheet, so we don't really have any. We're basically, the best we can do is kind of just a generalized kind of what is the runoff from land, and I'm not really an expert in exactly how it's calculated on Greenland, but my understanding is basically just kind of a hill of snow, and a little bit of it melts off every year. So it doesn't. I don't think we're coming close to really capturing the important meltwater dynamics here. There's also all these complicated interactions in terms of productivity, where if you have surface meltwater versus basal melt, and actually you can have these freshwater plumes that are bringing all this nutrients to the surface, even if you are, and you can be increasing surface nutrients while increasing stratification simultaneously. So in a dream world, I'd love to have like a super high resolution coupled ocean, sea ice, ice sheet model that could really get at these questions, but I think we're still a little bit a ways from that. But yeah, that's a really important point.
So I'll let Ed ask a question in a bit.
I have the same question as Dave.
It was the same question. Perfect. All right. Can you stop sharing maybe? And then we'll have Courtney start. So continuing on sort of the VGC theme, we have Courtney Payne.
All right. This is just really nice piggyback off of, I think, Jed's and even David's to some extent work. So as we all know, I will minimize that. As we all know, the Arctic is kind of characterized by some really severe light limitation in winter months due to the polar night and also due to sea ice cover. And that really leads to, in our kind of classic understanding, a very constrained growing period for primary production. So we kind of classically think of ice algae as being the first primary producers to emerge in the late spring. And we envision that that's followed by a phytoplankton bloom, which is generated just around the time of sea ice breakup and retreat and kind of can persist in the surface ocean through the summer months. And maybe not even using up all the nutrients in the surface ocean. Of course, this kind of vision is maybe being called into question in recent years because sea ice dynamics have changed really substantially, as you all know very well in the Arctic. So here's a photo from 1890, and sea ice doesn't always look like this now, but it can. It's substantially thinner. There are, of course, more leads, and we also have melt ponds, especially present on first-year ice. And all of this really impacts the surface light availability in the ocean. And so in 2011, there was a research cruise that was aiming to look at that pre-phytoplankton bloom dynamic in the Arctic. And they kind of anticipated, as they were going through ice, seeing waters that looked something like this, where there's a lot of ice and some light getting through it, but not a whole ton of primary production. And they ended up seeing waters that looked a lot more like this. Sea ice, entirely sea ice covered consolidated ice, but one of the largest, actually the largest phytoplankton bloom ever observed anywhere in the world's oceans. And this has really, this first observation was in the Chukchi Sea between Alaska and Russia. But in the years since this observation, this massive under ice phytoplankton bloom, we've seen that they're actually common throughout the Arctic. So here's a bunch of different locations where they've been observed. So it seems like there's kind of a need for updating our vision of what primary production looks like, what the timing of it looks like in the Arctic. So forgive me for maybe my very thick snow layer. It's not real, of course, but kind of a new vision of what primary production looks like in the Arctic is that we still have ice algae kind of as a start, the primary producers at the start of this growing season, but they've shifted earlier in the year, likely. And in many places, melt ponds allow phytoplankton and just thin ice allow phytoplankton blooms to be generated in that under ice part of the year. And in some places, by the time of breakup and retreat, the surface ocean is entirely devoid of nutrients, and phytoplankton are instead growing in subsurface chlorophyll maxima. And of course, the challenge for this is it makes it really difficult to observe these phytoplankton blooms if they're almost exclusively happening in parts of the years where we can't use satellites to look at them. Another challenge with kind of primary production shifting potentially in this way is it has some pretty big impacts on kind of biogeochemistry and trophic dynamics. So if we kind of think of the classic bloom I described in the beginning, most productivity is happening at the ice edge and into the open water part of the year. And so the ocean temperatures are pretty high, or relatively for the Arctic. And that allowed a lot of zooplankton grazing and for trophic transfer to occur and for you to get to support a lot of migrating organisms. If instead that primary production is happening in an ice-covered part of the year where temperatures are minus 1.8, that's going to reduce the amount, we think, of zooplankton grazing on that biomass and should have, unfortunately, negative consequences on some upper trophic level organisms. So I was really motivated to look into how much under ice phytoplankton blooms are contributing to total net primary production, and also how this has changed over time. And also to kind of look into some questions of biogeochemistry, and specifically, I'll show you today I'll talk a little bit today about some results of how these blooms are affecting food availability in the Chukchi. So in order to do this, I made a little 1D model, which has kind of a radiative transfer model, as well as 2 zooplankton, 2 phytoplankton, and an ice algae component. And I gave it a great name, the chaos model. And I coupled this to a physical model, GOTM, and also to a sedimentary chemistry model, Omexia. And I had deployed this model in 2 different locations in the Chukchi Sea, one in the north and one in the south. And you can see here that they're on the same advective flow path, so they should have pretty similar winter nutrient conditions. But they have very different sea ice regimes. So the location in the northern Chukchi Sea has multi-year ice covering the model location in about half the years, and sea ice retreat typically happens in late July. And of course, to the south, it's exclusively covered by first-year ice in all of my model years, which is 1988 to 2018. And also is the retreat happens 6 weeks earlier in early June. And at these 2 locations, I integrated the amount of net primary production we had in 4 distinct periods. So the ice algal period, which, although Dave has some confidence I can really improve this in CSM, I have to be honest, they aren't a big component, so I often neglect them. I'm not going to talk about them at all today. And then we also have productivity in the water column during the under ice, marginal ice, and open water periods. And that is, those are characterized by either complete ice cover or retreating ice or no ice cover at all. And over any given year, I would integrate with respect to depth for each of these periods. And now I'm going to show you kind of the relative contributions of the ice algal, under ice, marginal ice, and open water periods to total NPP. So it's probably of no surprise that these 2 places, which I've described as having really different ice conditions, have very different lengths of under ice period. So the northern location, there was growth of phytoplankton during the under ice period for about 42 days. And in the south, on average, it was only 28 days long and shrinking. So a pretty substantial difference between these 2 locations. There was, not surprisingly, some pretty big differences in net primary production between these 2 places. So here's under ice net primary production from 1988 to 2018. And the northern station is in gray, while the southern station is in black. And you can see that the northern station has about 1.5 times the NPP that the south does. And in the south, it's also diminishing over time. And that just tracks an earlier and earlier retreat and the shortening of the under ice period. And this set up pretty different total net primary production between these 2 locations. So here I'm showing a plot where I've plotted the relative contributions of each of these blooms to total net primary production. So we have ice algae, under ice, marginal ice, and an open water bloom stacked one on top of the other. And we can see that under ice blooms are a really important contributor. They account for about half of total NPP. And also we can see that total NPP is increasing over time in this northern location. And that increase was driven by years with high under ice NPP. The south looks really different. In the south, the open water period is the most important contributor to total NPP. It accounts for about 60% of the NPP in the south. And also that allows much more NPP to be generated than in the north. It's 22% greater. And the difference in the primary production really led to a difference in zooplankton grazing as well. I won't show you a plot, but the south had 2.5 times the zooplankton grazing that the north was able to support. So this work overall demonstrated to me that under ice blooms can generate half of total NPP in the northern Chukchi Sea, but that their contributions to NPP are diminishing in this more southern location. And also that under ice blooms are associated with lower zooplankton grazing. And I think this work made me realize that the Chukchi Sea is but one sea, and I was very interested in looking into the Arctic Ocean as a whole and how the distribution of under ice blooms were changing across the Arctic and where they were kind of concentrated. And in order to do this, I used satellite remote sensing of ocean color and chlorophyll specifically. So I looked at satellite retrievals right around the time to classify blooms, and I kind of specifically split I split for each pixel, 4 kilometer by 4 kilometer pixel. I split kind of the time into 2 periods, one in a couple of days following ice retreat, and one in the 3 weeks following that. And if chlorophyll concentrations were initially low and then increased over time, that indicated to me that there was an alleviation of light limitation and growth was able to be generated at a more rapid clip. And so thus I consider it to support a marginal isome bloom. If instead chlorophyll concentrations were initially high right at the time of ice retreat and then declined in the few weeks afterwards, I determined that that location supported an under ice bloom because maybe it was an indication that nutrient concentrations were being depleted in the surface ocean. And I think this metric should be relatively conservative and not and really give us confidence that the places I'm identifying as supporting under ice blooms actually had under ice blooms, because we can probably imagine scenarios where there could be productivity earlier in this period and it's still be increasing, but for it to have been generated by an under ice bloom. As my ice retreat threshold, I considered a pixel to have experienced retreat when ice cover fell to 10%. And of course, there were a bunch of places in the Arctic where ice was always 10% through my analysis. But I thus was able to classify any given pixel as either supporting an under ice or marginal isome bloom, as you can see for 2003 here, or as having insufficient observations. So that's places where I just didn't have chlorophyll, at least one chlorophyll observation during each of those two periods, due to return of sea ice cover or cloud cover or low sun angle. And then finally, I found a bunch of pixels that were ice-free consistently over time. Okay, so I ran this analysis for 2003 to 2021. And over that period, I found that 64% of the seasonally ice-free Arctic Ocean generated marginal isome blooms, which is not super, this is probably not super surprising, but maybe the more interesting result is that under ice blooms covered the remaining 36% of that seasonally ice-free and observable Arctic Ocean. And specifically, you can see that in the Chukchi Sea, there's clearly a lot of under ice bloom activity, as well as in the kind of Canadian archipelago, Beaufort Sea, and then also in Jed's favorite Baffin Bay area. I also found that under ice blooms were overall declining as a proportion of total observable area. So they covered about 41% of the observable area in 2003 and only 33% by 2021. And I was really curious about what was driving this decline in under ice blooms. So I broke the Arctic up into 10 different regions. And I looked at the relative contributions of marginal isome and under ice blooms over that 2003 to 2021 period for each of these regions. And three different regions, Baffin Bay, Chukchi Sea, and the Laptev Sea, all really drove this secular decline in under ice frequency. But really, the Chukchi Sea was once again kind of brought out of my analysis. And actually, the Chukchi Sea is kind of unusual through this analysis in a bunch of different ways. The under ice blooms were the most prevalent in the Chukchi Sea. They covered about 56% of the observable area of the region, which was an area of about 100,000 square kilometers. And they were also declining more rapidly in the Chukchi Sea than any other region. So they covered 130,000 square kilometers at the beginning of my time series, but only 66,000 square kilometers by the end, which represents a nearly 50% decline. And also lower latitudes of the Chukchi Sea were really driving that decline in under ice blooms. So this kind of tracks well with my model results. I think that there's a decline in net primary production in that, and this found a decline in area of coverage as well. So this work demonstrated to me that under ice blooms are likely generated across 40% or nearly 40% of the sea ice covered Arctic. That they're most prevalent in the Chukchi, but that the Chukchi is also driving their decline in prevalence across the Arctic overall. And I think this has some pretty important implications that modelers like you all should take into account. These blooms are really widespread, and they can substantially contribute to total annual net primary production. We also have evidence, although I haven't fully demonstrated that to you today, that they're pretty important for determining food availability and biogeochemical cycling in the region. So they have some pretty big importance in those regards. And then finally, that they are likely declining across the Arctic, and that those declines are driven by changes in coverage in the Chukchi and at lower latitudes specifically. Yeah, so thank you so much.
Great. Questions, Courtney? Keith?
Hi, Courtney. Thanks for the great presentation. How much of a role do you think there would be of lateral transport going from your southern location to the northern location? Is the bloom, your southern location, removing nutrients and stopping them from getting to the northern location?
Yeah, great question. So I have it like advection. I have advection stimulated in my model, and the nutrient loss from the south is certainly an impact, but it's not a huge impact. But I think on like the overall bloom size. However, I think that that kind of highlights another really important thing, which is that these blooms are largely happening on Arctic shelves where if you're not consuming the biomass in the water column, you're letting it export to the sediments. And in the sediments, this is something I didn't really highlight in this presentation, but in the sediments, the organic matter is subject to like sedimentary denitrification. So even if there's not a huge nitrogen loss from moving from up from southerly waters in the short term, I think there's a huge implication for a nutrient loss in the long term through sedimentary denitrification. So I imagine that waters are generally becoming nutrient poorer over time as a result of this change in biomass timing.
Thank you.
Yeah.
David, go ahead.
A question about so the sea ice model you're using, how is light transmission represented in it?
Yeah, this is the Courtney Payne sea ice model, the famous one. I have a couple different, I have spectral light with like 10 nanometer wavelength bands, and I pass it differently through different substrates like bare ice, ponded ice. I think there are like 6 or 7 different, or maybe four different ice categories and 3 different snow categories, wet snow versus dry. And the like thickness of the ice is based on kind of a ice age to ice thickness funky equation thing. Yeah, I'm not sure if I fully answered your question.
Have you compared it with the actual
It looks
transmission?
really nice compared to the actual transmission for these locations.
For those locations. Cool.
Great. Marika, do you want to go ahead?
Really nice talk, Courtney. So, so you're only computing under ice blooms for regions that go seasonally ice-free, and I appreciate that's partly a constraint of the data, right? You only have chlorophyll in those locations, but how important are under ice blooms in areas that don't go seasonally ice-free? Do you have any idea on that?
Yeah, so Jackie Clement Kinney has a nice paper on looking at under ice productivity in the central Arctic, and there ice algae are much more important than they are in kind of the more marginal Arctic seas. I think ice algae typically account for 50% of net primary production, and under ice productivity is a lot of the remainder. So yeah, so I think they aren't, I mean, they're relatively important, but in those regions, yeah, they can account for about 50% in kind of areas that are consistently ice covered. Yeah, obviously with satellites, it's difficult to get a good estimate of what's going on under the ice, but.
And I guess that argues for why we should have biogeochemistry in the sea ice.
Yes, yeah, I think so. I think that and coupling it to the water column, I think is pretty critical, because there's a lot of evidence that ice algae, which are also diatoms, are likely seeding under ice phytoplankton blooms. They have really similar photophysiology, and they're in the same species. So. And they're happening one after the other, so it's just kind of a move of in where they're growing. So I completely agree with that assessment.
So we're gonna transition to Ash for presentation, but Laura, you had a
Yeah, I just
question?
have one quick question. Thank you. That was a great talk. It's fun to know more about what you're doing. And I don't know the answer to this one. Well, you might not either, but I'm curious if, like, I was struck by how important for net primary productivity in some areas the under ice algae is. I'm also curious if it's a different like species composition than open water and whether or not there are different ecosystems or marine like ecosystems that might thrive if they get nutrients from the ones that could, the algae that contributes to under ice algae blooms versus an open water, and whether you anticipate shifts in whole appropriate transfers or species or ecosystem as we have a changing areas of under ice blooms.
Yeah, so I would say that, I mean, I have a, two functional type model that I've used, so I can tell you about my two functional types. I think diatoms are largely responsible for a lot of the, that high intensity under ice phytoplankton bloom. And we also see them migrating into the subsurface chlorophyll maximum. So a lot of the surface water is these poor, sad, little small phytoplankton that are barely growing and using the almost no nutrients that remain. And there's a fair amount of evidence too that the physiology of the species are the same from the under ice bloom all the way to the subsurface chlorophyll maximum. So it's could really be like successive generations, but it's the same community composition that's there through the year. It's just where it's happening in the water column that's changing.
Great. Yeah. Thanks. Thank you.
Great, thanks. Next we have Ash Gilbert, going to switch it up with the title a little bit, less controversial maybe. So anyway, Ash, take it away.
Yeah, so I guess certainly I'm Ash Gilbert. I work with Dan Kay at CU Boulder. And my talk today is about a breakdown of controls on observed Arctic warming using CESM2. So first I'm going to talk a little about the motivation for this and some previous work. So we know that the Arctic is warming faster than anywhere else on Earth, but the magnitude of the warming remains uncertain. You can see this highlighted in the widespread of 2050 amplification predictions from various models. We can attribute some of this spread to model differences and incomplete understanding of driving processes, but some uncertainties are unreducible due to internal variability. The graph on the right shows global and Arctic decadal temperature trends from CESM1 large ensemble for individual members, and the spread on the surface warming for 1980 to 2020 is 0.6 Kelvin per decade, all due to internal variability. And so now when we look at trends, the length of time the trend is calculated from is important to determining whether the trend is within the bounds of internal variability. For example, I have a plot here of decadal Arctic temperature trends from the CESM1 pre-industrial control, which is the black bars, and from CESM1 large ensemble members split into time periods of 1920 to 2006, which is the blue, and 2007 to 2091, the red. And the trends are calculated from 10 years of data. The distribution spread is very large, and even most trends from 2007 to 2091 fall within the minimum maximum trend values from the pre-industrial control. And so now let's look at decadal temperature trends calculated from 40 years of data. The distribution spread is now very small, and you can see that the 2007 to 2091 trend distribution is completely separate from the pre-industrial control. So when you're calculating trends, the longer time periods are better for determining when the forced response emerged from internal variability. And that's why both of my experiments and other experiments that I will review for motivation use longer model runs. So as previously mentioned by several people, as I previously mentioned, there's a large intermodal spread for the magnitude of Arctic amplification, and this is partly due to the Arctic's large internal variability and our incomplete understanding of it. One technique we can use to understand and constrain internal variability is called wind nudging, previously mentioned by several people today, where the model pushes the model U and V wind components toward observed reanalysis winds for given horizontal and vertical window. Example domain shown here, where the winds are nudged between 60 and 90 north and above the boundary layer. Wind nudging can produce the same dynamical setup across different model runs, which reduces ensemble spread, constrains the internal variability due to circulation, and thus emphasizes trends. And so now I'll talk about a couple of studies that use wind nudging to investigate the impact of winds on sea ice and temperature in the polar regions. So in a study from Roach and Blanchard-Frigglesworth, they nudged winds in the Arctic to try and improve model reproductions of Arctic temperature and September sea ice. Shown here is the Arctic surface temperature anomaly, where OBS represents the products GISS, temp, had current, and ERA interim, and LENS is all of the members from the CDSM-1 large ensemble, and LENS mean is that ensemble mean. And then the ANODGE runs are initialized from 1980 from 3 CDSM-1 large ensemble members with their winds nudged to ERA interim between 60 and 90 north and above 850 kilopascal. Their nudge runs are much closer to the observations than the LENS members and the LENS mean, and reproduce both the observed temperature trend and variability pattern. Now for the sea ice, this is the September sea ice extent, and again, the nudge runs do a much better job of reproducing the downward trend and interannual variability than the LENS mean. This work shows how important the winds are to interannual variability and the trends of Arctic temperature and September sea ice. And so switching to the other pole for a brief moment, another study from Blanchard-Frigglesworth, the nudged winds and SSTs in the Antarctic to try and explain the recent increase in sea ice that the models haven't been able to capture. Here in the CSM-1 large ensemble, the black lines show the downward trend, whereas the observations in blue show a slight increase in extent, as well as sort of an increase in interannual variability. The winds alone, the red lines, reproduce the interannual variability, but do not capture long-term trend in sea ice extent. Nudging both winds and SSTs, the pink lines can reproduce long-term trend and variability in sea ice. And now looking at temperature, you can see that both nudging experiments capture the trend and interannual variability in the temperature better than the LENS mean. This work again shows that winds and ocean temperatures are necessary to understand Antarctic sea ice trends and variability. So my research questions that I have sort of after reviewing all of this are how much of the observed warming trend and variability can we attribute to the winds alone? And how can we reproduce the full observed trend in interannual variability? And so now I want to briefly introduce the framework for thinking about my new experiments, placing them into context of previous experiments, and identifying future experiments to run. So remember, Cole's projects that previously stated is to determine how we can reproduce the full Arctic observed temperature trend and interannual variability. So let's start from a blank slate. N equals 1, where everything in the model is pre-industrial, no observed trend, interannual variability, anything. And then add N equals 1, where our winds are now nudged to observed winds. And then we have all the in-between, N equals 2, N equals 3, N to N minus 1. And then we have finally N equals N, where we have reproduced the full observed trend and variability. And so our new experiments, they'll be at this N equals 1 stage. So here are the initial results from those experiments. So these experiments had, like I said, pre-industrial climates and wind nudge to reanalysis values from 1980 to 2018 in the Arctic, a total of 39 years. And I ran one ensemble with an atmosphere-only setup and one with a coupled setup. From these experiments, I want to learn if the winds alone could reproduce the observed Arctic temperature trend and interannual variability. So first, we'll look at the trend. So here we have the near surface Arctic temperature anomalies for the observations, which we're using ERA interim data for, and for the 3 atmosphere-only members. And over 39 years, the ERA interim warms about 2.5 Kelvin, about 0.6 Kelvin per decade. And over the same time period, the atmosphere-only members warm on average about 0.035 Kelvin, about 0.01 Kelvin per decade. And then adding in the coupled runs, again, over 39 years, the coupled runs an average of 0.35 Kelvin, about 0.09 Kelvin per decade. Neither the 1850 wind nudge coupled or the atmosphere only can reproduce the trend, showing that the winds alone cannot produce the observed temperature trend in the Arctic, just starting from a pre-industrial climate. Switching to the interannual variability, we can look at the trended anomalies. We can see that the nudging the winds can explain some of the observed interannual variability, both the atmosphere only and coupled model ensembles. To quantify how much the model runs explain the observed interannual variability, we can use the R² value, sort of comparing the coupled or atmosphere runs to the area interim. And for the coupled runs, R² ranges from about 0.03 to 0.13 for individual members, and R² for the atmosphere only goes from 0.14 to 0.2. So we can explain some of the interannual variability, but definitely not all. And so looking at this framework again, n equals 0, n equals 1, which is the results we just saw, and then all the in between, and then n equals n. So now what we're interested in is the in between. How do we get from n equals 1 to n equals n? And so here's where the future experiments that we'll do will come from. So first off, I do want to do an n equals n historical run with wind nudging in the Arctic for CESM2, since all previous studies are in CESM1. To compare other experiments where we want to have apples to apples comparison. And then the first proposed experiment would keep the wind nudging in 1850 climate, but exchange the 1850 forcing, either aerosols or greenhouse gas, for historical forcing, similar to single forcing CESM1 ensembles. We may use the aerosol and greenhouse gas forcing set separately or together to test the effect of these different forcings. We also expect that adding the historical greenhouse gas forcing will enable the model to reproduce most, if not all, of the trend. And then next, I want to propose running the same experiment as on the slide before, but now the sea ice cover has been initialized to a smaller cover area than the pre-industrial cover. And we expect that with less sea ice and more ocean atmosphere exchange, the model will capture more of the interannual variability due to seasonal ice ocean feedbacks looking more like observed feedbacks. And we've also thought about initializing with the warmer ocean surface, either with the sea ice or separately. And then finally, I want to propose adding cloud locking to the previous experiment, such that the clouds have been set to either CAM 5, low opacity clouds, or CAM 6, high opacity clouds. And from previous cloud locking experiments in CESM1, locking Arctic clouds did not impact Arctic surface warming. However, CESM2 has corrected for the underestimation of supercooled liquid in CESM1, and thus has increased the radiative impact of these clouds, so we may see an effect in CESM2. We expect that with the locked clouds, the model will capture, again, more of the observed interannual variability, because we now have the added observed seasonal cycle of Arctic clouds. We also know that this additive scheme, sort of adding on one piece at a time, is not the only way to explore this problem, and have also considered the value of turning on one piece at a time. It's sort of like doing cloud locking or low sea ice or greenhouse gas forcing with a wind nudged 1850 climate, or doing a combination of these three proposed changes. So in summary, winds alone can help explain the interannual variability in the observed Arctic temperature, but do not explain the trend. And future work will determine how much the trend and variability we can attribute from these states and forcing changes. Thanks for your time, and I'm happy to take questions.
Questions for Ash?
For your n equals 3 case,
yeah,
are you nudging the sea ice to keep it small, or like are you just initializing and
initializing? I think this is sort of all very nebulous, but I think at the moment we're just thinking about initial conditions, but not necessarily forcing it. Or
How long are you gonna run for? I would think it would,
I think it'd be the same time period, 39 years.
okay. But would you just analyze the early portion or? I mean,
The whole portion.
Okay.
Yeah, really good to see these results and this work of the seeds of this project. I am a little bit surprised that your explained interannual variability is as low as it is, because we get 0.7 like in the detrended.
Yeah.
And I think you will get in 0.2 or
Yeah.
and I wonder if I know we use CSM1, but I'm not sure that that should give you such a big difference. I did notice that in your nudging domain, it almost looked like you'd used like a donut domain, and you left out the North Pole. And I mean, you should still be able to constrain that circulation of the North Pole because your nudging is not that far away. But I don't know. Like, I wonder if you've just kind of taken a step back and just compared, say, your sea level pressure trends or your wind trends in your nudge runs compared to your target, which is 0.5.
Yeah. I'll address the sort of nudging band. That was my mistake on interpreting a parameter. So I do plan to rerun those in Duratio with the full 60 to 90. So that will be fixed. As far as, but I did sort of compare the targets to model winds, and there's very under 1 meter, under 1 meter per second, differences. That's sort of for the whole 60 to 90 region.
Yeah, that's interesting. I suppose you could also just compare the internal variability regionally, right? Like make a spatial plot of that agreement between your nudge simulation and ERA5. Basically, it'd be like a correlation plot, right, of the correlation at each grid cell in the annual time series.
Yeah.
And I just went back to my paper with Oletti's paper, and because I guess we didn't really talk much about the acceleration of the trend in the temperatures compared to the CSM lens, but I do see we get about 0.25 Kelvin per decade with the nudge runs, and my first guess as to why that is probably or might be tied in with a trend in the Arctic oscillation, because that's the only thing I can think of that in terms of modes of atmospheric circulation that has had a long-term trend. And we know the AO has had this 50-year-long positive trend in observations, I think models struggle with, and that's the kind of thing that I could imagine why a observed mode of circulation variability would have given you an acceleration or some kind of change in the temperature trends, but that should be picked up by the nudge runs, right? Like you should you should see your AO index in the nudge runs going up to in observation. So that might be something useful to dig into. Or
yeah, I'll definitely look into that. Thanks.
Okay, Marika, you want to go ahead?
So just following on Ed's comments, I wonder if there's a possibility that the variability and the influence of winds on the variability of sea ice could be influenced by the mean state of the sea ice. So in the late 20th century, this time series, it's acting on a thinner sea ice pack than an industrial run. And so you could see there could be the potential that the winds are more influential on interannual changes in sea ice if the ice is thinner. And one way to look at that would just be to look at, variability in the pre-industrial climate state and variability in the lens in the late 20th, early 21st century climate state. And does, kind of similar wind patterns, wind variability, does it drive differences in the sea ice variability? So, you could kind of tease out whether that might explain some of the reason for the differences in your results versus Ed and Letty's results on the interannual variability. Does that make sense?
Yeah, that does. Thank you.
Any other questions? A minute. to let Marika cough before she presents. So, yeah, okay. Well, this is great. So Marika, do you want to try sharing your slides?
Sure. Let me see if I can just share my screen. All right, can you guys see my screen?
I can see your screen. Slides look good.
And does that still work?
No, for some reason when you hit the hide. Oh, there it is.
Is it back?
Yeah, looks good.
Okay, I can't see you guys, but that's fine. So yeah, I'm really sorry I can't be there in person because I would have loved to have been there in person. And I'm going to try and make this fairly short, in part because I think it would be useful to have a good discussion, and we're planning to end at 4. So, but before I get started, I wanted to show this amazing photo. We often show photos of the Arctic and Antarctic, where, you know, a lot of us are focused in terms of our research, but we work in this amazing place, and all of you are you know, sitting at this amazing lab. So my friend up the street took this photo a few days ago, and I told him I'm going to show it in all my talks from now on because I think it's just amazing. Anyway, so I'm going to provide a little bit of an update on these CESM2 CMIP5 simulations. And in particular, I'm kind of putting out a plea that we use some of the existing simulations that we've run, including these, but others as well, to really dig deeper into polar climate, because we have so many simulations available, and I think they're sort of underutilized by the polar research community. So, you know, so I'm going to motivate this just because of these CESM2 CMIP5 runs, but I think this is true more generally. So I'm showing here kind of how we think about uncertainty in climate projections, and this is probably familiar to most of you. You know, we often categorize that uncertainty as having 3 different sources: internal variability, so the chaotic nature of the system; model structure, the fact that our models differ and there's uncertainty in our models and how they parameterize things; and then the scenario forcing. And so you can do nice studies like this paper led by Dave Bonin, looking at, you know, the relative imprint of these different aspects of uncertainty on something like September Arctic sea ice change. Of course, we also focus a lot on internal variability, and we think about this a lot in terms of our historical runs as well. And Ash just showed some aspects of that and how we might kind of tease out or reduce that internal variability uncertainty to look at other aspects of the system. And so, of course, you know, plots like this are pretty familiar to all of us. If we look at something like a decadal trend, and that's shown here in the blue for 1920 to 1940 and black for 2000 to 2040. This is from the CESM1 large ensemble. You can see similar things from other large ensembles. Of course, you have a huge range in that trend from different ensemble members, just because of the internal variability in the system. This is things we all know. And this, of course, these things can affect things like the sea ice sensitivity. And so this is a plot from one of Patricia's papers a couple of years ago, where she's showing the CESM1 large ensemble, CESM2 large ensemble. This is the Northern Hemisphere ice sensitivity metrics, so the change in September ice area per global mean surface temperature. And you can see that, you know, there's a difference between these two models. So there's model uncertainty here, but there's also a huge internal variability as shown in the box and whiskers. And so both of these things are going to contribute to differences in how we simulate historical climate. I think what's less appreciated is that our historical forcings are also quite uncertain. And so you can see this if you just look at the different forcings that were used for CMIP5 versus CMIP6. And so I'm showing those prescribed forcings here from a number of the different forcings: black carbon, primary organic matter, sulfur dioxide, secondary organic aerosols. And you can see that prior to that blue line, so for the historical part of the runs, the forcings that we apply in our simulations are fundamentally different. We don't know these forcings completely. And so different choices are made, different forcings are used, and this of course can have an impact on our simulations. This is also true for the volcanic emissions that we apply in our simulations. And so actually, I think it grew out of one of these polar climate working group meetings. You know, the fact that this is true, the fact that Patricia had done this work showing that biomass burning emissions had an impact on the sea ice simulations. Excuse me. And so, you know, not only the mean of the emissions, but the variability in emissions, how that differs between different generations of CMIP forcing has an influence on things like the polar climate sensitivity and sea ice trends in the late 20th century or the historical period. We actually talked at this meeting about it would be useful to have these simulations of CESM2, but run with CMIP5 forcings instead of CMIP6 forcings. And so some of this was basically to address this question of what's the influence of forcing uncertainty on historical Arctic change. So I'm just going to give a very brief update showing some results from these runs. And I'm going to focus on the force signal, so just the ensemble means. And this is just, you know, done to look at CESM2 versus CESM5 and the inherent uncertainty that is represented by the CMIP6 versus CMIP5 forcings. Okay, so everybody knows, you know, we have these CESM1 large ensemble, 40 members, it's run with CMIP5 forcings. We have the CESM2 large ensemble, 50 members run with CMIP6 forcings. We also have these additional 50 members of the CESM2 large ensemble in which the biomass burning emissions were smooth. This was in part due to, you know, results like those shown in Patricia's paper that showed that increase in variability in the biomass burning in the late historical period had an impact on the simulations. And so then we've run these additional simulations, these 15 members, CESM2, so the newer model, but run with the CMIP5 forcings. Okay, so now there's been tons of work that's looked at differences between CESM2 and CESM1 large ensembles. And now we're able to actually use these new runs to attribute those differences to model uncertainty. So we can take our CESM2, CMIP5 runs minus the CESM1 large ensemble. So the only difference here should be the forcing. I think it should be the model, sorry. And then we can do the same thing for CESM2 large ensemble minus CESM2 CMIP5 to look at what that forcing uncertainty inherent in the CMIP6 versus CMIP5 forcing gives you. And then additionally, we can look at this biomass burning forcing uncertainty. This isn't the entire forcing uncertainty associated with biomass burning, but that kind of highly variable versus smooth difference. But it gives us some metric of how important the biomass burning forcing impact is on this total forcing uncertainty. And I'm partly presenting this because these new simulations have been described in this paper that's just been published or is in press. And these simulations are available. If you just Google CESM2 CMIP5 simulations, you'll find them on the web. Okay, so, and these have a big impact on polar climates. So this is the Arctic change, and I'm really just going to focus on the historical period. So this is the Arctic temperature change simulated by CESM2 for the 2000 to 2020 average period, minus this period in the early part of the 20th century. And this is the difference in that warming response in CESM2 versus CESM1 large ensembles. So the CESM1 large ensemble, CESM2 large ensemble has more warming in the Arctic and less warming in the Southern Ocean. Okay, so that's the case. Naively, you would think, well, this is because of the model, but that's not actually true. Some of it is because of the forcing differences. And so we can use these new simulations to attribute those differences to model, shown on the left here, versus forcing, shown on the bottom right. And what you see is that the reduced Southern Ocean warming that you see in CESM2 on the upper right relative to CESM1, that's largely driven by differences in the model structure. The warming, the enhanced warming that you get in CESM2 in the Arctic, however, is largely driven by the forcing. So that increased Arctic warming results from differences in the CMIP6 forcing versus the CMIP5 forcing. And that's counteracted by model structure. So actually the model structure leads to less warming in CESM2 in the Arctic. You also see this when you look at sea ice loss. So this is the Arctic sea ice cover in September. The CESM1 large ensemble is shown in red, and the CESM2 large ensemble is shown in black here. And then these intermediate runs are shown in the other colors. And what you see is that, there's a very big difference in the mean state, as we all know. CESM1 had a lot more sea ice. It looked actually more realistic. And CESM2 has much lower mean sea ice. That's largely a result of model structure, as you can see on the right-hand kind of attribution panel. But also what's interesting is that CESM1 large ensemble, actually, it has less sea ice loss for the 2000 to 2020 period than you get in the CESM2 large ensemble. And that's largely because of forcing. So the CMIP6 forcing. And about half of that could be attributed to that biomass burning forcing, and the fact that the biomass burning forcing becomes really variable with the incorporation of satellite observations in the CMIP6 forcing in the late historical period. This isn't just true in September. It's actually true year round. So this is the change in northern hemisphere ice area. Excuse me. Showing that CESM2 has larger ice loss year round. And again, that's because of the CMIP6 forcing. So there's lots of interesting Arctic things to dig into in these runs. Now, one thing that's interesting is that this larger ice area loss should drive a larger surface albedo feedback in CESM2, but that's not what occurs. So CESM2, and this is results from Jen's analysis, CESM2 has a weaker albedo feedback. This is showing the surface albedo feedback for this 2000 to 2020 period as a function of latitude. CESM2 actually has a weaker albedo feedback than CESM1, and that's a result of model structure. So the forcing is trying to drive a stronger albedo feedback. The forcing is driving larger sea ice loss, but the model structure is counteracting that. So there's, again, interesting things to dig into here, and it suggests that the CESM2 large ensemble albedo feedback, there's other things going on than just the amount of sea ice loss. And so I think this kind of motivates some of the diagnostic discussion that I think we're going to have, and also some of the other work that people are doing to try and improve the model. So of course, changes in ice area are important for the albedo feedback and the albedo response, but changes in the albedo of the sea ice are also very important. And so these changes in ice area are not what's leading to this late historical period difference in the CESM2 large ensemble versus CESM1 large ensemble albedo feedback. Instead, it's suggestive that it's this change in how the model is treating the surface of the sea ice itself. And there's some, I'm just going to skip over this one because I think people know this, but there's some importance, there's some reason to suspect that snow on top of the sea ice is part of that story. This is some of Melinda's work showing that CESM2 has a thinner snowpack and a longer snow-free season than CESM1 large ensemble. So that can affect how the albedo changes with a loss of snow cover might affect the surface albedo feedback with you just having less snow to lose, a longer snow-free season. There's less capacity for a strong snow influence on a change in albedo in a warming climate. And there's also good reason to think that some of our problems with ponds that David has talked about in an earlier talk are also important. So, you know, we have too much ponding, but those ponds don't look all that much different from bare sea ice when you think about their albedo, because they're only centimeters thick. So this is very problematic, but it also means that as ponding changes in a warming climate, we're not going to get an albedo feedback associated with that in CESM2 like we should. So I think this really motivates why we're focusing on things like snow on sea ice, the ponded ice cover, and its optical properties. Okay, so basically I've just kind of given you some teasers and some thoughts on why simulations like this CESM2, CMIP5 runs are useful. And I want to note that historical forcing uncertainty is sizable. It complicates the comparison of simulations across CMIP generations, and also the comparison with observations, because we know we aren't, you know, there's uncertainty in our forcings that we're using to just drive our historical runs. In CESM2, the large ensemble, the CMIP6 forcing drives increased early 21st century Arctic warming and sea ice loss. But also the surface albedo feedback is weaker despite that larger ice area loss. So there's interesting things to dig into further here. And it also motivates, you know, looking at things like the ice surface properties. So analysis of CESM2 and CESM1 and CESM3 simulations is needed. And we need some more focus on things like snow climatology, possibly episodic snowfall events, on fractional coverage and their optical properties and their depths. And you know, so this is in part to try to motivate thinking about diagnostics and what should we really be looking at when we're evaluating CESM3, which is coming up soon, as Dave mentioned. And I also just want to note that I'm hopeful. I hope that people go and use these CESM2, CMIP5 simulations. There's already been some nice work done by David Schneider, and Patricia's looked at them and others, but I think there's a lot more to do. I also really want to note that we have a lot of other potentially useful simulations that I think our community should be using, like the single forcing large ensemble. There's a CESM2 single forcing large ensemble. Isla Simpson has a paper documenting those. There's high resolution runs, these 10th degree ocean model runs, quarter degree atmosphere model runs. They're known as the IHASP runs. I think there's more work that can be done with that, although there are some issues with the mean state biases in the Arctic. And then things like our prediction ensembles, like the single multi-year large ensemble. So that's basically where I want to end. And I wanted to, you know, use that to motivate our discussion, thinking about diagnostics and what kind of diagnostic needs we have, what experiments we should be thinking about running. I mean, we're hearing so much work being done with these nudged experiments. You know, should we have some standardized nudged experiments that we're considering as a working group, and also future modeling needs? And I think we've heard some nice work today already on some of the things that people are pursuing. So I'm happy to take questions. I'm gonna go out of full screen mode so I can see you guys. And I guess I'll leave it there. So yeah, maybe I'll stop sharing my screen. So
Great.
But thanks everyone. I'm happy to take questions.
Thanks, Marie. Questions for Marika? John.
Hi, Marika. I'm wondering, from observation perspective, which model has better albedo feedback, CSM1 or CSM2?
I think that's kind of hard to answer because of the internal variability question. And so, yeah, so I mean, if you look at, so what I showed you was the ensemble mean albedo feedback from these different variations of CSM1, CSM2, but there's a lot of spread in the 2000 to 2020 albedo feedback strength, and in the sea ice loss, and in the Arctic warming, and all of those things. And so I think it's actually quite challenging to figure out where we are relative to observations because of that internal variability.
Okay, thank you. I will quickly add that this has implication for glacial climate simulation. So for glacial climate, we have a lot of sea ice, so the albedo feedback is quite important. And I noticed similar difference in abrupt 4x CO2 simulation. So basically, the albedo feedback in CSM1 is 2 times the albedo feedback in CSM2. Big difference. Thank you.
I think it does argue that we should be getting our albedos and the factors that drive the albedos in sea ice better simulated.
Go ahead. Hi, Marika, this is Ed. Thanks for the talk. Hope you're feeling better. Just a quick practical question. Is there a component set for running CSM2 with the CIMIC 5 forcing?
There's not a comp set, but there is on the website, we have documentation on how to do those runs. And so Cecile Hene actually did most of the runs and help with the run setup. And so we have a website that basically tells you, and gives you the name list changes and all of those things that you need to do to set up a CESM2 CMIP5 run. Okay. And Dave did the last 5 ensemble members of these too. So, if there's interest in adding ensemble members or doing something with also wind nudging, or I don't know, I think there would be resources to help set those up.
Well, I think Ed and I had a discussion at the break, basically, that, we should do a CSM3 CMIP6 set of runs, before we get the new CMIP7 forcing too, so that we can also, have a similar constraint on this, because as soon as we get that new forcing, all bets are off.
Well, and honestly, this came up in the CESM2 development, right? And we were developing CESM2, but we didn't have the new forcings yet. And so we were using CMIP5 forcings to run our CESM2 historical runs in our development sequence. And things look great. And then we put in the CMIP6 forcings, and we got global cooling. And so, so this, we kind of had hints that this was an issue. Right. That the difference in forcing was leading to some actually large scale differences in the climate. But we're also we don't have a lot of control over the timeline to put together CMIP forcings.
Yeah.
Or the process, although there's some people in the CESM community that are involved in that process. But some of the decisions made are a mystery to me, like why change the variability in the biomass burning emissions? I mean, that was just, I don't know if there was discussions about it or if it was just one person went and did it and it ended up in the forcing, but anyway.
Alice.
I guess my question, when you were presenting, Dave, you talked about there's going to be a code freeze in June-ish, presumably of this year.
Say a year.
But you were saying it's going to take a lot longer to get these forcings. So I haven't been going to the CESM project, formerly co-chairs meetings, right? Because I have enough meetings. But has there been discussion that you guys, there's general desire to freeze the code, release CESM3, and then when the CMIP7 forcing is available, that presumably CESM3 will be used, but it's not being developed around the CESM. CESM3 is not being developed around the CMIP7 forcing.
Correct.
Okay.
Yeah, yeah. And I think that's slightly different than CSM2. I think
Yeah.
we were kind of developing CSM2. And then as Marika highlights, you know, we were running with CMIP5 forcing, and then all of a sudden, oh, here's the CMIP6 forcing, and we changed right over. So it definitely changed our CSM2 development. So I think Dave Lawrence, the current chief scientist, has decided that we're going to release a CSM3 that's going to have CMIP6 forcing, and that'll be later this year sometime, maybe early next year. But then when we get the next forcing, the CMIP7, there will be a 3.1 or a 3.2 or something like that. So I think that we can easily sort of draw a line and say, this version of the model, we understand pretty well with the current forcing that we have. So
okay,
I think, yeah. Alex?
I think Dave was first.
Oh, okay. You can go ahead. Yeah.
Just like to kind of come back, I think there's a lot of value for like having these runs with the CMIP6 forcing, because the forcing will change again, and then we have that question again, is it the model is, and so I think especially with the timeline working out that way, I think that makes a lot of sense to have those runs so that we can do the kind of experiments Mariko was showing, or kind of analysis that Mariko was showing, but not 2 years after, but like right at the beginning when the CMIP7 forcing comes out and those runs come out, we can kind of really assess that from the ground up.
Right. Sorry, David.
No, that's more relevant. But relatedly, this question of variability, I mean, I recognize we might not have much influence over the CMIP7 forcing, but when we have forcings that we know are variable temporally, we just don't necessarily, like the biomass burning, we know it was temporally variable before the satellite record. We just don't have direct measurements of it.
Right.
Should we push for that variability to still just be included in the forcing, even if we don't know exactly like when the peaks or troughs were?
I mean,
or should we push for it to always be smooth, or like?
Yeah.
I mean, I think it's a really open question. Honestly, I think it's very hard, and that, you know, those biomass burning emission variability are also climate variability driven, and so, you know, they should go with a certain soil moisture state and things like that. And if you apply them to all ensemble members, regardless of that, you're probably missing some feedbacks and stuff too. So I honestly don't know what the right answer is. I mean, we know biomass burning emissions should be variable, right? They are variable. We have some data to show how variable they've been over the recent period. But I mean, yeah, it's hard. What we really need is like interactive fire models, and people are working on that, but so I'm not sure what the right thing is to suggest with biomass burning emission variability, or if you do something different. I don't know. It's a hard question, I think.
Yeah, I think it's really tough, and we have representatives from NCAR who are on this committee determining the forcing and things like that. But I think, you know, as Marika alluded to, there are still sometimes data sets where there's a single person sort of involved in producing something. And I don't know, and at one point, Marika, we talked about actually developing like a forcing diagnostic package or something, so that when we receive it, we should be able to run it through this diagnostic package to get an assessment of, you know, maybe some early indication of how it might influence the model. But yeah, I don't know.
I mean, I've been arguing that for a long time, partly because we often, when we have errors in our runs setup, it's often because we're not using the right prescribed forcing. Like it's come up multiple times where we've had to like throw away a bunch of runs because someone didn't set the right path to the right aerosol emissions or something.
Right.
And so if we had a forcing diagnostic package, you could quickly look and go, oh yeah, that's the aerosol emissions I want.
Right.
We don't have that. I keep trying to bring it up, but in the context of diagnostics, so back to the discussion topics, diagnostics, I think that would be a good thing to have.
Yeah. Yeah.
I'm trying to take notes.
Yeah, I'm kind of taking notes too. So the other funny piece to this too, is that we will be doing prognostic CO2 for all of our CMIP experiments. So this is a new thing. We'd always prescribed the CO2 levels well mixed globally, but now we're going to have a prognostic CO2 component in the atmosphere for all of our runs. So this is what used to be called the sort of Earth system model type experiments, but that's going to be the default going forward. And so we're a little worried about that too, because you're initializing in 1850 and you're running prognostic CO2 forward. Hopefully we end up in 2020 similar to, so
Get our under ice blooms just right.
Yeah.
No CO2.
And so that's going to be the actual radiatively active forcing, not just an output that runs along.
Yeah. So we have
We definitely need diagnostic.
We did these for the
analysis.
last CMIP. We did one or two where it was prognostic CO2, the ESM runs. And so, and in general, we got, pretty close to present day CO2 and temperature, but that's going to be a curious side thing. So
We have a prognostic industrial economy.
I mean, whatever. Sure. No, not yet, but you're prescribing the surface emissions basically. So,
Not the, okay.
so that's what's there.
But it's only the CO2.
But the CO2 in the atmosphere will be allowed.
And the other greenhouse gases are still prescribed? Prognostic too,
I
like methane.
think that's a good question. I think like aerosols are going to also be predicted, computed, and not prescribed. So
Which is what's done, but I don't know about, I don't know about all greenhouse gases.
Right. Yeah. Heath, you have an answer.
I'm pretty sure that CO2 is the only greenhouse gas that's going to be prognostic.
Okay.
I don't think any Earth system models have a comprehensive methane coupled methane model that would allow them to prognostically compute it. Whereas it's much more common to have a fully coupled carbon cycle.
So I think the other reason to have this diagnostic discussion is, I'm developing this new notebook. I'm doing a lot of work on this, and I think this is a great opportunity to rethink things. Are there people who have access to new data sets, tools for analyzing them, and I think maybe more importantly, give me help with this, because I think I'm kind of doing this all on my own right now, and I'm just following the example of the old diagnostic package, but I'm open to suggestions and thoughts on how to re-envision this again.
And I think it would be useful to think about kind of process level diagnostics.
Yeah.
So, I mean, we do a lot of maps and time series, but, are there distributions, things that we should be looking at that give us a better appreciation for the quality of the simulation?
And on that note, are you thinking of doing any scoring or ranking, in the CVDP, and then John Pasulo has a separate package where he ranks the different models or different ensemble members against some observational benchmark? Is there any thought of doing that within the polar diagnostics?
There's definitely thought about it. We're just not sure the best way to do it, but I think, definitely more of those quantitative measures would be very useful here, I think. And we started to get there with some of Alex's work on bringing in the ISAT distributions and looking at PDFs of ISAT thickness versus model thickness. And so you could get a better quantitative idea instead of these very qualitative math sort of things too. So Alice, you have a thought or?
Not necessarily.
Okay.
I think it's worth having, and I can help with this, but having the diagnostic package output things that we don't necessarily have gridded products to compare with.
Yeah.
Like, for example, take an obvious one, pond depth, right? If that had been an output earlier on in some diagnostic package, we probably would have realized far sooner that the ponds are, you know, centimeter to millimeter. But you can imagine doing similar things with like ice salinity profiles or stuff like that, where we might not have a like gridded data set that we can compare with, you know, temporally resolved. But if your ice salinity profile is totally wrong, or, you know, your upper ocean stratification is totally off, like knowing that pretty soon in diagnostics would be probably a helpful point to have.
Yeah, and I was definitely trying to go for expanding the variables available by having this YAML list. So, you know, somebody comes along and puts a new variable in there with contour levels, everything. That'd be great.
I think the key is getting input on what those should be.
Yeah.
You know, if you go look, there's like not infinite, but you know, like many things that could be done. And then you get, as Dave was showing, and then like more plots.
Yeah.
You know, so then it can be a lot. I was just going to say what I was thinking, but I was not actually raising my hand when you called on me. Just adding the capability, like the old diagnostics, and to some extent the current diagnostics are set up to compare one run versus another.
Yeah.
And just having more capabilities in there of comparing to like ensembles or, you know, distributions and spreads in there, especially if there's like, okay, we're going to look at ice salinity profiles and maybe we don't have a lot of observations of that, but just see like, okay, what's the spread of this in the model as well, whether it's spatial average or temporal average or whatever.
Yeah.
Are you gonna have like a Google Doc or some public doc that people can put their favorite metrics or a poll?
Yeah.
It's on GitHub already. You can open an issue.
Yeah, I mean,
feature request.
Why don't you have diagnostic?
I have on that Cupid page, I have a sea ice related issue already. So that's a place for discussion, but I agree, maybe a Google document too, to just, you know, I think we need to be careful. We've done this before where we had our sort of wish list for diagnostics and observational model comparisons. You know, Jen and Alex were involved in these, and I think the thing is we don't want them to just go away, you know. So we need to think about exactly how we want to try to get these in, and then I will say the caveat too that, you know, there's a time variance here. You know, right now we're developing CSM3. We just want to know if the lab C is freezing over or not. You know, that's our number one priority, is just getting a stable pre-industrial condition. However, later we're going to start generating a bunch of historical runs. And I think there we're going to want to do a more sophisticated analysis of saying, you know, how does our 20th century look compared to these metrics and things like that? So there's a little bit of that, but I'm definitely open to trying to add some things. So.
And do you have like snow thickness, since we know that that's been an issue in the
Yeah,
past?
snow thickness is there. Yeah, not snow fraction, but snow thickness is there. You know.
But we don't have the nice plots like Melinda's comparison to the iceberg observations and things like that. And I think, you know, that would be a nice thing to add. I mean, in Melinda's CSM2 snow paper, she has these nice plots with comparisons to not gridded products. You know, some of them are just point products, but
you could do something similar maybe with like Mosaic, right? Where you just automatically run, you know, like you sort of track whatever grid cell that was a Mosaic, and you get like a spread of like model results, like an ensemble mean, ensemble spread, and you know, this is what we measured in Mosaic for whatever variable. And that might be a pretty efficient way of like validating or getting a sense of, you know, the model's yeah, something like the pond depth that if we had that metric quite quickly, I think. I mean, at least Dave would have been like,
Yeah,
wait a second.
yeah.
I think Alec had his hand up too. I just want to.
Sure, Alec, go ahead.
Oh yeah, thanks guys. Yeah, I've just wondered. I'm not too familiar with the old diagnostics package, but I know in the forecast world, I've seen like ECMWF kind of put out these scorecards where there are like key metrics and yeah, like accuracy assessments, and then it's just like a much more visual display of a lot of things all at once to kind of get a sense of how a given forecast compares to another one. Is that the kind of end goal of some of this, or? Because some of the stuff you were showing, Dave, to me looked more like, yeah, analysis and kind of exploration of the data rather than like this kind of quick.
Oh yeah, we have not been terribly quantitative to date.
Okay.
You know, and I think a lot of it is, you know, just not my vision, maybe not being clear enough on this and seeing ways to do this. So that's why we're looking for creative input on this and ways to do this better. So I think there is, I will note this ILAM package that the LAN put out, and this was an international collaboration, and they have this sort of thing. They have a scorecard, and you know, they have these metrics of how well is the surface temperature simulated, how well is the soil temperature simulated, and that sort of thing. And so it gives you a much more quantitative idea of how maybe two model runs are comparing and things like that. But these ensemble ideas are great too. You know, that's some of that's in the CVDP, the climate variability package, but you know, but we can certainly expand upon that. Yeah.
I know it's 4, so I'll keep it relatively brief. But I was gonna say part of it, just to point out, with putting together like a skill card or like things like that, is we don't have like special dedicated person with funding for that. It's mostly Dave, and probably I will help with some of it, and we will ask other people to provide input. But it's not like, oh, we're hiring a couple people to help with that. So I think there are some limits there, and to some extent, you know, maybe it can grow over time, but I don't think it's going to be like something really fancy, like a fancy website with all the things. But the other thing I was going to say, I would also advocate in terms of people like, I don't know what the answer is right now, but I think we should have one centralized place that people put, like if you want to add something, it goes through GitHub, because I think if we have multiple paths, it's just one of them will get forgotten about. And so I would strongly advocate for that. And I think that can be a discussion, how that it'll be done, but then we can try to communicate that to the community.
I mean, I haven't said much about it, but I will say that I've been doing work with Emma on a separate benchmark package, which is much more quantitative. And we've been specifically focusing it on our Navigating the New Arctic project, but I think that there is still going to be potentially a greater use out of this type of package as well. So
I guess my other concern is that that can easily turn into like the places you're interested in for your navigation. You say, oh, this is better than that. And people say, well, now this model is better, but there's so much more nuance in that. That's one of the reasons I feel worried about. Anyway.
Yeah, go ahead.
I just wanted to come back to what Marika said. I think there is some value to have these nudged runs as another way to kind of see how the model is doing, both for the Arctic and the Antarctic, I think. So, and having that as a community resource, kind of then start from for sensitivity runs that people want to do. I think that would be a cool new thing to kind of do.
Yep. Marika?
Yeah, I was going to talk about the benchmarking stuff, but I agree with you, Alex. I think there's lots of, you know, I think we could think about with CESM3, whether the Polar Climate Working Group should spearhead doing some nudged wind runs. And we probably, you know, want a lot of input from Ed and Letty and Ash and Jen's group, you know, Xinhua, all the people that have been doing these runs. So to try and do something that would be useful for everyone. I was also going to say about the benchmarking or a skill card or, you know, that kind of thing. I think that might be the type of thing that would lend itself to maybe a proposal to some group to help fund. I mean, it depends on how big it is, but I could see there's so many cool satellite products that we're not really well utilizing.
Yeah.
Maybe there's some way we could work together to actually get some funding resources to do this in a better way than just relying on Dave.
Well, there's also this thing kind of led by David Nealon, the Model Diagnostic Task Force, and I've had to present to them, and they're supposedly providing some sort of resource too. So anyway, so all right. Well, before David, is there anyone else who has something burning that they want to bring up? Because we're running out of time.
No biomass to burn?
All right, David, we'll let you have the closing word.
Oh, well, that's appropriate, but just on this topic, don't forget about the buoys either, right? Like they are not a straightforward way to, right? They're not a straightforward data set in the way of some of these other things, but it's, there's one Mosaic, there's one Sheba. There's actually a lot of Russian drifting stations. They were a good way to compare with those data. But there's lots and lots of buoys that have been deployed. I know Ellen McElhatton, UW is working on some of that, but like factoring that in with any of these diagnostics, I think could be especially helpful because we know some of the reanalysis products have pretty severe biases. In CIs. So
the other UW, by the way, that was Wisconsin. Anyway, so with that, I think we'll close. Marika, do you have any final remarks or?
I'm in the middle of a coughing fit, but thanks everyone. It was really great to see you, if only virtually, but hopefully we see you in June too. And I hope you all are like going to Southern Sun for Stout Month or something, but I won't be joining, so.
Yeah. All right. Well, thank you all. And so do send your presentations to Elizabeth when you get a chance. So, all right. Yeah.
I was kind of thinking I would work from home and then
From there,
I was to be determined. I had an appointment in West Noonish, so that's why I
still don't understand exactly what the point was. Just they asked me to give a presentation on what we're
Did you want to talk about work stuff or just?
and then he just kept saying, let us know anyway.
Through the ice.
Yeah. I will.
I don't know. I don't
Email
understand.
and we can, yes, I will be around on Thursday, one way or the other.
Probably.
And I'm
You're
live
about
close
to
enough
get
to
that.
hear
Certainly one of
So, thanks all.
Logistics.
and I
I am
other periods.
I am clear to stay Friday night.